Mastering Blockchain, a deep dive into distributed ledgers, consensus protocols, smart contracts, dApps, cryptocurrencies, Ethereum, and more, 3rd edition. Written by Imran Bashir. Narrated by Telly Frias Jr. Chapter 1. Blockchain 101. It is very likely that if you are reading this book, you already have heard about blockchain and have some fundamental appreciation of its enormous potential. If not, then let me tell you that this is a technology that has promised to positively alter the existing paradigms of nearly all industries, including, but not limited to, the IT, finance, government, media, medical, and law sectors. This chapter is an introduction to blockchain technology, its technical foundations, the theory behind it, and various techniques that have been combined together to build what is known today as blockchain. In this chapter, the theoretical foundations of distributed systems are described first. Next, the precursors of Bitcoin are presented. Finally, blockchain technology is introduced. This approach is a logical way of understanding blockchain technology, as the roots of blockchain are in distributed systems and cryptography. We will be covering a lot of ground quickly here, but don't worry. We will go over a great deal of this material in much greater detail as you move throughout the book. The growth of blockchain technology. With the invention of Bitcoin in 2008, the world was introduced to a new concept which revolutionized the whole of society. It was something that promised to have an impact upon every industry. This new concept was blockchain, the underlying technology that underpins Bitcoin. Some describe blockchain as a revolution, whereas another school of thought believes that it is going to be more evolutionary, and it will take many years before any practical beliefs of blockchain reach fruition. This thinking is correct to some extent, but in my opinion, the revolution has already begun. It is a technology that has an impact on current technologies too, and possesses the ability to change them at a fundamental level. Many prominent organizations all around the world have moved on from the proof of concept stage and are already writing production systems utilizing blockchain. The disruptive potential of blockchain has now been fully recognized. For example, decentralized finance, DeFi, has recently emerged as a new disruptive idea that aims to decentralize the existing financial system. DeFi offers individuals more control over their assets, allowing them to fully own and operate their financial strategy on blockchain without requiring any intermediaries. This is already challenging traditional finance by creating decentralized platforms for trading, investment, insurance, payments, and lending. A glimpse of the potential of DeFi can be seen at DeFiPulse.com. A noticeable fact is the amount of total value locked in the system, which is almost $5 billion US. However, some organizations are still in the preliminary exploration stage, though they are expected to progress more quickly as the technology matures. Progress toward maturity. If we look at the last few years, we notice that in 2013, some ideas started to emerge that suggested that blockchain may have the potential for application in areas other than cryptocurrencies. Around that time, the primary usage of blockchain was in cryptocurrency spaces, such as Bitcoin and Litecoin, and many new coins emerged during that period. Cryptocurrency can be defined as a digital currency that is secured by cryptography. The following graph shows a broad spectrum outline of the year-wise progression and adoption trends of blockchain technology. The years shown on the x-axis indicate the range of time in which a specific phase of blockchain technology falls. Each phase has a name that represents the stage at which the technology was reached. And this is shown on the x-axis starting from the period of ideas and thoughts in 2013 to eventually maturity and further progress expected in 2025. The y-axis shows the level of activity, involvement, and adoption of blockchain technology. The graph shows that by roughly 2025, blockchain technology is expected to become mature and have a high number of users. The preceding graph shows that in 2013, ideas and thoughts emerged regarding other usages of blockchain technology apart from cryptocurrencies. Then in 2014, some research and experimentation began, which led to proofs of concept, further research, and full-scale trial projects between 2015 and 2017. In 2018, we saw real-world implementations. Already many projects are underway and set to replace existing systems. For example, the Australian Securities Exchange, ASX, is soon to become the first organization to replace its legacy clearing and settling system with blockchain technology. More information on this topic can be found at www.asx.com. Another recent prominent example is that of a production-ready project implemented by Santander, where the first end-to-end blockchain bond has been issued. This is a significant step toward the mainstream adoption of blockchain. It is expected that during 2020 more research will be carried out, along with an increasing interest toward the regulation and standardization of blockchain technology. After this, production-ready projects and off-the-shelf projects will be available utilizing blockchain technology from 2020, and by 2021, mainstream production-level usage of blockchain technology is expected. Progress in blockchain technology almost feels like the Internet.com boom of the late 1990s. In the next few years, research in the scalability of blockchains, where blockchains will be able to handle a large number of transactions similar to traditional financial networks, is expected to become more mature. Also, during the first few years of the 2020s, we will see more production-level usage of blockchain addressing issues such as privacy, decentralized identity, and some progress toward the decentralized web or Internet decentralization. Note that such solutions already exist but are not in mainstream use. The mainstream usage of such technologies is expected from the start of 2020. It is expected that, at the start of the next decade, research in such areas will continue along with the adoption and further maturity of blockchain technology. Finally, in 2025, it is expected that the technology will be mature enough to be used on a day-to-day basis by less tech-savvy people. For example, blockchain networks can be used as easily and naturally as consumers using the Internet now. Further research is expected to continue even beyond this point. Please note that the timeliness provided in the chart are not strict and may vary, as it is quite difficult to predict when exactly blockchain technology will become mature. This graph is based on the progress made in recent years and the current climate of research, interest, and enthusiasm regarding this technology, which can be extrapolated to predict that blockchain will progress to become a mature technology by 2025. Increasing interest. Interest in blockchain technology has risen quite significantly over the last few years. Once dismissed simply as geek money from a cryptocurrency point of view, or as something that was just not considered worth pursuing, blockchain is now being researched by the largest companies and organizations around the world. Millions of dollars are being spent to adopt and experiment with this technology. This is evident from recent actions taken by the European Union, where they have announced plans to increase funding for blockchain research to almost €340 million by 2020. Another report suggests that global spending on blockchain technology research could reach $9.2 billion by 2021. Also, the interest in blockchain within academia is astounding, and many educational establishments, including prestigious universities around the world, are conducting research and development on blockchain technology. There are not only educational courses being offered by many institutions, but academics are also conducting high-quality research and producing a number of insightful research papers on the topic. There are also a number of research groups and conferences around the world that specifically focus on blockchain research. This is extremely useful for the growth of the entire blockchain ecosystem. A simple online search of blockchain research groups would reveal hundreds, if not thousands, of these research groups. There are also various consortiums such as Enterprise Ethereum Alliance, EEA, at entethalliance.org, and Hyperledger at hyperledger.org, which have been established for research, development, and the standardization of blockchain technology. Moreover, a large number of startups are providing blockchain-based solutions already. A simple trend search on Google reveals the immense scale of interest in blockchain technology over the last few years. It should be noted that the decrease shown at the end of the graph does not necessarily directly translate into the decreased interest in blockchain technology, but it simply captures the fact that the search term was searched fewer times as compared to late 2017 and early 2018. This could be simply due to the fact that people interested in blockchain technology have already understood enough about blockchain to no longer warrant searching for it on Google. We do see, however, a significant and continued interest in blockchain technology. Various benefits of this technology have already been envisioned, such as decentralized trust, cost savings, transparency, and efficiency. However, there are multiple challenges too that are actively being researched on blockchain, such as scalability and privacy. In this book, we are going to see how blockchain technology can help to bring about the benefits mentioned previously. You are going to learn what exactly blockchain technology is and how it can reshape businesses, multiple industries, and indeed everyday life by bringing about a plenitude of benefits such as efficiency, cost savings, transparency, and security. We will also explore what distributed ledger technology, DLT, is, decentralization and smart contracts, and how technology solutions can be developed and implemented using mainstream blockchain platforms such as Ethereum and Hyperledger. We will also investigate what challenges need to be addressed before blockchain can become a mainstream technology. We'll also take a critical look at blockchain. Chapter 21, Scalability and Other Challenges, is dedicated to a discussion of the limitations and challenges of blockchain technology. We shall begin our exploration of blockchain by looking at distributed systems in the following section. This is a foundational paradigm used with blockchain, and we must have a firm grasp on what distributed systems are before we can meaningfully discuss blockchain in detail. Distributed systems. Understanding distributed systems is essential to our understanding blockchain, as blockchain was a distributed system at its core. It is a distributed ledger that can be centralized or decentralized. A blockchain is originally intended to be, and is usually used as a decentralized platform. It can be thought of as a system that has properties of the both decentralized and distributed paradigms. It is a decentralized, distributed system. Distributed systems are a computing paradigm whereby two or more nodes work with each other in a coordinated fashion to achieve a common outcome. It is modeled in such a way that end users see it as a single logical platform. For example, Google's search engine is based on a large distributed system. However, to a user, it looks like a single, coherent platform. A node can be defined as an individual player in a distributed system. All nodes are capable of sending and receiving messages to and from each other. Nodes can be honest, faulty, or malicious, and they have memory and a processor. A node that exhibits irrational behavior is also known as a Byzantine node, after the Byzantine generals' problem. The Byzantine generals' problem. In 1982, a thought experiment was proposed by Lamport et al. In their research paper, The Byzantine Generals' Problem, which is available here. In this problem, a group of army generals who lead different parts of the Byzantine army is planning to attack or retreat from a city. The only way of communicating among them is via a messenger. They need to agree to strike at the same time in order to win. The issue is that one or more generals might be traitors, who could send a misleading message. Therefore, there is a need for a viable mechanism that allows for agreement among the generals, even in the presence of the treacherous ones, so that the attack can still take place at the same time. As the analogy for distributed systems, the generals can be considered honest nodes.
the traders as Byzantine nodes, that is, nodes with arbitrary behavior.
And the messenger can be thought of as a channel of communication among the generals.
The problem was solved in 1999 by Castro and Liskov, who presented the practical Byzantine fault tolerance (PBFT) algorithm, which solves the consensus problem in the presence of Byzantine faults
in asynchronous networks by utilizing the state machine replication protocol.
PBFT goes through a number of rounds to eventually reach an agreement between nodes on the proposed value. PBFT and other consensus protocols will be discussed in greater detail in Chapter 5, Consensus Algorithms. This type of inconsistent behavior of Byzantine nodes can be intentionally malicious, which is detrimental to the operation of the network. Any expected behavior by a node on the network, whether malicious or not, can be categorized as Byzantine. A small-scale example of a distributed system is shown in the following diagram. This distributed system has 6 nodes, out of which 1 and 4 is a Byzantine node, leading to possible data inconsistency. L2 is a link that is broken or slow, and this can lead to a partition in the network. The primary challenge of a distributed system design is the coordination between nodes and fault tolerance. Even if a certain threshold dictated by the consensus protocol of the nodes become faulty or network links break, the distributed system should be able to tolerate this and continue to work to achieve the desired result. This problem has been an active area of distributed system design research for many years, and several algorithms and mechanisms have been proposed to overcome these issues. Distributed systems are so challenging to design that a theory known as the CAP theorem has been proven, which states that a distributed system cannot have all 3 of the much desired properties simultaneously, that is, consistency, availability, and partition tolerance. We will dive into the CAP theorem in more detail later in this chapter. Even though blockchain can be considered to be both a distributed and decentralized system, there are, however, critical differences between distributed systems and decentralized systems that
make both of these systems
architecturally different. We will discuss these differences in detail in Chapter 2, Decentralization. With a better understanding of distributed systems, let's now move on to talking about blockchain itself. We'll begin with a brief rundown of the history of blockchain and Bitcoin. The history of blockchain and Bitcoin. Blockchain was introduced with the invention of Bitcoin in 2008.
Its practical implementation then occurred in 2009.
For the purposes of this chapter, it is sufficient to review Bitcoin very briefly, as it will be explored in great depth in Chapter 6, Introducing Bitcoin. However, it is essential to refer to Bitcoin because without it, the history of blockchain is not complete. The events that led to blockchain. Now we will look at the early history of computing and computer networks, and we'll discuss how these technologies evolved and contributed to the development of Bitcoin in 2008. We can view this in chronological order. 1960s, invention of computer networks. 1969, development of ARPANET. 1970s, early work on secure network communication including public key cryptography. 1970s, cryptographic hash functions. 1973, extension of ARPANET to other geographic locations. 1974, first Internet Service Provider, Telenet. 1976, Diffie-Hellman work on securely exchanging cryptographic keys. 1978, invention of public key cryptography. 1979, invention of Merkle trees, hashes in a tree structure by Ralph C. Merkle. 1980s, development of TCP/IP. 1980, protocols for public key cryptosystems, Ralph C. Merkle. 1982, blind signatures proposed by David Chaum. 1982, the Byzantine generals problem. Bitcoin can be considered a solution to the Byzantine generals problem. However, the original intention of the Bitcoin network was to address the previously unsolved double spending problem. 1985, work on elliptic curve cryptography by Neil Koblitz and Victor Miller. 1991, Haber and Stornetta work on tamper-proofing document timestamps. This can be considered the earliest idea of a chain of block or hash chains. 1992, Cynthia Dwork and Moni Nar publish Pricing via Processing, or combating junk mail. This is considered the first use of proof of work, POW. 1993. Haber, Bayer, and Stornetta upgraded the tamper-proofing of document timestamps system with Merkle trees. 1995. David Chaum's DigiCash system, an anonymous electronic cash system, started to be used in some banks. 1998. BitGold, a mechanism for decentralized digital currency, invented by Nick Szabo. It used hash chaining and Byzantine quorums. 1999. Emergence of a file-sharing application mainly used for music sharing, Napster, which is a P2P network, but was centralized with the use of indexing servers. 1999. Development of a secure timestamping service for the Belgian project, Timesec. 2000. Gintella file-sharing network, which introduced decentralization. 2001. Emergence of BitTorrent and distributed hash tables, DHTs. 2002. Hashcash by Adam Back. 2004. Development of B-Money by Wei Day using Hashcash. 2004. Hal Finney, the invention of the reusable POW system. 2005. Prevention of Sybil attacks by using computation puzzles due to James Aspness et al. 2009. Bitcoin, first blockchain. The aforementioned technologies contributed in some way to the development of Bitcoin, even if not directly. The work is relevant to the problem that Bitcoin solved. All previous attempts to create anonymous and decentralized digital currency were successful to some extent, but they could not solve the problem of preventing double spending in a completely trustless or permissionless environment. This problem was finally addressed by the Bitcoin blockchain, which introduced the Bitcoin cryptocurrency. It should be noted that other concepts such as state-machine replication, the SMR problem, introduced in 1978 by Leslie Lamport and formalized in 1980 by Fred Schneider, are also solvable by Bitcoin. Bitcoin solved the SMR problem probabilistically by allowing the replication of blocks and ensuring consistency via its POW consensus mechanism. The SMR, or state machine replication problem, is a technique used to provide fault-tolerant replication in distributed systems. We will explore this in greater detail in Chapter 5, Consensus Algorithms. Now we will discuss some of the major milestones in the history of blockchain in more detail. Electronic cash. The concept of electronic cash, eCash, or digital currency is not new. Since the 1980s, eCash protocols have existed that are based on a model proposed by David Chaum. Just as understanding the concept of distributed systems is necessary to comprehend blockchain technology, the idea of eCash is also essential in order to appreciate the first and astonishingly successful application of blockchain, Bitcoin, and more broadly, cryptocurrencies in general.
Two fundamental eCash system issues need to be addressed: accountability and anonymity. Accountability is required to ensure that cash is spendable only once,
addressing the double spending problem, and that it can only be spent by its rightful owner. The double spending problem arises when the same money can be spent twice, as it is quite easy to make copies of digital data. This becomes a big issue in digital currencies as you can make many copies of the same amount of digital cash. Anonymity is required to protect users' privacy. With physical cash, it is almost impossible to trace back spending to the individual who actually paid the money, which provides adequate privacy should the consumer choose to hide their identity.
In the digital world, however, providing such a level of privacy
is often difficult due to inherent personalization, tracing, and logging mechanisms in digital payment systems such as
credit card payments.
This is indeed a required feature for ensuring the security and safety of the financial network, but it is also often seen as a breach of privacy.
This is due to the fact that end users do not have any control over who their data might be shared with, even without their consent.
Nevertheless, this is a solvable problem, and cryptography is used to address such issues. Especially in blockchain networks, the privacy and anonymity of the participants on the blockchain are sought-after features. We will learn more about this in Chapter 4, Public Key Cryptography. David Chaum solved both of these problems during his work in the 1980s by using two cryptographic operations, namely blind signatures and secret sharing. These terminologies and related concepts will be discussed in detail in Chapter 4, Public Key Cryptography. For the moment, it is sufficient to say that blind signatures allow for signing a document without actually seeing it, and secret sharing is a concept that enables the detection of double spending, that is, using the same eCash token twice. In 2009, the first practical implementation of an eCash system named Bitcoin appeared.
The term cryptocurrency emerged later. For the very first time, it solved the problem of distributed consensus in a trustless network.
It used public key cryptography with a POW mechanism to provide a secure and decentralized method of minting digital currency. The key innovation was the idea of an ordered list of blocks composed of transactions which is cryptographically secured by the POW mechanism to prevent double spending in a trustless environment. This concept will be explained in greater detail in Chapter 6, Introducing Bitcoin. Other technologies used in Bitcoin but which existed before its invention include Merkle trees, hash functions, and hash chains.
All these concepts are explained in appropriate depth in Chapter 4, Public Key Cryptography.
Looking at all the technologies mentioned previously and their relevant history, it is easy to see how concepts from eCash schemes and distributed systems were combined to create Bitcoin and what now is known as blockchain. This concept can also be visualized with the help of the following diagram. Within the emergence of eCash covered along with the ideas that led to the formation of Bitcoin and blockchain, we can now begin to discuss blockchain itself. Blockchain. In 2008, a groundbreaking paper entitled Bitcoin, a peer-to-peer electronic cash system, was written on the topic of peer-to-peer eCash under the pseudonym of Satoshi Nakamoto. This paper is available at bitcoin.org/bitcoin.pdf. It introduced the term chain of blocks. No one knows the actual identity of Satoshi Nakamoto. After introducing Bitcoin in 2009, he remained active in the Bitcoin developer community until 2011. He then handed over Bitcoin development to its core developers and simply disappeared. Since then, there has been no communication from him whatsoever, and his existence and identity are shrouded in mystery. The term chain of blocks evolved over the years into the word blockchain. As stated previously,
blockchain technology incorporates a multitude of applications that can be implemented in various economic sectors.
Particularly in the finance sector, a significant improvement in the performance of financial transactions and settlements manifests as highly desirable time and cost reductions. Additional light will be shed on these aspects of blockchain in Chapter 19, Blockchain Outside of Currencies, where practical use cases will be discussed in detail for various industries. For now, it is sufficient to say that parts of nearly all economic sectors have already realized the potential and promise of blockchain and have embarked, or will do so soon, on the journey to capitalize on the benefits of blockchain technology. Blockchain defined. A good place to start learning what blockchain is would be to see its definition. There are some different ways that blockchain may be defined. Following are two of the most widely accepted definitions. Layman's definition. Blockchain is an ever-growing secure shared record-keeping system in which each user of the data holds a copy of the records, which can only be updated if all parties involved in a transaction agree to update. Technical definition. Blockchain is a peer-to-peer distributed ledger that is cryptographically secure, append-only, immutable, extremely hard to change, and updatable only via consensus or agreement among peers. Now let's examine things in some more detail. We will look at the keywords from the technical definition one by one. Peer-to-peer. The first keyword in the technical definition is peer-to-peer, or P2P. This means that there is no central controller in the network, and all participants, nodes, talk to each other directly. This property allows for transactions to be conducted directly among the peers without third-party involvement such as by a bank. Distributed ledger. Dissecting the technical definition further reveals that blockchain is a distributed ledger, which means that a ledger is spread across the network among all peers in a network, and each peer holds a copy of the complete ledger. Cryptographically secure. Next, we will see that this ledger is cryptographically secure, which means that cryptography has been used to provide security services that makes this ledger secure against tampering and misuse. These services include non-repudiation, data integrity, and data origin authentication. You will see how this is achieved later in Chapter 4, Public Key Cryptography, which introduces the fascinating world of cryptography. Append-only. Another property that we encounter is that blockchain is append-only, which means that data can only be added to the blockchain in time-sequential order. This property implies that once data is added to the blockchain, it is almost impossible to change that data, and it can be considered practically immutable. In other words, blocks added to the blockchain cannot be changed, which allows blockchain to become immutable and tamper-proof ledger of transactions. However, remember that it can be changed in rare scenarios wherein collusion against the blockchain network by bad actors succeeds in gaining more than 51% of the power. Otherwise, the blockchain is practically immutable. There may be some legitimate reasons to change data in the blockchain once it has been added, such as the right to be forgotten or right to erasure, also defined in the GDPR ruling, gdpr-info.eu/art-17-GDPR/. However, those are individual cases that need to be handled separately and that require an elegant technical solution. For all practical purposes, blockchain is indeed immutable and cannot be changed. Updatable via consensus. The most critical attribute of a blockchain is that it is updatable only via consensus. This is what gives it the power of decentralization.
In this scenario,
no central authority is in control of updating the ledger.
Instead, any update made to the blockchain is validated against strict criteria defined by the blockchain protocol and added to the blockchain only after consensus has been reached among all participating peers, nodes on the network.
To achieve consensus, there are various consensus facilitation algorithms that ensure all parties agree on the final state of the data on the blockchain network and resolutely agree upon it to be true. Consensus algorithms are introduced later in this chapter, and then in more detail in Chapter 5, Consensus Algorithms. Blockchain Architecture. Having detailed the primary features of blockchain, we are now in a position to begin to look at its actual architecture. We'll begin by looking at how blockchain acts as a layer within a distributed peer-to-peer network. Blockchain by layers. Blockchain can be thought of as a layer of distributed peer-to-peer network running on top of the internet, as can be seen in the following diagram. It is analogous to SMTP, HTTP, or FTP running on top of TCP/IP. Now we'll discuss all these elements one by one. In the preceding diagram, the lowest layer is the network, which is usually the internet and provides a base communication layer for any blockchain. A peer-to-peer network runs on top of the network layer, which consists of information propagation protocols such as gossip or flooding protocols. After this comes the cryptography layer, which contains crucial cryptographic protocols
that ensure the security of the blockchain.
These cryptographic protocols play a vital role in the integrity of blockchain processes, secure information dissemination, and blockchain consensus mechanisms. This layer consists of public key cryptography and relevant components such as digital signatures and cryptographic hash functions. Sometimes this layer is abstract away, but it has been included in the diagram because it plays a fundamental role in blockchain operations. Next comes the consensus layer, which is concerned with the usage of various consensus mechanisms to ensure agreement among different participants of the blockchain. This is another crucial part of the blockchain architecture,
which consists of various techniques such as SMR, proof-based consensus mechanisms, or traditional distributed systems research, Byzantine fault-tolerant consensus protocols. Further to this, we have the execution layer,
which can consist of virtual machines, blocks, transaction, and smart contracts. This layer, as the name suggests, provides execution services on the blockchain and performs operations such as
value transfer, smart contract execution, and block generation. Virtual machines such as Ethereum Virtual Machine
EVM
provide an execution environment for smart contracts to execute.
Finally, we have the applications layer, which is composed of smart contracts, decentralized applications, DAOs, and autonomous agents. This layer can effectively contain all sorts of various user-level agents and programs that operate on the blockchain. Users interact with the blockchain via decentralized applications. We will discuss more about decentralized applications in Chapter 2, Decentralization. All these concepts will be discussed in detail later in this book in various chapters. Next, we'll look at blockchain from more of a business-oriented perspective. Blockchain and business. From a business standpoint, a blockchain can be defined as a platform where peers can exchange value, eCash, using transactions without the need for a centrally trusted arbitrator. For example, for cash transfers,
banks act as a trusted third party.
In financial trading, this concept is compelling, and once you absorb it, you'll realize the enormous potential of blockchain technology. This disintermediation allows blockchain to be a decentralized consensus mechanism where no single authority is in charge of the database. Immediately, you'll see a significant benefit of decentralization here, because if no banks or central clearinghouses are required, then it immediately leads to cost savings, faster transaction speeds, and more trust. We've now looked at what blockchain is at a fundamental level. Next, we'll go a little deeper and look at some of the elements that comprise a blockchain. Generic elements of a blockchain. Now let's walk through the generic elements of a blockchain.
You can use this as a handy reference section
if you ever need a reminder
about the different parts of a blockchain. More precise elements will be discussed
in the context of their respective
blockchains in later chapters.
For example, the Ethereum blockchain, the structure of a generic blockchain can be visualized with the help of the following diagram. Elements of a generic blockchain are described here one by one. These are the elements that you will come across in relation to blockchain. Address. Addresses are unique identifiers used in a blockchain transaction to denote senders and recipients. An address is usually a public key or derived from a public key. Transaction. A transaction is the fundamental unit of a blockchain. A transaction represents a transfer of value from one address to another. Block. A block is composed of multiple transactions and other elements, such as the previous block hash, hash pointer, timestamp, and nonce. A block is composed of a block header and a selection of transactions bundled together and organized logically. A block contains several elements, which we introduce as follows. A reference to a previous block is also included in the block unless it is a genesis block. This reference is the hash of the header of the previous block. A genesis block is the first block in the blockchain that is hard-coded at the time the blockchain was first started. The structure of a block is also dependent on the type and design of a blockchain. A nonce is a number that is generated and used only once. A nonce is used extensively in many cryptographic operations to provide replay protection, authentication, and encryption. In blockchain, it's used in POW consensus algorithms and for transaction replay protection. A block also includes the nonce value. A timestamp is the creation time of the block.
Merkle root is a hash of all of the nodes of a Merkle tree.
In a blockchain block, it is the combined hash of the transactions in the block. Merkle trees are widely used to validate large data structures securely and efficiently. In the blockchain world, Merkle trees are commonly used to allow efficient verification of transactions. Merkle root in a blockchain is present in the block header section of a block, which is the hash of all transactions in a block. This means that verifying only the Merkle root is required to verify all transactions present in the Merkle tree instead of verifying all transactions one by one. We will elaborate further on these concepts in Chapter 4, Public Key Cryptography. In addition to the block header, the block contains transactions that make up the block body. A transaction is a record of an event, for example, the event of transferring cash from a sender's account to a beneficiary's account. A block contains transactions, and its size varies depending on the type and design of the blockchain. The following structure is a simple block diagram that depicts a block. Specific block structures relative to their blockchain technologies will be discussed later in the book with greater in-depth technical detail. Generally, however, there are just a few attributes that are essential to the functionality of a block. The block header, which is composed of the hash of the previous block's header, the timestamp, nonce, Merkle root, and the block body that contains the transactions. There are also other attributes in a block, but generally the components introduced in this section are usually available in a block. Peer-to-peer network. As the name implies, a peer-to-peer network is a network topology wherein all peers can
communicate with each other
and send and receive messages. The scripting or programming language. Scripts or programs perform various operations on a transaction in order to facilitate various functions. For example, in Bitcoin, transaction scripts are predefined in a language called script, which consists of sets of commands that allow nodes to transfer Bitcoins from one address to another. Script is a limited language in the sense that it only allows essential operations that are not necessary for executing transactions.
but it does not allow for arbitrary program development.
Think of the scripting language as a calculator that only supports standard pre-programmed arithmetic operations. As such, the Bitcoin script language cannot be called Turing-complete. In simple words, a Turing-complete language means that it can perform any computation. It is named after Alan Turing, who developed the idea of a Turing machine that can run any algorithm however complex. Turing-complete languages need loops and branching capability to perform complex computations. Therefore, Bitcoin's scripting language is not Turing-complete, whereas Ethereum's Solidity language is. To facilitate arbitrary program development on a blockchain, a Turing-complete programming language is needed, and it is now a very desirable feature to have for blockchains. Think of this as a computer that allows the development of any program using programming languages.
Nevertheless,
the security of such languages is a crucial question and an essential and ongoing research area. We will discuss this in greater detail in Chapter 6, Introducing Bitcoin, Chapter 10, Smart Contracts, and the chapters on Ethereum development later in this book. Virtual machine. This is an extension of the transaction script introduced previously. A virtual machine allows Turing-complete code to be run on a blockchain as smart contracts, whereas a transaction script is limited in its operation. However, virtual machines are not available on all blockchains.
Various blockchains use virtual machines to run programs such as Ethereum Virtual Machine
(EVM) and Chain Virtual Machine (CVM). CVM is used in the Ethereum blockchain, while CVM is a virtual machine developed for and used in an enterprise-grade blockchain called ChainCore. State machine. A blockchain can be viewed as a state transition mechanism whereby a state is modified from its initial form to the next one by nodes on the blockchain network as a result of transaction execution. Smart contracts. These programs run on top of the blockchain and encapsulate the business logic
to be executed when certain conditions are met.
These programs are enforceable and automatically executable. The smart contract feature is not available on all blockchain platforms, but it is now becoming a very desirable feature due to the flexibility and power that it provides to blockchain applications. Smart contracts have many use cases, including but not limited to identity management, capital markets, trade finance, record management, insurance, and e-governance. Smart contracts will be discussed in more detail in Chapter 10, Smart Contracts. Node. A node in the blockchain network performs various functions depending on the role that it takes on. A node can propose and validate transactions and perform mining to facilitate consensus and secure the blockchain. This goal is achieved by following a consensus protocol, most commonly POW. Nodes can also perform other functions such as simple payment verification, lightweight nodes, validation, and many other functions depending on the type of the blockchain used and the role assigned to the node. Nodes also perform a transaction signing function. Transactions are first created by nodes and then also digitally signed by nodes using private keys as proof that they are the legitimate owner of the asset that they wish to transfer to someone else on the blockchain network. This asset is usually a token or virtual currency such as Bitcoin, but it can also be any real-world asset represented on the blockchain by using tokens. There are also now standards related to tokens. For example, on Ethereum there are ERC20, ERC721, and a few others that define the interfaces and semantics of tokenization. We will cover these in Chapter 12, Further Ethereum. A high-level diagram of blockchain architecture highlighting the key elements mentioned previously is shown as follows. The preceding diagram shows a 4-node blockchain network, top, each maintaining a chain of blocks, virtual machine, state machine, and address. The blockchain is then further magnified, middle, to show the structure of the chain of blocks, which is again magnified, bottom, to show the structure of a transaction. Note that this is a generic structure of a blockchain. We will see specific blockchain structures in detail in the context of Ethereum and Bitcoin blockchains later in this book. How blockchain works. We have now defined and described blockchain. Now let's see how a blockchain actually works. Nodes are either miners who create new blocks and mint cryptocurrency, coins, or block signers who validate and digitally sign the transactions. A critical decision that every blockchain network has to make is to figure out which node will append the next block to the blockchain. This decision is made using a consensus mechanism. The consensus mechanism will be described later in this chapter. For now, we will look at how a blockchain validates transactions and creates and adds blocks to grow the blockchain. We will look at a general scheme for creating blocks. This scheme is presented here to give you a general idea of how blocks are generated and what the relationship is between transactions and blocks. 1. Transaction is initiated. A node starts a transaction by first creating it and then digitally signing it with its private key. A transaction can represent various actions in a blockchain. Most commonly, this is a data structure that represents the transfer of value between users on the blockchain network. The transaction data structure usually consists of some logic of transfer of value, relevant rules, source and destination addresses, and other validation information. Transactions are usually either a cryptocurrency transfer of value, or smart contract invocation that can perform any desired operation. A transaction occurs between two or more parties. This will be covered in more detail in specific chapters on Bitcoin and Ethereum later in the book. 2. Transaction is validated and broadcast. A transaction is propagated, broadcast, usually by using data dissemination protocols, such as Gossip Protocol, to other peers that validate the transaction based on preset validity criteria. Before a transaction is propagated, it is also verified to ensure that it is valid. 3. Find new block. When the transaction is received and validated by special participants called miners on the blockchain network, it is included in a block, and the process of mining starts. This process is also sometimes referred to as finding a new block. Here, nodes called miners race to finalize the block they've created by a process known as mining. 4. New block found. Once a miner solves a mathematical puzzle or fulfills the requirements of the consensus mechanism implemented in a blockchain, the block is considered found and finalized. At this point, the transaction is considered confirmed. Usually in cryptocurrency blockchains such as Bitcoin, the miner who solves the mathematical puzzle is also rewarded with a certain number of coins as an incentive for their effort and the resources they spent in the mining process. 5. Add new block to the blockchain. The newly created block is validated. Transactions or smart contracts within it are executed, and it is propagated to other peers. Peers also validate and execute the block. It now becomes part of the blockchain ledger, and the next block links itself cryptographically back to this block. This link is called a hash pointer. This process can be visualized in the diagram as follows. This completes the basic introduction to blockchain. In the next section, you will learn about the benefits and limitations of this technology. Benefits, features, and limitations of blockchain. Numerous advantages of blockchain technology have been discussed in many industries and proposed by thought leaders around the world who are participating in the blockchain space. The notable benefits of blockchain technology are as follows. 1. Decentralization. This is a core concept and benefit of blockchain. There is no need for a trusted third party or intermediary to validate transactions. Instead, a consensus mechanism is used to agree on the validity of transactions. 2. Transparency and trust. As blockchains are shared and everyone can see what is on the blockchain, this allows the system to be transparent. As a result, trust is established. This is more relevant in scenarios such as the disbursement of funds or benefits where personal discretion in relation to selecting beneficiaries needs to be restricted. 3. Immutability. Once the data has been written to the blockchain, it is extremely difficult to change it back. It is not genuinely immutable, but because changing data is so challenging and nearly impossible, this is seen as a benefit to maintaining an immutable ledger of transactions. 4. High availability. As the system is based on thousands of nodes in a peer-to-peer network and the data is replicated and updated on every node, the system becomes highly available. Even if some nodes leave the network or become inaccessible, the network as a whole continues to work, thus making it highly available. This redundancy results in high availability. 5. Highly secure. All transactions on a blockchain are cryptographically secured and thus provide network integrity. Any transactions posted from the nodes on the blockchain are verified based on a predetermined set of rules. Only valid transactions are selected for inclusion in a block. The blockchain is based on proven cryptographic technology that ensures the integrity and availability of data. Generally, confidentiality is not provided due to the requirements of transparency. This limitation is the leading barrier to its adoption by financial institutions and other industries that require the privacy and confidentiality of transactions. As such, the privacy and confidentiality of transactions on the blockchain are being researched very actively, and advancements are already being made. It could be argued that in many situations, confidentiality is not needed and transparency is preferred. For example, with Bitcoin, confidentiality is not an absolute requirement. However, it is desirable in some scenarios. A more recent example is Zcash. https://z.cash, which provides a platform for conducting anonymous transactions. Other security services such as non-repudiation and authentication are also provided by blockchain, as all actions are secured using private keys and digital signatures. 6. Simplification of current paradigms. The current blockchain model in many industries such as finance or health is somewhat disorganized. In this model, multiple entities maintain their own databases and data sharing can become very difficult due to the disparate nature of the systems. However, as a blockchain can serve as a single shared ledger among many interested parties, this can result in simplifying the model by reducing the complexity of managing the separate systems maintained by each entity. 7. Faster dealings. In the financial industry, especially in post-trade settlement functions, blockchain can play a vital role by enabling the quick settlement of trades. Blockchain does not require a lengthy process of verification, reconciliation, and clearance because a single version of agreed-upon data is already available on a shared ledger between financial organizations. 8. Cost saving. As no trusted third party or clearinghouse is required in the blockchain model, this can massively eliminate overhead costs in the form of the fees, which are paid to such parties. 9. Platform for smart contracts. A blockchain is a platform on which programs can run that execute business logic on behalf of the users. This is a very useful feature, but not all blockchains have a mechanism to execute smart contracts. However, this is a very desirable feature. It is available on newer blockchain platforms such as Ethereum and multi-chain, but not on Bitcoin. Smart contracts. Blockchain technology provides a platform for running smart contracts. These are automated autonomous programs that reside on the blockchain network and encapsulate the business logic and code needed to execute a required function when certain conditions are met. For example, think about an insurance contract where a claim is paid to the traveler if the flight is cancelled. In the real world, this process normally takes a significant amount of time to make the claim, verify it, and pay the insurance amount to the claimant, traveler. What if this whole process were automated with cryptographically enforced trust, transparency, and execution so that as soon as the smart contract received the feed that the flight in question has been cancelled, it automatically triggers the insurance payment to the claimant? If the flight is on time, the smart contract pays itself. This is indeed a revolutionary feature of blockchain, as it provides flexibility, speed, security, and automation for real-world scenarios that can lead to a completely trustworthy system with significant cost reductions. Smart contracts can be programmed to perform any actions that blockchain users need and according to their specific business requirements. 10. Smart property. It is possible to link a digital or physical asset to the blockchain in such a secure and precise manner that it cannot be claimed by anyone else. You are in full control of your asset and it cannot be double spent or double owned. Compare this with a digital music file, for example, which can be copied many times without any controls. While it is true that many digital rights management (DRM) schemes are being used currently along with copyright laws, none of them are enforceable in the way a blockchain-based DRM can be. Blockchain can provide digital rights management functionality in such a way that it can be enforced fully.
There are famously broken DRM schemes that look great in theory but were hacked due to one limitation or another.
One example is the Oculus hack. www.wire.co.uk/article/Oculus Rift-DRM-hacked. Another example is the PS3 hack. Also copyrighted digital music, films, and ebooks are routinely shared on the internet without any limitations. We have had copyright protection in place for many years. But digital piracy refutes all attempts to fully enforce the law. On a blockchain, however, if you own an asset, no one else can claim it unless you decide to transfer it. This feature has far-reaching implications, especially in DRM and eCash systems,
where double spend detection is a crucial requirement.
The double spend problem was first solved without the requirement of a trusted third party in Bitcoin. As with any technology, some challenges need to be addressed in order to make a system more robust, useful, and accessible. Blockchain technology is no exception. In fact, much effort is being made in both academia and industry to overcome the challenges posed by blockchain technology. The most sensitive blockchain problems are as follows. Scalability. Currently, blockchain networks are not as scalable as, for example, current financial networks. This is a known area of concern and a very ripe area for research. Adoption. Often, blockchain is seen as a nascent technology, even though this perspective is rapidly changing.
There is still a long way to go before the mass adoption of this technology.
The challenge here is to allow blockchain networks to be easier to use so that adoption can increase. In addition, several other challenges such as scalability introduced previously exist, which must be solved in order to increase adoption. Regulation. Due to its decentralized nature, regulation is almost impossible on blockchain. This is sometimes seen as a barrier toward adoption because traditionally, due to the existence of regulatory authorities, consumers have a certain level of confidence that if something goes wrong, they can hold someone accountable. However, in blockchain networks, no such regulatory authority
and control exist, which is an inhibiting factor
for many consumers. Relative immature technology. As compared to traditional IT systems that have benefited from decades of research, blockchain is still a new technology that requires a lot of research to achieve maturity. Privacy and confidentiality. Privacy is a concern on public blockchains such as Bitcoin, where everyone can see every single transaction. This transparency is not desirable in many industries such as the financial, law, or medical sectors. This is also a known concern, and a lot of valuable research, with some impeccable solutions, has already been developed. However, further research is still required to drive the mass adoption of blockchain. All of these issues and possible solutions will be discussed in detail in Chapter 21, Scalability and Other Challenges. You now know the basics of blockchain and its benefits and limitations. Now let's take a look at the various types of blockchain that exist. Types of blockchain. Based on the way that blockchain has evolved over the last few years, it can be divided into multiple categories with distinct, though sometimes partially overlapping attributes. You should note that the tiers described earlier in the chapter are a different concept, whereby the logical categorization of blockchain based upon its evolution and usage is presented. In this section, we will examine the different types of blockchains from a technical and business use perspective. These blockchain types can occur on any blockchain tier, as there is no direct relationship between those tiers mentioned earlier and the various types of blockchain. In this section, we'll examine distributed ledgers, distributed ledger technology, DLT, blockchains, ledgers. Distributed ledgers. First, I need to clarify an ambiguity. It should be noted that a distributed ledger is a broad term describing shared databases. Hence, all blockchains technically fall under the umbrella of shared databases or distributed ledgers. Although all blockchains are fundamentally distributed ledgers, all distributed ledgers are not necessarily blockchains. A critical difference between a distributed ledger and a blockchain is that a distributed ledger does not necessarily consist of blocks of transactions to keep the ledger growing. Rather, a blockchain is a special type of shared database that is comprised of blocks of transactions. An example of a distributed ledger that does not use blocks of transactions is R3's Corda, www.corda.net. Corda is a distributed ledger that is developed to record and manage agreements and is especially focused on the financial services industry. On the other hand, more widely known blockchains like Bitcoin and Ethereum make use of blocks to update the shared database. As the name suggests, a distributed ledger is distributed among its participants and spread across multiple sites or organizations. This type of ledger can be either private or public. The fundamental idea here is that, unlike many other blockchains, the records are stored continuously instead of being sorted into blocks. This concept is used in Ripple, which is a blockchain and cryptocurrency-based global payment network. Distributed ledger technology. It should be noted that over the last few years, the terms distributed ledger or DLT have grown to be commonly used to describe blockchain in the finance industry. Sometimes blockchain and DLT are used interchangeably, though this is not entirely accurate. It is how the term has evolved recently. especially in the finance sector. In fact, DLT is now a very active and thriving area of research in the financial sector. From a financial sector point of view, DLTs are permissioned blockchains that are used by consortiums. DLTs usually serve as a shared database, with all participants known and verified. They do not have a cryptocurrency and do not require mining to secure the ledger. At a broader level, DLT is an umbrella term that represents distributed ledger technology as a whole, comprising of blockchains and distributed ledgers of different types. Public blockchains. As the name suggests, public blockchains are not owned by anyone.
They are open to the public, and anyone can participate as a node in the decision-making process.
Users may or may not be rewarded for their participation. All users of these permissionless or unpermissioned ledgers maintain a copy of the ledger on their local nodes and use a distributed consensus mechanism to decide the eventual state of the ledger. Bitcoin and Ethereum are considered public blockchains. Private blockchains. As the name implies, private blockchains are just that, private. That is, they are open only to a consortium or group of individuals or organizations who have decided to share the ledger among themselves. There are various blockchains now available in this category, such as Cadena and Quorum. Optionally, both of these blockchains can also run in public mode if required, but their primary purpose is to provide a private blockchain.
Semi-private blockchains.
With semi-private blockchains, part of the blockchain is private and part of it is public. Note that this is still just a concept today, and no real-world proofs of concept have yet been developed. With a semi-private blockchain, the private part is controlled by a group of individuals, while the public part is open for participation by anyone. This hybrid model can be used in scenarios where the private part of the blockchain remains internal and shared among known participants, while the public part of the blockchain can still be used by anyone, optionally allowing mining to secure the blockchain. This way, the blockchain as a whole can be secured using POW, thus providing consistency and validity for both the private and public parts. This type of blockchain can also be called a semi-decentralized model, where it is controlled by a single entity, but still allows for multiple users to join the network by following appropriate procedures. Sidechains, more precisely known as pegged sidechains. This is a concept whereby coins can be moved from one blockchain to another and then back again. Typical uses include the creation of new altcoins, alternative cryptocurrencies, whereby coins are burnt as a proof of an adequate stake. Burnt or burning the coins in this context means that the coins are sent to an address that is unspendable, and this process makes the burnt coins irrecoverable. This mechanism is used to bootstrap a new currency or introduce scarcity, which results in the increased value of the coin. This mechanism is also called proof of burn, and is used as an alternative method for distributed consensus to POW and proof of stake POS. The example provided previously for burning coins applies to a one-way pegged sidechain. The second type is called a two-way pegged sidechain, which allows the movement of coins from the main chain to the sidechain and back to the main chain when required. This process enables the building of smart contracts for the Bitcoin network. Rootstock is one of the leading examples of a sidechain, which enables smart contract development for Bitcoin using this paradigm. It works by allowing a two-way peg for the Bitcoin blockchain, and this results in much faster throughput. Permissioned ledger. A permissioned ledger is a blockchain where participants of the network are already known and trusted. Permissioned ledgers do not need to use a distributed consensus mechanism. Instead, an agreement protocol is used to maintain a shared version of the truth about the state of the records on the blockchain. In this case, for verification of transactions on the chain, all verifiers are already pre-selected by a central authority, and typically there is no need for a mining mechanism. By definition, there is also no requirement for a permissioned blockchain to be private, as it can be a public blockchain but with regulated access control. For example, Bitcoin can become a permissioned ledger if an access control layer is introduced on top of it that verifies the identity of a user and then allows access to the blockchain. Shared ledger. This is a generic term that is used to describe any application or database that is shared by the public or a consortium. Generally, all blockchains fall into the category of a shared ledger. Fully private and proprietary blockchains. There is no mainstream application of these types of blockchains, as they derive from the core concept of decentralization in blockchain technology. Nonetheless, in specific private settings within an organization, there could be a need to share data and provide some level of guarantee of the authenticity of the data. An example of this type of blockchain might be to allow for collaboration and the sharing of data between various government departments. In that case, no complex consensus mechanism is required, apart from simple SMR and an agreement protocol with known central validators.
Even in private blockchains, tokens are not really required,
but they can be used as a means of transferring value or representing some real-world assets. Tokenized blockchains. These blockchains are standard blockchains that generate cryptocurrency as a result of consensus process via mining or initial distribution. Bitcoin and Ethereum are prime examples of this type of blockchain. Tokenless blockchains. These blockchains are designed in such a way that they do not have the basic unit for the transfer of value. However, they are still valuable in situations where there is no need to transfer value between nodes and only the sharing of data among various trusted parties is required. This is similar to fully private blockchains, the only difference being that the use of tokens is not required. This can also be thought of as a shared distributed ledger used for storing and sharing data between the participants. It does have its benefits when it comes to immutability, tamper-proofing, security, and consensus-driven updates, but is not used for a common blockchain application of value transfer or cryptocurrency. Most of the permission blockchains can be seen as an example of tokenless blockchains. For example, Hyperledger Fabric or Quorum. Tokens can be built on these chains as an application, but intrinsically these blockchains do not have a token associated with them. All the aforementioned terminologies are used in literature, but fundamentally all these blockchains are distributed ledgers and fall under the top-level category of DLTs. We can view these different types in the simple chart as follows. This ends our examination of the various types of blockchain. We'll now move on to the next section to discuss the concept of consensus. Consensus. Consensus is the backbone of a blockchain, as it provides the decentralization of control through an optional process known as mining. The choice of the consensus algorithm to utilize is governed by the type of blockchain in use. That is, not all consensus mechanisms are suitable for all types of blockchains. For example, in public permissionless blockchains, it would make sense to use POW instead of mechanisms that are more suitable for permissioned blockchains, such as proof of authority, POA, or traditional Byzantine fault-tolerant consensus mechanisms. Therefore, it is essential to choose an appropriate consensus algorithm for a particular blockchain project. Consensus is a process of achieving agreement between distrusting nodes on the final state of data. To achieve consensus, different algorithms are used. It is easy to reach an agreement between two nodes, in client-server systems for example. But when multiple nodes are participating in a distributed system and they need to agree on a single value, it becomes quite a challenge to achieve consensus. This process of attaining agreement on a common state or value among multiple nodes, despite the failure of some nodes, is known as distributed consensus. Consensus mechanism. A consensus mechanism is a set of steps that are taken by most or all nodes in a blockchain to agree on a proposed state or value. For more than 3 decades, this concept has been researched by computer scientists in industry and academia. With the advent of blockchain and Bitcoin, consensus mechanisms have come into the limelight again and gained considerable popularity. There are various requirements for a consensus mechanism. The following describes these requirements. Agreement. All honest nodes decide on the same value. Integrity. This is a requirement that no node can make the decision more than once in a single consensus cycle. Validity. The value agreed upon by all honest nodes must be the same as the initial value proposed by at least one honest node. Fault tolerant. The consensus algorithm should be able to run correctly in the presence of faulty or malicious nodes. Byzantine nodes. Termination. All honest nodes terminate the execution of the consensus process and eventually reach a decision. Having seen these general requirements, we'll now look at the different types of consensus mechanisms. Types of consensus mechanisms. All consensus mechanisms are developed with faults in a distributed system to allow distributed systems to reach a final state of agreement. There are 2 general categories of consensus mechanisms. These categories deal with all types of faults: fail-stop types or arbitrary. These common types of consensus mechanisms are as follows. Proof-based consensus mechanisms. This arrangement requires nodes to complete a leader election lottery, and the node that wins proposes the final value. The algorithm works on the principle of providing proof of some work and the possession of some authority or tokens to win the right of proposing the next block. For example, the POW mechanism used in Bitcoin falls into this category, where a miner who solves the computational puzzle as a proof of computational effort expended wins the right to add the next block to the blockchain. Traditional fault tolerance based. With no compute-intensive operations such as partial hash inversion, as in Bitcoin POW, this type of consensus mechanism relies on a simple scheme of nodes that publish and verify signed messages in a number of phases. Eventually, when a certain number of messages are received over a period of rounds, phases, then an agreement is reached. To achieve fault tolerance, replication is used. This is a standard and widely used method to achieve fault tolerance. In general, there are 2 types of faults that a node can experience. Fail-stop faults. This type of fault occurs when a node merely has crashed. Fail-stop faults are the easier ones to deal with of the 2 fault types. Paxos or the RAF protocol introduced earlier in this chapter are normally used to deal with this type of fault. These faults are simpler to deal with. Byzantine faults. The second type of fault is one where the faulty node exhibits malicious or inconsistent behavior arbitrarily. This type is difficult to handle since it can create confusion due to misleading information. This can be a result of an attack by adversaries, a software bug, or data corruption. SMR protocols such as Practical Byzantine Fault Tolerance, PBFT, was developed to address this second type of faults. Many other implementations of consensus protocols have been proposed in traditional distributed systems. Paxos is the most famous of these protocols. It was introduced by Leslie Lamport in 1989. With Paxos, nodes are assigned various roles such as proposer, acceptor, and learner. Nodes or processes are named replicas, and consensus is achieved in the presence of faulty nodes by an agreement among a majority of nodes. An alternative to Paxos is Raft, which works by assigning any of the 3 states, that is, follower, candidate, or leader, to the nodes. A leader is elected after a candidate node receives enough votes, and all changes then have to go through the leader. The leader commits the proposed changes once replication on the majority of the follower nodes is completed. We will briefly touch on some aspects of consensus in blockchain now, but more detail on the theory of consensus mechanisms from a distributed system point of view, and also from the blockchain perspective, will be presented in Chapter 5, Consensus Algorithms.
Consensus in blockchain. Consensus is a distributed computing concept that has been used in blockchain in order to provide a means of agreeing to a single version of the truth by all peers on the blockchain network.
This concept was previously discussed in the distributed systems section of this chapter. In this section, we will address consensus in the context of blockchain technology.
Some concepts presented following are still relevant to the distributed systems theory, but they are explained from a blockchain perspective.
Roughly, the following describes the two main categories of consensus mechanisms. 1. Proof-based leader election, lottery-based, or the Nakamoto consensus, whereby a leader is elected at random using an algorithm and proposes a final value. This category is also referred to as the fully decentralized or permissionless type of consensus mechanism. This type is well used in the Bitcoin and Ethereum blockchain in the form of a POW mechanism. 2. Byzantine fault tolerance, BFT based, is a more traditional approach based on rounds of votes.
This class of consensus is also known as the consortium or permission type of consensus mechanism.
BFT-based consensus mechanisms perform well when there are a limited number of nodes, but they do not scale well.
On the other hand, leader election lottery-based POW consensus mechanisms scale very well, but perform very slowly. As there is significant research being conducted in this area, new types of consensus mechanisms are also emerging, such as the semi-decentralized type, which is used in the Ripple network. The Ripple network will be discussed in detail in this book's online content pages. Here, static.packs/downloads/altcoins_ethereum_projects_and_more_bonus_content.pdf. There are also various other proposals out there which are trying to find the right balance between scalability and performance. Some notable projects include PBFT, Hybrid BFT, Block DAG, Tezos, Stellar, and Ghost.
The consensus algorithms available today or that are being researched in the context of blockchain are presented as follows. The following is not an exhaustive list, but it includes all notable algorithms. Proof of work, POW. This type of consensus mechanism relies on proof that adequate computational resources have been spent before
proposing a value for acceptance
by the network. This scheme is used in Bitcoin, Litecoin, and other cryptocurrency blockchains. Currently, it is the only algorithm that has proven to be
astonishingly
successful against any collusion attacks on a blockchain network, such as the Sybil attack. The Sybil attack will be discussed in Chapter 6, Introducing Bitcoin. Proof of stake.
This algorithm works on the idea that a node or user has an adequate stake in the system. That is, the user has invested enough in the system so that any malicious attempt by that user would outweigh the benefits of performing such an attack on the network. This idea was first introduced by Peercoin, and it is going to be used in the Ethereum blockchain version called Serenity. Another important concept in POS is coinage, which is a criterion derived from the amount of time and number of coins that have not been spent. In this model, the chances of proposing and signing the next block increase with the coinage. Delegated Proof of Stake, DPoS. This is an innovation over standard POS, whereby each node that has a stake in the system can delegate the validation of a transaction to other nodes by voting. It is used in the BitShares blockchain. Proof of Elapsed Time, POET. Introduced by Intel in 2016, POET uses a Trusted Execution Environment, TEE, to provide randomness and safety in the leader election process via a guaranteed wait time. It requires the Intel SGX Software Guard Extensions processor to provide the security guarantee for it to be secure. This concept is discussed in more detail in Chapter 17, Hyperledger. in the context of the Intel Sawtooth Lake blockchain project. Proof of deposit, POD. In this case, nodes that wish to participate in the network have to make a security deposit before they can mine and propose blocks. This mechanism is used in the Tendermint blockchain. Proof of importance, POI. This idea is significant and different from POS. POI not only relies on how large a stake a user has in the system, but it also monitors the usage and movement of tokens by the user in order to establish a level of trust and importance. It is used in the NEM coin blockchain. More information about this coin is available from NEM's website, nem.io. Federated consensus or Federated Byzantine consensus. This mechanism is used in the Stellar Consensus Protocol. Nodes in this protocol retain a group of publicly trusted peers and propagate only those transactions that have been validated by the majority of trusted nodes. Reputation-based mechanisms. As the name suggests, a leader is elected by the reputation it has built over time on the network. It is based on the votes of other members. Practical Byzantine fault tolerance, PBFT. This mechanism achieves SMR, which provides tolerance against Byzantine nodes. Various other protocols, including PBFT, Paxos, Raft, and Federated Byzantine Agreement, FBA, are also being used or have been proposed for use in many different implementations or distributed systems and blockchains. Proof of activity, POA. This scheme is a combination of POS and POW, which ensures that a stakeholder is elected in a pseudo-random but uniform fashion. This is a comparatively more energy-efficient mechanism as compared to POW. It utilizes a new concept called Follow the Satoshi. In this scheme, POW and POS are combined together to achieve consensus and a good level of security. This scheme is more energy efficient as POW is used only in the first stage of the mechanism. After the first stage, it switches to POS, which consumes negligible energy. We will discuss these ideas further in Chapter 7, Bitcoin Network and Payments, where protocols are reviewed in the context of advanced Bitcoin protocols. Proof of capacity, POC. This scheme uses hard disk space as a resource to mine the blocks. This is different from POW, where CPU resources are used. In POC, hard disk space is utilized for mining and, as such, is also known as hard drive mining. This concept was first introduced in the Burstcoin cryptocurrency. Proof of storage. This scheme allows for the outsourcing of storage capacity. This scheme is based on the concept that a particular piece of data is probably stored by a node, which serves as a means to participate in the consensus mechanism. Several variations of this scheme have been proposed, such as proof of replication, proof of data possession, proof of space, and proof of space-time. Proof of authority, POA. This scheme utilizes the identity of the participants, called validators, as a stake on the network. Validators are known and have the authority to propose new blocks. Validators propose the new blocks and validate them as per blockchain rules. Commonly used POA algorithms are Click and Aura. Some prominent protocols in blockchain will be discussed in detail in Chapter 5, Consensus Algorithms. In this chapter, a light introduction is presented only. Remember, earlier in this chapter we said that distributed systems are difficult to build and a distributed system cannot have consistency, availability, and partition tolerance at the same time. This is a proven result. However, in blockchain it seems that this theorem is somehow violated. In the next section we will introduce the CAP theorem formally and discuss why blockchain appears to achieve all three properties simultaneously. CAP theorem and blockchain. The CAP theorem, also known as Brewer's theorem, was introduced by Eric Brewer in 1998 as a conjecture. In 2002, it was proved as a theorem by Seth Gilbert and Nancy Lynch. The theorem states that any distributed system cannot have consistency, availability, and partition tolerance simultaneously. Consistency is a property that ensures that all nodes in a distributed system have a single, current, and identical copy of the data. Consistency is achieved using consensus algorithms in order to ensure that all nodes have the same copy of the data. This is also called state machine replication. The blockchain is a means for achieving state machine replication. Availability means that the nodes in the system are up, accessible for use, and are accepting incoming requests and responding with data without any failures as and when required. In other words, data is available at each node, and the nodes are responding to requests. Partition tolerance ensures that if a group of nodes is unable to communicate with other nodes due to network failures, the distributed system continues to operate correctly. This can occur due to network and node failures. A Venn diagram is commonly used to visualize the CAP theorem. The preceding diagram shows that only two properties at a time can be achieved, either AP, CA, or CP. In summary, 1. If we opt for CP, consistency and partition tolerance, we sacrifice availability. 2. If we opt for AP, availability and partition tolerance, we sacrifice consistency. 3. If we opt for AC, availability and consistency, we sacrifice partition tolerance. Usually a network partition cannot be ignored. Therefore, the choice mostly becomes either consistency or availability in the case of a network partition. As shown previously, a distributed system cannot have consistency, availability, and partition tolerance simultaneously. This can be explained with the following example. Let's imagine that there is a distributed system with two nodes. Now let's apply the three-theorem properties on the smallest of possible distributed systems only with two nodes. Consistency is achieved if both nodes have the same shared state, that is, they have the same up-to-date copy of the data. Availability is achieved if both nodes are up and running and responding with the latest copy of data. Partition tolerance is achieved if, despite communication failure or delay between nodes, the network distributed system continues to operate. Now think of a scenario where a partition occurs, and nodes can no longer communicate with each other. If new updated data comes in now, it can only be updated on one node only. In that case, if the node accepts the update, then only that one node in the network is updated, and therefore consistency is lost. Now if the update is rejected by the node, that would result in loss of availability. In that case, due to partition tolerance, both availability and consistency are unachievable. This is strange because somehow blockchain manages to achieve all of these properties. Or does it? It seems that the CAP theorem is violated by blockchain, especially in its most successful implementation, Bitcoin. However, this is not the case. In blockchain, consistency is sacrificed in favor of availability and partition tolerance. In this scenario, consistency, C, on the blockchain is not achieved simultaneously with partition tolerance, P, and availability, A, but is achieved over time. This is called eventual consistency, where consistency is achieved as a result of validation from multiple nodes over time. It means that there can only be a temporary disagreement between nodes on the final state, but it is eventually agreed upon. For example, in Bitcoin, multiple transaction confirmations are required to achieve a good level of confidence that transactions may not be rolled back in the future, and eventually a consistent view of transaction history is available to all nodes. Multiple confirmations of a transaction over time provide eventual consistency in Bitcoin. For this purpose, the process of mining was introduced in Bitcoin. Mining is a process that facilitates the achievement of consensus by using the POW algorithm. At a higher level, mining can be defined as a process that is used to add more blocks to the blockchain. We will cover more on this later in Chapter 6, Introducing Bitcoin. Summary. This chapter introduced blockchain technology at an advanced level. Firstly, we discussed blockchain's progress toward becoming a mature technology, followed by some basic concepts about distributed systems, and then the history of blockchain was reviewed. Concepts such as eCash were also discussed. Various definitions of blockchain from different points of view were presented. Some applications of blockchain technology were also introduced. Next, different types of blockchain were explored. Finally, the benefits and limitations of this new technology were also examined. Some topics such as blockchain scalability and adaptability issues were intentionally introduced only lightly, as they will be discussed in depth in later chapters. In the next chapter, we will introduce the concept of decentralization, which is central to the idea behind blockchains and their vast number of applications.
After the Byzantine generals problem. The Byzantine generals problem. In 1982, a thought experiment was proposed by Lamport et al. In their research paper, The Byzantine Generals Problem, which is available here. In this problem, a group of army generals who lead different parts of the Byzantine army is planning to attack or retreat from a city. The only way of communicating among them is via a messenger. They need to agree to strike at the same time in order to win. The issue is that one or more generals might be traitors, who could send a misleading message. Therefore, there is a need for a viable mechanism that allows for agreement among the generals, even in the presence of the treacherous ones, so that the attack can still take place at the same time. As the analogy for distributed systems, the generals can be considered honest nodes, the traitors as Byzantine nodes, that is, nodes with arbitrary behavior.
And the messenger can be thought of as a channel of communication among the generals.
The problem was solved in 1999 by Castro and Liskov, who presented the practical Byzantine fault tolerance (PBFT) algorithm, which solves the consensus problem in the presence of Byzantine faults
in asynchronous networks by utilizing the state machine replication protocol.
PBFT goes through a number of rounds to eventually reach an agreement between nodes on the proposed value. PBFT and other consensus protocols will be discussed in greater detail in Chapter 5, Consensus Algorithms. This type of inconsistent behavior of Byzantine nodes can be intentionally malicious, which is detrimental to the operation of the network. Any expected behavior by a node on the network, whether malicious or not, can be categorized as Byzantine. A small-scale example of a distributed system is shown in the following diagram. This distributed system has 6 nodes, out of which 1 and 4 is a Byzantine node, leading to possible data inconsistency. L2 is a link that is broken or slow, and this can lead to a partition in the network. The primary challenge of a distributed system design is the coordination between nodes and fault tolerance. Even if a certain threshold dictated by the consensus protocol of the nodes become faulty or network links break, the distributed system should be able to tolerate this and continue to work to achieve the desired result. This problem has been an active area of distributed system design research for many years, and several algorithms and mechanisms have been proposed to overcome these issues. Distributed systems are so challenging to design that a theory known as the CAP theorem has been proven, which states that a distributed system cannot have all 3 of the much desired properties simultaneously. That is, consistency, availability, and partition tolerance. We will dive into the CAP theorem in more detail later in this chapter. Even though blockchain can be considered to be both a distributed and decentralized system, there are, however, critical differences between distributed systems and decentralized systems that
make both of these systems
architecturally different. We will discuss these differences in detail in Chapter 2, Decentralization. With a better understanding of distributed systems, let's now move on to talking about blockchain itself. We'll begin with a brief rundown of the history of blockchain and Bitcoin. The history of blockchain and Bitcoin. Blockchain was introduced with the invention of Bitcoin in 2008.
Its practical implementation then occurred in 2009.
For the purposes of this chapter, it is sufficient to review Bitcoin very briefly, as it will be explored in great depth in Chapter 6, Introducing Bitcoin. However, it is essential to refer to Bitcoin because without it, the history of blockchain is not complete. The events that led to blockchain. Now we will look at the early history of computing and computer networks, and we'll discuss how these technologies evolved and contributed to the development of Bitcoin in 2008. We can view this in chronological order. 1960s, invention of computer networks. 1969, development of ARPANET. 1970s, early work on secure network communication including public key cryptography. 1970s, cryptographic hash functions. 1973, extension of ARPANET to other geographic locations. 1974, first Internet service provider, Telenet. 1976, Diffie-Hellman work on securely exchanging cryptographic keys. 1978, invention of public key cryptography. 1979, invention of Merkle trees, hashes in a tree structure by Ralph C. Merkle. 1980s, development of TCP/IP. 1980, protocols for public key cryptosystems, Ralph C. Merkle. 1982, blind signatures proposed by David Chaum. 1982, the Byzantine generals problem. Bitcoin can be considered a solution to the Byzantine generals problem. However, the original intention of the Bitcoin network was to address the previously unsolved double spending problem. 1985, work on elliptic curve cryptography by Neil Koblitz and Victor Miller. 1991, Haber and Stornetta work on tamper-proofing document timestamps. This can be considered the earliest idea of a chain of block or hash chains. 1992, Cynthia Dwork and Moni Nar publish Pricing via Processing or Combating Junk Mail. This is considered the first use of proof of work, POW. 1993, Haber, Bayer, and Stornetta upgraded the tamper-proofing of document timestamps system with Merkle trees. 1995, David Chaum's DigiCash system, an anonymous electronic cash system, started to be used in some banks. 1998, BitGold, a mechanism for decentralized digital currency, invented by Nick Szabo. It used hash chaining and Byzantine quorums. 1999, emergence of a file-sharing application mainly used for music sharing, Napster, which is a P2P network, but was centralized with the use of indexing servers. 1999, development of a secure timestamping service for the Belgian project, Timesec. 2000, Gintella file-sharing network, which introduced decentralization. 2001, emergence of BitTorrent and distributed hash tables, DHTs. 2002, Hashcash by Adam Back. 2004, development of B-Money by Wei Day using Hashcash. 2004, Hal Finney, the invention of the reusable POW system. 2005, prevention of Sybil attacks by using computation puzzles due to James Aspness et al. 2009, Bitcoin, first blockchain. The aforementioned technologies contributed in some way to the development of Bitcoin, even if not directly. The work is relevant to the problem that Bitcoin solved. All previous attempts to create anonymous and decentralized digital currency were successful to some extent, but they could not solve the problem of preventing double spending in a completely trustless or permissionless environment. This problem was finally addressed by the Bitcoin blockchain, which introduced the Bitcoin cryptocurrency. It should be noted that other concepts such as state-machine replication, the SMR problem, introduced in 1978 by Leslie Lamport and formalized in 1980 by Fred Schneider, are also solvable by Bitcoin. Bitcoin solves the SMR problem probabilistically by allowing the replication of blocks and ensuring consistency via its POW consensus mechanism. The SMR or state machine replication problem is a technique used to provide fault-tolerant replication in distributed systems. We will explore this in greater detail in Chapter 5, Consensus Algorithms. Now we will discuss some of the major milestones in the history of blockchain in more detail. Electronic cash. The concept of electronic cash, eCash, or digital currency is not new. Since the 1980s, eCash protocols have existed that are based on a model proposed by David Chaum. Just as understanding the concept of distributed systems is necessary to comprehend blockchain technology, the idea of eCash is also essential in order to appreciate the first and astonishingly successful application of blockchain, Bitcoin, and more broadly, cryptocurrencies in general.
Two fundamental eCash system issues need to be addressed: accountability and anonymity. Accountability is required to ensure that cash is spendable only once,
addressing the double spending problem, and that it can only be spent by its rightful owner. The double spending problem arises when the same money can be spent twice, as it is quite easy to make copies of digital data. This becomes a big issue in digital currencies as you can make many copies of the same amount of digital cash. Anonymity is required to protect users' privacy. With physical cash, it is almost impossible to trace back spending to the individual who actually paid the money, which provides adequate privacy should the consumer choose to hide their identity.
In the digital world, however, providing such a level of privacy
is often difficult due to inherent personalization, tracing, and logging mechanisms in digital payment systems such as
credit card payments.
This is indeed a required feature for ensuring the security and safety of the financial network, but it is also often seen as a breach of privacy.
This is due to the fact that end users do not have any control over who their data might be shared with, even without their consent.
Nevertheless, this is a solvable problem, and cryptography is used to address such issues. Especially in blockchain networks, the privacy and anonymity of the participants on the blockchain are sought-after features. We will learn more about this in Chapter 4, Public Key Cryptography. David Chaum solved both of these problems during his work in the 1980s by using two cryptographic operations, namely blind signatures and secret sharing. These terminologies and related concepts will be discussed in detail in Chapter 4, Public Key Cryptography. For the moment, it is sufficient to say that blind signatures allow for signing a document without actually seeing it, and secret sharing is a concept that enables the detection of double spending, that is, using the same eCash token twice. In 2009, the first practical implementation of an eCash system named Bitcoin appeared.
The term cryptocurrency emerged later. For the very first time, it solved the problem of distributed consensus in a trustless network.
It used public key cryptography with a POW mechanism to provide a secure and decentralized method of minting digital currency. The key innovation was the idea of an ordered list of blocks composed of transactions which is cryptographically secured by the POW mechanism to prevent double spending in a trustless environment. This concept will be explained in greater detail in Chapter 6, Introducing Bitcoin. Other technologies used in Bitcoin but which existed before its invention include Merkle trees, hash functions, and hash chains.
All these concepts are explained in appropriate depth in Chapter 4, Public Key Cryptography.
Looking at all the technologies mentioned previously and their relevant history, it is easy to see how concepts from eCash schemes and distributed systems were combined to create Bitcoin and what now is known as blockchain. This concept can also be visualized with the help of the following diagram. Within the emergence of eCash covered along with the ideas that led to the formation of Bitcoin and blockchain, we can now begin to discuss blockchain itself. Blockchain. In 2008, a groundbreaking paper entitled Bitcoin, a peer-to-peer electronic cash system, was written on the topic of peer-to-peer eCash under the pseudonym of Satoshi Nakamoto. This paper is available at bitcoin.org/bitcoin.pdf. It introduced the term chain of blocks. No one knows the actual identity of Satoshi Nakamoto. After introducing Bitcoin in 2009, he remained active in the Bitcoin developer community until 2011. He then handed over Bitcoin development to its core developers
and simply disappeared.
Since then, there has been no communication from him whatsoever, and his existence and identity are shrouded in mystery. The term chain of blocks evolved over the years into the word blockchain. As stated previously,
blockchain technology incorporates a multitude of applications that can be implemented in various economic sectors.
Particularly in the finance sector, a significant improvement in the performance of financial transactions and settlements manifests as highly desirable time and cost reductions. Additional light will be shed on these aspects of blockchain in Chapter 19, Blockchain Outside of Currencies, where practical use cases will be discussed in detail for various industries. For now, it is sufficient to say that parts of nearly all economic sectors have already realized the potential and promise of blockchain and have embarked, or will do so soon, on the journey to capitalize on the benefits of blockchain technology. Blockchain defined. A good place to start learning what blockchain is would be to see its definition. There are some different ways that blockchain may be defined. Following are two of the most widely accepted definitions. Layman's definition. Blockchain is an ever-growing secure shared record-keeping system in which each user of the data holds a copy of the records, which can only be updated if all parties involved in a transaction agree to update. Technical definition. Blockchain is a peer-to-peer distributed ledger that is cryptographically secure, append-only, immutable, extremely hard to change, and updatable only via consensus or agreement among peers. Now let's examine things in some more detail. We will look at the keywords from the technical definition one by one. Peer-to-peer. The first keyword in the technical definition is peer-to-peer, or P2P. This means that there is no central controller in the network, and all participants, nodes, talk to each other directly. This property allows for transactions to be conducted directly among the peers without third-party involvement, such as by a bank. Distributed ledger. Dissecting the technical definition further reveals that blockchain is a distributed ledger, which means that a ledger is spread across the network among all peers in a network, and each peer holds a copy of the complete ledger. Cryptographically secure. Next, we will see that this ledger is cryptographically secure, which means that cryptography has been used to provide security services that makes this ledger secure against tampering and misuse. These services include non-repudiation, data integrity, and data origin authentication. You will see how this is achieved later in Chapter 4, Public Key Cryptography, which introduces the fascinating world of cryptography. Append-only. Another property that we encounter is that blockchain is append-only, which means that data can only be added to the blockchain in time-sequential order. This property implies that once data is added to the blockchain, it is almost impossible to change that data, and it can be considered practically immutable. In other words, blocks added to the blockchain cannot be changed, which allows blockchain to become immutable and tamper-proof ledger of transactions. However, remember that it can be changed in rare scenarios wherein collusion against the blockchain network by bad actors succeeds in gaining more than 51% of the power. Otherwise, the blockchain is practically immutable. There may be some legitimate reasons to change data in the blockchain once it has been added, such as the right to be forgotten or right to erasure, also defined in the GDPR ruling, gdpr-info.eu/art-17-GDPR/. However, those are individual cases that need to be handled separately and that require an elegant technical solution. For all practical purposes, blockchain is indeed immutable and cannot be changed. Updatable via consensus. The most critical attribute of a blockchain is that it is updatable only via consensus. This is what gives it the power of decentralization.
In this scenario,
no central authority is in control of updating the ledger.
Instead, any update made to the blockchain is validated against strict criteria defined by the blockchain protocol and added to the blockchain only after consensus has been reached among all participating peers, nodes on the network.
To achieve consensus, there are various consensus facilitation algorithms that ensure all parties agree on the final state of the data on the blockchain network and resolutely agree upon it to be true. Consensus algorithms are introduced later in this chapter, and then in more detail in Chapter 5, Consensus Algorithms. Blockchain Architecture. Having detailed the primary features of blockchain, we are now in a position to begin to look at its actual architecture. We'll begin by looking at how blockchain acts as a layer within a distributed peer-to-peer network. Blockchain by layers. Blockchain can be thought of as a layer of distributed peer-to-peer network running on top of the internet, as can be seen in the following diagram. It is analogous to SMTP, HTTP, or FTP running on top of TCP/IP. Now we'll discuss all these elements one by one. In the preceding diagram, the lowest layer is the network, which is usually the internet and provides a base communication layer for any blockchain. A peer-to-peer network runs on top of the network layer. which consists of information propagation protocols such as gossip or flooding protocols. After this comes the cryptography layer, which contains crucial cryptographic protocols
that ensure the security of the blockchain.
These cryptographic protocols play a vital role in the integrity of blockchain processes, secure information dissemination, and blockchain consensus mechanisms. This layer consists of public key cryptography and relevant components such as digital signatures and cryptographic hash functions. Sometimes this layer is abstract away, but it has been included in the diagram because it plays a fundamental role in blockchain operations. Next comes the consensus layer, which is concerned with the usage of various consensus mechanisms to ensure agreement among different participants of the blockchain. This is another crucial part of the blockchain architecture,
which consists of various techniques such as SMR, proof-based consensus mechanisms, or traditional distributed systems research, Byzantine fault-tolerant consensus protocols. Further to this, we have the execution layer,
which can consist of virtual machines, blocks, transaction, and smart contracts. This layer, as the name suggests, provides execution services on the blockchain and performs operations such as
value transfer, smart contract execution, and block generation. Virtual machines such as Ethereum Virtual Machine
(EVM)
provide an execution environment for smart contracts to execute.
Finally, we have the applications layer, which is composed of smart contracts, decentralized applications, DAOs, and autonomous agents. This layer can effectively contain all sorts of various user-level agents and programs that operate on the blockchain. Users interact with the blockchain via decentralized applications. We will discuss more about decentralized applications in Chapter 2, Decentralization. All these concepts will be discussed in detail later in this book in various chapters. Next, we'll look at blockchain from more of a business-oriented perspective. Blockchain and business. From a business standpoint, a blockchain can be defined as a platform where peers can exchange value, eCash, using transactions without the need for a centrally trusted arbitrator. For example, for cash transfers,
banks act as a trusted third party.
In financial trading, this concept is compelling, and once you absorb it, you'll realize the enormous potential of blockchain technology. This disintermediation allows blockchain to be a decentralized consensus mechanism where no single authority is in charge of the database. Immediately, you'll see a significant benefit of decentralization here, because if no banks or central clearinghouses are required, then it immediately leads to cost savings, faster transaction speeds, and more trust. We've now looked at what blockchain is at a fundamental level. Next, we'll go a little deeper and look at some of the elements that comprise a blockchain. Generic elements of a blockchain. Now let's walk through the generic elements of a blockchain.
You can use this as a handy reference section
if you ever need a reminder
about the different parts of a blockchain. More precise elements will be discussed
in the context of their respective
blockchains in later chapters.
For example, the Ethereum blockchain, the structure of a generic blockchain can be visualized with the help of the following diagram. Elements of a generic blockchain are described here one by one. These are the elements that you will come across in relation to blockchain. Address. Addresses are unique identifiers used in a blockchain transaction to denote senders and recipients. An address is usually a public key or derived from a public key. Transaction. A transaction is the fundamental unit of a blockchain. A transaction represents a transfer of value from one address to another. Block. A block is composed of multiple transactions and other elements, such as the previous block hash, hash pointer, timestamp, and nonce. A block is composed of a block header and a selection of transactions bundled together and organized logically. A block contains several elements, which we introduce as follows. A reference to a previous block is also included in the block unless it is a genesis block. This reference is the hash of the header of the previous block. A genesis block is the first block in the blockchain that is hard-coded at the time the blockchain was first started. The structure of a block is also dependent on the type and design of a blockchain. A nonce is a number that is generated and used only once. A nonce is used extensively in many cryptographic operations to provide replay protection, authentication, and encryption. In blockchain, it's used in POW consensus algorithms and for transaction replay protection. A block also includes the nonce value. A timestamp is the creation time of the block.
Merkle root is a hash of all of the nodes of a Merkle tree.
In a blockchain block, it is the combined hash of the transactions in the block. Merkle trees are widely used to validate large data structures securely and efficiently. In the blockchain world, Merkle trees are commonly used to allow efficient verification of transactions. Merkle root in a blockchain is present in the block header section of a block, which is the hash of all transactions in a block. This means that verifying only the Merkle root is required to verify all transactions present in the Merkle tree instead of verifying all transactions one by one. We will elaborate further on these concepts in Chapter 4, Public Key Cryptography. In addition to the block header, the block contains transactions that make up the block body. A transaction is a record of an event, for example, the event of transferring cash from a sender's account to a beneficiary's account. A block contains transactions, and its size varies depending on the type and design of the blockchain. The following structure is a simple block diagram that depicts a block. Specific block structures relative to their blockchain technologies will be discussed later in the book with greater in-depth technical detail. Generally, however, there are just a few attributes that are essential to the functionality of a block. The block header, which is composed of the hash of the previous block's header, the timestamp, nonce, Merkle root, and the block body that contains the transactions. There are also other attributes in a block, but generally the components introduced in this section are usually available in a block. Peer-to-peer network. As the name implies, a peer-to-peer network is a network topology wherein all peers can
Communicate with each other.
and send and receive messages. The scripting or programming language. Scripts or programs perform various operations on a transaction in order to facilitate various functions. For example, in Bitcoin, transaction scripts are predefined in a language called script, which consists of sets of commands that allow nodes to transfer bitcoins from one address to another. Script is a limited language in the sense that it only allows essential operations that are not necessary for executing transactions.
But it does not allow for arbitrary program development.
Think of the scripting language as a calculator that only supports standard pre-programmed arithmetic operations. As such, the Bitcoin script language cannot be called Turing-complete. In simple words, a Turing-complete language means that it can perform any computation. It is named after Alan Turing, who developed the idea of a Turing machine that can run any algorithm however complex. Turing-complete languages need loops and branching capability to perform complex computations. Therefore, Bitcoin scripting language is not Turing-complete, whereas Ethereum's Solidity language is. To facilitate arbitrary program development on a blockchain, a Turing-complete programming language is needed, and it is now a very desirable feature to have for blockchains. Think of this as a computer that allows the development of any program using programming languages.
Nevertheless,
The security of such languages is a crucial question and an essential and ongoing research area. We will discuss this in greater detail in Chapter 6, Introducing Bitcoin, Chapter 10, Smart Contracts, and the chapters on Ethereum development later in this book. Virtual machine. This is an extension of the transaction script introduced previously. A virtual machine allows Turing-complete code to be run on a blockchain as smart contracts, whereas a transaction script is limited in its operation. However, virtual machines are not available on all blockchains.
Various blockchains use virtual machines to run programs such as Ethereum Virtual Machine
(EVM) and Chain Virtual Machine (CVM). CVM is used in the Ethereum blockchain, while CVM is a virtual machine developed for and used in an enterprise-grade blockchain called Chain Core. State machine. A blockchain can be viewed as a state transition mechanism whereby a state is modified from its initial form to the next one by nodes on the blockchain network as a result of transaction execution. Smart contracts. These programs run on top of the blockchain and encapsulate the business logic to be executed when certain conditions are met. These programs are enforceable and automatically executable. The smart contract feature is not available on all blockchain platforms, but it is now becoming a very desirable feature due to the flexibility and power that it provides to blockchain applications. Smart contracts have many use cases, including but not limited to identity management, capital markets, trade finance, record management, insurance, and e-governance. Smart contracts will be discussed in more detail in Chapter 10, Smart Contracts. Node. A node in the blockchain network performs various functions depending on the role that it takes on. A node can propose and validate transactions and perform mining to facilitate consensus and secure the blockchain. This goal is achieved by following a consensus protocol, most commonly POW. Nodes can also perform other functions such as simple payment verification, lightweight nodes, validation, and many other functions depending on the type of the blockchain used and the role assigned to the node. Nodes also perform a transaction signing function. Transactions are first created by nodes and then also digitally signed by nodes using private keys as proof that they are the legitimate owner of the asset that they wish to transfer to someone else on the blockchain network. This asset is usually a token or virtual currency such as Bitcoin, but it can also be any real-world asset represented on the blockchain by using tokens. There are also now standards related to tokens. For example, on Ethereum there are ERC20, ERC721, and a few others that define the interfaces and semantics of tokenization. We will cover these in Chapter 12, Further Ethereum. A high-level diagram of blockchain architecture highlighting the key elements mentioned previously is shown as follows. The preceding diagram shows a 4-node blockchain network, top, each maintaining a chain of blocks, virtual machine, state machine, and address. The blockchain is then further magnified, middle, to show the structure of the chain of blocks, which is again magnified, bottom, to show the structure of a transaction. Note that this is a generic structure of a blockchain. We will see specific blockchain structures in detail in the context of Ethereum and Bitcoin blockchains later in this book. How blockchain works. We have now defined and described blockchain. Now let's see how a blockchain actually works. Nodes are either miners who create new blocks and mint cryptocurrency, coins, or block signers who validate and digitally sign the transactions. A critical decision that every blockchain network has to make is to figure out which node will append the next block to the blockchain. This decision is made using a consensus mechanism. The consensus mechanism will be described later in this chapter. For now, we will look at how a blockchain validates transactions and creates and adds blocks to grow the blockchain. We will look at a general scheme for creating blocks. This scheme is presented here to give you a general idea of how blocks are generated and what the relationship is between transactions and blocks. 1. Transaction is initiated. A node starts a transaction by first creating it and then digitally signing it with its private key. A transaction can represent various actions in a blockchain. Most commonly, this is a data structure that represents the transfer of value between users on the blockchain network. The transaction data structure usually consists of some logic of transfer of value, relevant rules, source and destination addresses, and other validation information. Transactions are usually either a cryptocurrency transfer, transfer of value, or smart contract invocation that can perform any desired operation. A transaction occurs between two or more parties. This will be covered in more detail in specific chapters on Bitcoin and Ethereum later in the book. 2. Transaction is validated and broadcast. A transaction is propagated, broadcast, usually by using data dissemination protocols, such as Gossip Protocol, to other peers that validate the transaction based on preset validity criteria. Before a transaction is propagated, it is also verified to ensure that it is valid. 3. Find new block. When the transaction is received and validated by special participants called miners on the blockchain network, it is included in a block, and the process of mining starts. This process is also sometimes referred to as finding a new block. Here, nodes called miners race to finalize the block they've created by a process known as mining. 4. New block found. Once a miner solves a mathematical puzzle or fulfills the requirements of the consensus mechanism implemented in a blockchain, the block is considered found and finalized. At this point, the transaction is considered confirmed. Usually in cryptocurrency blockchains such as Bitcoin, the miner who solves the mathematical puzzle is also rewarded with a certain number of coins as an incentive for their effort and the resources they spent in the mining process. 5. Add new block to the blockchain. The newly created block is validated. Transactions or smart contracts within it are executed, and it is propagated to other peers. Peers also validate and execute the block. It now becomes part of the blockchain ledger, and the next block links itself cryptographically back to this block. This link is called a hash pointer. This process can be visualized in the diagram as follows. This completes the basic introduction to blockchain. In the next section, you will learn about the benefits and limitations of this technology. Benefits, features, and limitations of blockchain. Numerous advantages of blockchain technology have been discussed in many industries and proposed by thought leaders around the world who are participating in the blockchain space. The notable benefits of blockchain technology are as follows. 1. Decentralization. This is a core concept and benefit of blockchain. There is no need for a trusted third party or intermediary to validate transactions. Instead, a consensus mechanism is used to agree on the validity of transactions. 2. Transparency and trust. As blockchains are shared and everyone can see what is on the blockchain, this allows the system to be transparent. As a result, trust is established. This is more relevant in scenarios such as the disbursement of funds or benefits where personal discretion in relation to selecting beneficiaries needs to be restricted. 3. Immutability. Once the data has been written to the blockchain, it is extremely difficult to change it back. It is not genuinely immutable, but because changing data is so challenging and nearly impossible, this is seen as a benefit to maintaining an immutable ledger of transactions. 4. High availability. As the system is based on thousands of nodes in a peer-to-peer network and the data is replicated and updated on every node, the system becomes highly available. Even if some nodes leave the network or become inaccessible, the network as a whole continues to work, thus making it highly available. This redundancy results in high availability. 5. Highly secure. All transactions on a blockchain are cryptographically secured and thus provide network integrity. Any transactions posted from the nodes on the blockchain are verified based on a predetermined set of rules. Only valid transactions are selected for inclusion in a block. The blockchain is based on proven cryptographic technology that ensures the integrity and availability of data. Generally, confidentiality is not provided due to the requirements of transparency. This limitation is the leading barrier to its adoption by financial institutions and other industries that require the privacy and confidentiality of transactions. As such, the privacy and confidentiality of transactions on the blockchain are being researched very actively, and advancements are already being made. It could be argued that in many situations, confidentiality is not needed and transparency is preferred. For example, with Bitcoin, confidentiality is not an absolute requirement. However, it is desirable in some scenarios. A more recent example is Zcash, https://z.cash, which provides a platform for conducting anonymous transactions. Other security services such as non-repudiation and authentication are also provided by blockchain, as all actions are secured using private keys and digital signatures. 6. Simplification of current paradigms. The current blockchain model in many industries such as finance or health is somewhat disorganized. In this model, multiple entities maintain their own databases and data sharing can become very difficult due to the disparate nature of the systems. However, as a blockchain can serve as a single shared ledger among many interested parties, this can result in simplifying the model by reducing the complexity of managing the separate systems maintained by each entity. 7. Faster dealings. In the financial industry, especially in post-trade settlement functions, blockchain can play a vital role by enabling the quick settlement of trades. Blockchain does not require a lengthy process of verification, reconciliation, and clearance because a single version of agreed-upon data is already available on a shared ledger between financial organizations. 8. Cost saving. As no trusted third party or clearinghouse is required in the blockchain model, this can massively eliminate overhead costs in the form of the fees, which are paid to such parties. 9. Platform for smart contracts. A blockchain is a platform on which programs can run that execute business logic on behalf of the users. This is a very useful feature, but not all blockchains have a mechanism to execute smart contracts. However, this is a very desirable feature. It is available on newer blockchain platforms such as Ethereum and multi-chain, but not on Bitcoin. Smart contracts. Blockchain technology provides a platform for running smart contracts. These are automated autonomous programs that reside on the blockchain network and encapsulate the business logic and code needed to execute a required function when certain conditions are met. For example, think about an insurance contract where a claim is paid to the traveler if the flight is cancelled. In the real world, this process normally takes a significant amount of time to make the claim, verify it, and pay the insurance amount to the claimant, traveler. What if this whole process were automated with cryptographically enforced trust, transparency, and execution so that as soon as the smart contract received the feed that the flight in question has been cancelled, it automatically triggers the insurance payment to the claimant. If the flight is on time, the smart contract pays itself. This is indeed a revolutionary feature of blockchain, as it provides flexibility, speed, security, and automation for real-world scenarios that can lead to a completely trustworthy system with significant cost reductions. Smart contracts can be programmed to perform any actions that blockchain users need and according to their specific business requirements. 10. Smart property. It is possible to link a digital or physical asset to the blockchain in such a secure and precise manner that it cannot be claimed by anyone else. You are in full control of your asset and it cannot be double spent or double owned. Compare this with a digital music file, for example, which can be copied many times without any controls. While it is true that many digital rights management (DRM) schemes are being used currently along with copyright laws, none of them are enforceable in the way a blockchain-based DRM can be. Blockchain can provide digital rights management functionality in such a way that it can be enforced fully. There are There are famously broken DRM schemes that look great in theory but were hacked due to one limitation or another. One example is the Oculus hack. www.wired.co.uk/article/Oculus Rift-DRM-hacked. Another example is the PS3 hack. Also copyrighted digital music, films, and ebooks are routinely shared on the internet without any limitations. We have had copyright protection in place for many years. But digital piracy refutes all attempts to fully enforce the law. On a blockchain, however, if you own an asset, no one else can claim it unless you decide to transfer it. This feature has far-reaching implications, especially in DRM and eCash systems, where double spend detection is a crucial requirement. The double spend problem was first solved without the requirement of a trusted third party in Bitcoin. As with any technology, some challenges need to be addressed in order to make a system more robust, useful, and accessible. Blockchain technology is no exception. In fact, much effort is being made in both academia and industry to overcome the challenges posed by blockchain technology. The most sensitive blockchain problems are as follows. Scalability. Currently, blockchain networks are not as scalable as, for example, current financial networks. This is a known area of concern and a very ripe area for research. Adoption. Often, blockchain is seen as a nascent technology. Even though this perspective is rapidly changing, there is still a long way to go before the mass adoption of this technology. The challenge here is to allow blockchain networks to be easier to use so that adoption can increase. In addition, several other challenges such as scalability introduced previously exist, which must be solved in order to increase adoption. Regulation. Due to its decentralized nature, regulation is almost impossible on blockchain. This is sometimes seen as a barrier toward adoption because traditionally, due to the existence of regulatory authorities, consumers have a certain level of confidence that if something goes wrong, they can hold someone accountable. However, in blockchain networks, no such regulatory authority and control exists, which is an inhibiting factor for many consumers. Relative immature technology. As compared to traditional IT systems that have benefited from decades of research, blockchain is still a new technology that requires a lot of research to achieve maturity. Privacy and confidentiality. Privacy is a concern on public blockchains such as Bitcoin, where everyone can see every single transaction. This transparency is not desirable in many industries such as the financial, law, or medical sectors. This is also a known concern and a lot of valuable research with some impeccable solutions has already been developed. However, further research is still required to drive the mass adoption of blockchain. All of these issues and possible solutions will be discussed in detail in Chapter 21, Scalability and Other Challenges. You now know the basics of blockchain and its benefits and limitations. Now let's take a look at the various types of blockchain that exist. Types of blockchain. Based on the way that blockchain has evolved over the last few years, it can be divided into multiple categories with distinct, though sometimes partially overlapping attributes. You should note that the tiers described earlier in the chapter are a different concept, whereby the logical categorization of blockchain based upon its evolution and usage is presented. In this section, we will examine the different types of blockchains from a technical and business use perspective. These blockchain types can occur on any blockchain tier, as there is no direct relationship between those tiers mentioned earlier and the various types of blockchain. In this section, we'll examine In this section, we'll examine distributed ledgers, distributed ledger technology, DLT, blockchains, ledgers. Distributed ledgers. First, I need to clarify an ambiguity. It should be noted that a distributed ledger is a broad term describing shared databases. Hence, all blockchains technically fall under the umbrella of shared databases or distributed ledgers. Although all blockchains are fundamentally distributed ledgers, all distributed ledgers are not necessarily blockchains. A critical difference between a distributed ledger and a blockchain is that a distributed ledger does not necessarily consist of blocks of transactions to keep the ledger growing. Rather, a blockchain is a special type of shared database that is comprised of blocks of transactions. An example of a distributed ledger that does not use blocks of transactions is R3's Corda, Corda.net, www.corda.net. Corda is a distributed ledger that is developed to record and manage agreements and is especially focused on the financial services industry. On the other hand, more widely known blockchains like Bitcoin and Ethereum make use of blocks to update the shared database. As the name suggests, a distributed ledger is distributed among its participants and spread across multiple sites or organizations. This type of ledger can be either private or public. The fundamental idea here is that, unlike many other blockchains, the records are stored continuously instead of being sorted into blocks. This concept is used in Ripple, which is a blockchain and cryptocurrency-based global payment network. Distributed ledger technology. It should be noted that over the last few years, the terms distributed ledger or DLT have grown to be commonly used to describe blockchain in the finance industry. Sometimes blockchain and DLT are used interchangeably, though this is not entirely accurate. It is how the term has evolved recently, especially in the finance sector. In fact, DLT is now a very active and thriving area of research in the financial sector. From a financial sector point of view, DLTs are permissioned blockchains that are used by consortiums. DLTs usually serve as a shared database, with all participants known and verified. They do not have a cryptocurrency and do not require mining to secure the ledger. At a broader level, DLT is an umbrella term that represents distributed ledger technology as a whole, comprising of blockchains and distributed ledgers of different types. Public blockchains. As the name suggests, public blockchains are not owned by anyone. They are open to the public, and anyone can participate as a node in the decision-making process. Users may or may not be rewarded for their participation. All users of these permissionless or unpermissioned ledgers maintain a copy of the ledger on their local nodes and use a distributed consensus mechanism to decide the eventual state of the ledger. Bitcoin and Ethereum are considered public blockchains. Private blockchains. As the name implies, private blockchains are just that, private. That is, they are open only to a consortium or group of individuals or organizations who have decided to share the ledger among themselves. There are various blockchains now available in this category, such as Cadena and Quorum. Optionally, both of these blockchains can also run in public mode if required, but their primary purpose is to provide a private blockchain. Semi-private blockchains. With semi-private blockchains, part of the blockchain is private and part of it is public. Note that this is still just a concept today, and no real-world proofs of concept have yet been developed. With a semi-private blockchain, the private part is controlled by a group of individuals, while the public part is open for participation by anyone. This hybrid model can be used in scenarios where the private part of the blockchain remains internal and shared among known participants, while the public part of the blockchain can still be used by anyone, optionally allowing mining to secure the blockchain. This way, the blockchain as a whole can be secured using POW, thus providing consistency and validity for both the private and public parts. This type of blockchain can also be called a semi-decentralized model, where it is controlled by a single entity, but still allows for multiple users to join the network by following appropriate procedures. Sidechains, more precisely known as pegged sidechains. This is a concept whereby coins can be moved from one blockchain to another and then back again. Typical uses include the creation of new altcoins, alternative cryptocurrencies, whereby coins are burnt as a proof of an adequate stake. Burnt or burning the coins in this context means that the coins are sent to an address that is unspendable, and this process makes the burnt coins irrecoverable. This mechanism is used to bootstrap a new currency or introduce scarcity, which results in the increased value of the coin. This mechanism is also called proof of burn and is used as an alternative method for distributed consensus to POW and proof of stake POS. The example provided previously for burning coins applies to a one-way pegged sidechain. The second type is called a two-way pegged sidechain. Which allows the movement of coins from the main chain to the sidechain and back to the main chain when required. This process enables the building of smart contracts for the Bitcoin network. Rootstock is one of the leading examples of a sidechain, which enables smart contract development for Bitcoin using this paradigm. It works by allowing a two-way peg for the Bitcoin blockchain, and this results in much faster throughput. Permissioned ledger. A permissioned ledger is a blockchain where participants of the network are already known and trusted. Permissioned ledgers do not need to use a distributed consensus mechanism. Instead, an agreement protocol is used to maintain a shared version of the truth about the state of the records on the blockchain. In this case, for verification of transactions on the chain, all verifiers are already pre-selected by a central authority, and typically there is no need for a mining mechanism. By definition, there is also no requirement for a permissioned blockchain to be private, as it can be a public blockchain but with regulated access control. For example, Bitcoin can become a permissioned ledger if an access control layer is introduced on top of it that verifies the identity of a user and then allows access to the blockchain. Shared ledger. This is a generic term that is used to describe any application or database that is shared by the public or a consortium. Generally, all blockchains fall into the category of a shared ledger. Fully private and proprietary blockchains. There is no mainstream application of these types of blockchains, as they derive from the core concept of decentralization in blockchain technology. Nonetheless, in specific private settings within an organization, there could be a need to share data and provide some level of guarantee of the authenticity of the data. An example of this type of blockchain might be to allow for collaboration and the sharing of data between various government departments. In that case, no complex consensus mechanism is required, apart from simple SMR and an agreement protocol with known central validators. Even in private blockchains, tokens are not really required, but they can be used as a means of transferring value or representing some real-world assets. Tokenized blockchains. These blockchains are standard blockchains that generate cryptocurrency as a result of consensus process via mining or initial distribution. Bitcoin and Ethereum are prime examples of this type of blockchain. Tokenless blockchains. Tokenless blockchains. These blockchains are designed in such a way that they do not have the basic unit for the transfer of value. However, they are still valuable in situations where there is no need to transfer value between nodes and only the sharing of data among various trusted parties is required. This is similar to fully private blockchains, the only difference being that the use of tokens is not required. This can also be thought of as a shared distributed ledger used for storing and sharing data between the participants. It does have its benefits when it comes to immutability, tamper-proofing, security, and consensus-driven updates, but is not used for a common blockchain application of value transfer or cryptocurrency. Most of the permission blockchains can be seen as an example of tokenless blockchains. For example, Hyperledger Fabric or Quorum. Tokens can be built on these chains as an application, but intrinsically these blockchains do not have a token associated with them. All the aforementioned terminologies are used in literature, but fundamentally all these blockchains are distributed ledgers and fall under the top-level category of DLTs. We can view these different types in the simple chart as follows. This ends our examination of the various types of blockchain. We'll now move on to the next section to discuss the concept of consensus. Consensus is the backbone of a blockchain, as it provides the decentralization of control through an optional process known as mining. The choice of the consensus algorithm to utilize is governed by the type of blockchain in use. That is, not all consensus mechanisms are suitable for all types of blockchains. For example, in public permissionless blockchains, it would make sense to use POW instead of mechanisms that are more suitable for permission blockchains, such as proof of authority, POA, or traditional Byzantine fault-tolerant consensus mechanisms. Therefore, it is essential to choose an appropriate consensus algorithm for a particular blockchain project. Consensus is a process of achieving agreement between distrusting nodes on the final state of data. To achieve consensus, different algorithms are used. It is easy to reach an agreement between two nodes, in client-server systems for example. But when multiple nodes are participating in a distributed system and they need to agree on a single value, it becomes quite a challenge to achieve consensus. This process of attaining agreement on a common state or value among multiple nodes, despite the failure of some nodes, is known as distributed consensus. Consensus mechanism. A consensus mechanism is a set of steps that are taken by most or all nodes in a blockchain to agree on a proposed state or value. For more than 3 decades, this concept has been researched by computer scientists in industry and academia. With the advent of blockchain and Bitcoin, consensus mechanisms have come into the limelight again and gained considerable popularity. There are various requirements for a consensus mechanism. The following describes these requirements. Agreement. All honest nodes decide on the same value. Integrity. This is a requirement that no node can make the decision more than once in a single consensus cycle. Validity. The value agreed upon by all honest nodes must be the same as the initial value proposed by at least one honest node. Fault tolerant. The consensus algorithm should be able to run correctly in the presence of faulty or malicious nodes. Byzantine nodes. Termination. All honest nodes terminate the execution of the consensus process and eventually reach a decision. Having seen these general requirements, we'll now look at the different types of consensus mechanisms. Types of consensus mechanisms. All consensus mechanisms are developed with faults in a distributed system to allow distributed systems to reach a final state of agreement. There are two general categories of consensus mechanisms. These categories deal with all types of faults: fail-stop types or arbitrary. These common types of consensus mechanisms are as follows. Proof-based consensus mechanisms. This arrangement requires nodes to complete a leader election lottery, and the node that wins proposes the final value. The algorithm works on the principle of providing proof of some work and the possession of some authority or tokens to win the right of proposing the next block. For example, the POW mechanism used in Bitcoin falls into this category, where a miner who solves the computational puzzle as a proof of computational effort expended wins the right to add the next block to the blockchain. Traditional fault tolerance based. With no compute-intensive operations such as partial hash inversion, as in Bitcoin POW, this type of consensus mechanism relies on a simple scheme of nodes that publish and verify signed messages in a number of phases. Eventually, when a certain number of messages are received over a period of rounds, phases, then an agreement is reached. To achieve fault tolerance, replication is used. This is a standard and widely used method to achieve fault tolerance. In general, there are two types of faults that a node can experience. Fail-stop faults. This type of fault occurs when a node merely has crashed. Fail-stop faults are the easier ones to deal with of the two fault types. Paxos or the RAF protocol introduced earlier in this chapter are normally used to deal with this type of fault. These faults are simpler to deal with. Byzantine faults. The second type of fault is one where the faulty node exhibits malicious or inconsistent behavior arbitrarily. This type is difficult to handle since it can create confusion due to misleading information. This can be a result of an attack by adversaries, a software bug, or data corruption. SMR protocols such as Practical Byzantine Fault Tolerance, PBFT, was developed to address this second type of faults. Many other implementations of consensus protocols have been proposed in traditional distributed systems. Paxos is the most famous of these protocols. It was introduced by Leslie Lamport in 1989. With Paxos, nodes are assigned various roles such as proposer, acceptor, and learner. Nodes or processes are named replicas, and consensus is achieved in the presence of faulty nodes by an agreement among a majority of nodes. An alternative to Paxos is Raft, which works by assigning any of the three states, that is, follower, candidate, or leader, to the nodes. A leader is elected after a candidate node receives enough votes, and all changes then have to go through the leader. The leader commits the proposed changes. Once replication on the majority of the follower nodes. The leader commits the proposed changes once replication on the majority of the follower nodes is completed. We will briefly touch on some aspects of consensus in blockchain now, but more detail on the theory of consensus mechanisms from a distributed system point of view, and also from the blockchain perspective, will be presented in Chapter 5. Consensus algorithms. Consensus in blockchain. Consensus is a distributed computing concept that has been used in blockchain in order to provide a means of agreeing to a single version of the truth by all peers on the blockchain network. This concept was previously discussed in the distributed systems section of this chapter. In this section, we will address consensus in the context of blockchain technology. Some concepts presented following are still relevant to the distributed systems theory, but they are explained from a blockchain perspective. Roughly, the following describes the two main categories of consensus mechanisms. 1. Proof-based leader election, lottery-based, or the Nakamoto consensus, whereby a leader is elected at random using an algorithm and proposes a final value. This category is also referred to as the fully decentralized or permissionless type of consensus mechanism. This type is well used in the Bitcoin and Ethereum blockchain in the form of a POW mechanism. 2. Byzantine fault tolerance, BFT based, is a more traditional approach based on rounds of votes. This class of consensus is also known as the consortium or permission type of consensus mechanism. BFT-based consensus mechanisms perform well when there are a limited number of nodes, but they do not scale well. On the other hand, leader election lottery-based POW consensus mechanisms scale very well but perform very slowly. As there is significant research being conducted in this area, new types of consensus mechanism are also emerging, such as the semi-decentralized type, which is used in the Ripple network. The Ripple network will be discussed in detail in this book's online content pages. Here, static.pact-cdn.com/download/altcoins_Ethereum_projects_and_more bonus_content.pdf. There are also various other proposals out there, which are trying to find the right balance between scalability and performance. Some notable projects include PBFT, Hybrid, BFT, Block DAG, Tezos, Stellar, and Ghost. The consensus algorithms available today or that are being researched in the context of blockchain are presented as follows. The following is not an exhaustive list, but it includes all notable algorithms. Proof of work, POW. This type of consensus mechanism relies on proof that adequate computational resources have been spent before proposing a value for acceptance by the network. This scheme is used in Bitcoin, Litecoin, and other cryptocurrency blockchains. Currently, it is the only algorithm that has proven to be astonishingly successful against any collusion attacks on a blockchain network, such as the Sybil attack. The Sybil attack will be discussed in Chapter 6, Introducing Bitcoin. Proof of stake. This algorithm works on the idea that a node or user has an adequate stake in the system. That is, the user has invested enough in the system so that any malicious attempt by that user would outweigh the benefits of performing such an attack on the network. This idea was first introduced by Peercoin, and it is going to be used in the Ethereum blockchain version called Serenity. Another important concept in POS is coin age, which is a criterion derived from the amount of time and number of coins that have not been spent. In this model, the chances of proposing and signing the next block increase with the coin age. Delegated Proof of Stake, DPoS. This is an innovation over standard POS, whereby each node that has a stake in the system can delegate the validation of a transaction to other nodes by voting. It is used in the BitShares blockchain. Proof of Elapsed Time, POET. introduced by Intel in 2016. POET uses a Trusted Execution Environment, TEE, to provide randomness and safety in the leader election process via a guaranteed wait time. It requires the Intel SGX Software Guard Extensions processor to provide the security guarantee for it to be secure. This concept is discussed in more detail in Chapter 17, Hyperledger, in the context of the Intel Sawtooth Lake blockchain project. Proof of deposit. In this case, nodes that wish to participate in the network have to make a security deposit before they can mine and propose blocks. This mechanism is used in the Tendermint blockchain. Proof of importance, POI. This idea is significant and different from POS. POI not only relies on how large a stake a user has in the system, but it also monitors the usage and movement of tokens by the user in order to establish a level of trust and importance. It is used in the NEM coin blockchain. More information about this coin is available from NEM's website, nem.io. Federated Consensus or Federated Byzantine Consensus. This mechanism is used in the Stellar Consensus Protocol. Nodes in this protocol retain a group of publicly trusted peers and propagate only those transactions that have been validated by the majority of trusted nodes. Reputation-based mechanisms. As the name suggests, a leader is elected by the reputation it has built over time on the network. It is based on the votes of other members. Practical Byzantine Fault Tolerance, PBFT. This mechanism achieves SMR, which provides tolerance against Byzantine nodes. Various other protocols, including PBFT, Paxos, Raft, and Federated Byzantine Agreement, FBA, are also being used or have been proposed for use in many different implementations of distributed systems and blockchains. Proof of Activity, POA. This scheme is a combination of POS and POW, which ensures that a stakeholder is selected in a pseudo-random but uniform fashion. This is a comparatively more energy-efficient mechanism as compared to POW. It utilizes a new concept called Follow the Satoshi. In this scheme, POW and POS are combined together to achieve consensus and a good level of security. This scheme is more energy efficient as POW is used only in the first stage of the mechanism. After the first stage, it switches to POS, which consumes negligible energy. We will discuss these ideas further in Chapter 7, Bitcoin Network and Payments, where protocols are reviewed in the context of advanced Bitcoin protocols. Proof of Capacity, POC. This scheme uses hard disk space as a resource to mine the blocks. This is different from POW, where CPU resources are used. In POC, hard disk space is utilized for mining, and as such is also known as hard drive mining. This concept was first introduced in the Burstcoin cryptocurrency. Proof of Storage. This scheme allows for the outsourcing of storage capacity. This scheme is based on the concept that a particular piece of data is probably stored by a node, which serves as a means to participate in the consensus mechanism. Several variations of this scheme have been proposed, such as proof of replication, proof of data possession, proof of space, and proof of space-time. Proof of authority. This scheme utilizes the identity of the participants called validators as a stake on the network. Validators are known and have the authority to propose new blocks. Validators propose the new blocks and validate them as per blockchain rules. Commonly used POA algorithms are Click and Aura. Some prominent protocols in blockchain will be discussed in detail in Chapter 5, Consensus Algorithms. In this chapter, a light introduction is presented only. Remember, earlier in this chapter we said that distributed systems are difficult to build and a distributed system cannot have consistency, availability, and partition tolerance at the same time. This is a proven result. However, in blockchain it seems that this theorem is somehow violated. In the next section, we will introduce the CAP theorem formally and discuss why blockchain appears to achieve all three properties simultaneously. CAP theorem and blockchain. The CAP theorem, also known as Brewer's theorem, was first introduced by Eric Brewer in 1998 as a conjecture. In 2002, it was proven as a theorem by Seth Gilbert and Nancy Lynch. The theorem states that any distributed system cannot have consistency, availability, and partition tolerance simultaneously. Consistency is a property that ensures that all nodes in a distributed system have a single, current, and identical copy of the data. Consistency is achieved using consensus algorithms in order to ensure that all nodes have the same copy of the data. This is also called state machine replication. The blockchain is a means for achieving state machine replication. Availability means that the nodes in the system are up, accessible for use, and are accepting incoming requests and responding with data without any failures as and when required. In other words, data is available at each node and the nodes are responding to requests. Partition tolerance ensures that if a group of nodes is unable to communicate with other nodes due to network failures, the distributed system continues to operate correctly. This can occur due to network and node failures. A Venn diagram is commonly used to visualize the CAP theorem. Consistency, availability, partition tolerance. The preceding diagram shows that only two properties at a time can be achieved, either AP, CA, or CP. In summary, 1. If we opt for CP, consistency and partition tolerance, we sacrifice availability. 2. If we opt for AP, availability and partition tolerance, we sacrifice consistency. 3. If we opt for AC, availability and consistency, we sacrifice partition tolerance. Usually a network partition cannot be ignored. Therefore, the choice mostly becomes either consistency or availability in the case of a network partition. As shown previously, a distributed system cannot have consistency, availability, and partition tolerance simultaneously. This can be explained with the following example. Let's imagine that there is a distributed system with two nodes. Now let's apply the three theorem properties on the smallest of possible distributed systems only with two nodes. Consistency is achieved if both nodes have the same shared state. That is, they have the same up-to-date copy of the data. Availability is achieved if both nodes are up and running and responding with the latest copy of data. Partition tolerance is achieved if, despite communication failure or delay between nodes, the network distributed system continues to operate. Now think of a scenario where a partition occurs, and nodes can no longer communicate with each other. If new updated data comes in now, it can only be updated on one node only. In that case, if the node accepts the update, then only that one node in the network is updated, and therefore consistency is lost. Now if the update is rejected by the node, that would result in loss of availability. In that case, due to partition tolerance, both availability and consistency are unachievable. This is strange because somehow blockchain manages to achieve all of these properties, or does it? It seems that the CAP theorem is violated by blockchain, especially in its most successful implementation. Bitcoin. However, this is not the case. In blockchains, consistency is sacrificed in favor of availability and partition tolerance. In this scenario, consistency C on the blockchain is not achieved simultaneously with partition tolerance P and availability A, but it is achieved over time. This is called eventual consistency, where consistency is achieved as a result of validation from multiple nodes over time. It means that there can be a temporary disagreement between nodes on the final state, but it is eventually agreed upon. For example, in Bitcoin, multiple transaction confirmations are required to achieve a good level of confidence that transactions may not be rolled back in the future, and eventually a consistent view of transaction history is available to all nodes. Multiple confirmations of a transaction over time provide eventual consistency in Bitcoin. For this purpose, the process of mining was introduced in Bitcoin. Mining is a process that facilitates the achievement of consensus by using the POW algorithm. At a higher level, mining can be defined as a process that is used to add more blocks to the blockchain. We will cover more on this later in Chapter 6, Introducing Bitcoin. Summary. This chapter introduced blockchain technology at an advanced level. First, we discussed blockchain's progress toward becoming a mature technology, followed by some basic concepts about distributed systems, and then the history of blockchain was reviewed. Concepts such as eCash were also discussed. Various definitions of blockchain from different points of view were presented. Some applications of blockchain technology were also introduced. Next, different types of blockchain were explored. Finally, the benefits and limitations of this new technology were also examined. Some topics such as blockchain scalability and adaptability issues were intentionally introduced only lightly, as they will be discussed in depth in later chapters. In the next chapter, we will introduce the concept of decentralization, which is central to the idea behind blockchains and their vast number of applications.
Chapter 2. Decentralization. Decentralization is not a new concept. It has been in use in strategy, management, and government for a long time. The basic idea of decentralization is to distribute control and authority to the peripheries of an organization instead of one central body being in full control of the organization. This configuration produces several benefits for organizations, such as increased efficiency, expedited decision-making, better motivation, and a reduced burden on top management. In this chapter, the concept of decentralization will be discussed in the context of blockchain. The fundamental basis of blockchain is that no single central authority is in control of the network. This chapter will present examples of various methods of decentralization and ways to achieve it. Furthermore, the decentralization of the blockchain ecosystem, decentralized applications, and platforms for achieving decentralization will be discussed in detail. Many exciting applications and ideas emerge from the decentralized blockchain technology, such as decentralized finance and decentralized identity, which will be introduced in this chapter. Decentralization using blockchain. Decentralization is a core benefit and service provided by blockchain technology. By design, blockchain is a perfect vehicle for providing a platform that does not need any intermediaries and that can function with many different leaders chosen via consensus mechanisms. This model allows anyone to compete to become the decision-making authority. A consensus mechanism governs this competition, and the most famous method is known as proof of work, POW. Decentralization is applied in varying degrees from a semi-decentralized model to a fully decentralized one, depending on the requirements and circumstances. Decentralization can be viewed from a blockchain perspective as a mechanism that provides a way to remodel existing applications and paradigms, or to build new applications, to give full control to users. Information and Communication Technology, ICT, has conventionally been based on a centralized paradigm whereby database or application servers are under the control of a central authority, such as a system administrator. With Bitcoin and the advent of blockchain technology, this model has changed, and now the technology exists to allow anyone to start a decentralized system and operate it with no single point of failure or single trusted authority. It can either be run autonomously or by requiring some human intervention, depending on the type and model of governance used in the decentralized application running on the blockchain. The following diagram shows the different types of systems that currently exist: central, distributed, and decentralized. This concept was first published by Paul Baran in On Distributed Communications. 1. Introduction to Distributed Communications Networks. Rand Corporation, 1964. Centralized systems are conventional, client-server IT systems in which there is a single authority that controls the system, and who is solely in charge of all operations on the system. All users of a centralized system are dependent on a single source of service. The majority of online service providers, including Google, Amazon, eBay, and Apple's App Store, use this conventional model to deliver services. In a distributed system, data and computation are spread across multiple nodes in the network. Sometimes this term is confused with parallel computing. While there is some overlap in the definition, the main difference between these systems is that in a parallel computing system, computation is performed by all nodes simultaneously in order to achieve the result. For example, parallel computing platforms are used in weather research and forecasting, simulation, and financial modeling. On the other hand, in a distributed system, computation may not happen in parallel and data is replicated across multiple nodes that users view as a single, coherent system. Variations of both of these models are used to achieve fault tolerance and speed. In the parallel system model, there is still a central authority that has control over all nodes and governs processing. This means that the system is still centralized in nature. The critical difference between a decentralized system and distributed system is that in a distributed system, there is still a central authority that governs the entire system, whereas in a decentralized system, no such authority exists. A decentralized system is a type of network where nodes are not dependent on a single master node. Instead, control is distributed among many nodes. This is analogous to a model where each department in an organization is in charge of its own database server, thus taking away the power from the central server and distributing it to the sub-departments who manage their own databases. A significant innovation in the decentralized paradigm that has given rise to this new era of decentralization of applications is decentralized consensus. This mechanism came into play with Bitcoin, and it enables a user to agree on something via a consensus algorithm without the need for a central trusted third party, intermediary, or service provider. We can also now view the different types of networks shown earlier from a different perspective, where we highlight the controlling authority of these networks as a symbolic hand, as shown in the following diagram. This model provides a clearer understanding of differences between these networks from a decentralized point of view. The preceding diagram shows that the centralized model is the traditional one in which a central controller exists, and it can be viewed as a depiction of the usual client-server model. In the middle, we have distributed systems where we still have a central controller, but the system comprises many dispersed nodes. On the right-hand side, notice that there is no hand controller controlling the networks. This is the key difference between decentralized
and distributed networks. A decentralized system may look like a distributed system from a topological point of view, but it doesn't have a central authority that controls the network. The differences between distributed and decentralized systems can also be viewed at a practical level in the following diagrams. The following diagram shows a decentralized system based on blockchain, where an exact replica of the applications and data is maintained across the entire network on each participating node. A comparison between centralized and decentralized systems, networks, applications is shown in the following table. The comparison in the table only covers some main features and is not an exhaustive list of all features. There may be other features of interest that can be compared too, but this list should provide a good level of comparison. Now we will discuss what methods can be used to achieve decentralization. Methods of decentralization. Two methods can be used to achieve decentralization: disintermediation and competition. These methods will be discussed in detail in the sections that follow. Disintermediation. The concept of disintermediation can be explained with the aid of an example. Imagine that you want to send money to a friend in another country. You go to a bank which, for a fee, will transfer your money to the bank in that country. In this case, the bank maintains a central database that is updated, confirming that you have sent the money. With blockchain technology, it is possible to send this money directly to your friend without the need for a bank. All you need is the address of your friend on the blockchain. This way, the intermediary, that is, the bank, is no longer required, and decentralization is achieved by disintermediation. It is debatable, however, how practical decentralization through disintermediation is in the financial sector due to the massive regulatory and compliance requirements. Nevertheless, this model can be used not only in finance but in many other industries as well, such as health, law, and the public sector. In the health industry, where patients, instead of relying on a trusted third party, such as the hospital record system, can be in full control of their own identity and their data that they can share directly with only those entities that they trust. As a general solution, blockchain can serve as a decentralized health record management system where health records can be exchanged securely and directly between different entities, hospitals, pharmaceutical companies, patients, globally, without any central authority. Contest-driven decentralization. In the method involving competition, different service providers compete with each other in order to be selected for the provision of services by the system. This paradigm does not achieve complete decentralization. However, to a certain degree, it ensures that an intermediary or service provider is not monopolizing the service. In the context of blockchain technology, a system can be envisioned in which smart contracts can choose an external data provider from a large number of providers based on the reputation, previous score, reviews, and quality of service. This method will not result in full decentralization, but it allows smart contracts to make a free choice based on the criteria just mentioned. This way, an environment of competition is cultivated among service providers where they compete with each other to become the data provider of choice. In the following diagram, varying levels of decentralization are shown. On the left side, the conventional approach is shown where a central system is in control. On the right side, complete disintermediation is achieved, as intermediaries are entirely removed. Competing intermediaries or service providers are shown in the center. At that level, intermediaries or service providers are selected based on reputation or voting, thus achieving partial decentralization. There are many benefits of decentralization, including transparency, efficiency, cost-saving, development of trusted ecosystems, and in some cases, privacy and anonymity. Some challenges, such as security requirements, software bugs, and human error, need to be examined thoroughly. For example, in a decentralized system such as Bitcoin or Ethereum, where security is normally provided by private keys, how can we ensure that an asset or a token associated with these private keys cannot be rendered useless due to negligence or bugs in the code? What if the private keys are lost due to user negligence? What if, due to a bug in the smart contract code, the decentralized application becomes vulnerable to attack? Before embarking on a journey to decentralize everything using blockchain and decentralized applications, it is essential that we understand that not everything can or needs to be decentralized. This view raises some fundamental questions. Is a blockchain really needed? When is a blockchain required? In what circumstances is blockchain preferable to traditional databases? To answer these questions, go through the simple set of questions presented below. Answering all of these questions can help you decide whether or not a blockchain is required or suitable for solving the problem. Beyond the questions posed in this model, there are many other issues to consider, such as latency, choice of consensus mechanisms, whether consensus is required or not, and where consensus is going to be achieved. If consensus is maintained internally by a consortium, then a private blockchain should be used. Otherwise, if consensus is required publicly among multiple entities, then a public blockchain solution should be considered. Other aspects such as immutability should also be considered when deciding whether to use a blockchain or a traditional database. If strict data immutability is required, then a public blockchain should be used. Otherwise, a central database may be an option. As blockchain technology matures, there will be more questions raised regarding this selection model. For now, however, this set of questions is sufficient for deciding whether a blockchain-based solution is suitable or not. Now we understand different methods of decentralization and have looked at how to decide whether a blockchain is required or not in a particular scenario. Let's now look at the process of decentralization, that is, how we can take an existing system and decentralize it. First, we'll briefly look at the different ways to achieve decentralization. Routes to decentralization. There are systems that predate blockchain and Bitcoin, including BitTorrent and the Nutella file sharing system, which to a certain degree could be classified as decentralized, but due to a lack of any incentivization mechanism, participation from the community gradually decreased. There wasn't any incentive to keep the users interested in participating in the growth of the networks. With the advent of blockchain technology, many initiatives are being taken to leverage this new technology to achieve decentralization. The Bitcoin blockchain is typically the first choice for many, as it has proven to be the most resilient and secure blockchain and has a market cap of nearly $166 billion at the time of writing. Alternatively, other blockchains such as Ethereum serve as the tool of choice for many developers for building decentralized applications. Compared to Bitcoin, Ethereum has become a more prominent choice because of the flexibility it allows for programming any business logic into the blockchain by using smart contracts. How to decentralize. Arvind Narayanan and others have proposed a framework in their book Bitcoin and Cryptocurrency Technologies that can be used to evaluate the decentralization requirements of a variety of issues in the context of blockchain technology. The framework raises 4 questions whose answers provide a clear understanding of how a system can be decentralized. 1. What is being decentralized? 2. What level of decentralization is required? 3. What blockchain is used? 4. What security mechanism is used?
The first question simply asks you to identify what system is being decentralized. This can be any system, such as an identity system or a trading system.
The second question asks you to specify the level of decentralization required by examining the scale of decentralization. As discussed earlier, it can be full disintermediation or partial disintermediation. The third question asks developers to determine which blockchain is suitable for a particular application. It can be Bitcoin blockchain, Ethereum blockchain, or any other blockchain that is deemed fit for the specific application. Finally, a fundamental question that needs to be addressed is how the security of a decentralized system will be guaranteed. For example, the security mechanism can be atomicity-based, where either the transaction executes in full or does not execute at all. This deterministic approach ensures the integrity of the system. Other mechanisms may include one based on reputation, which allows for varying degrees of trust in a system. In the following section, let's evaluate a money transfer system as an example of an application selected to be decentralized. Decentralization framework example. The 4 questions discussed previously are used to evaluate the decentralization requirements of this application. The answers to these questions are as follows. 1. Money transfer system. 2. disintermediation. 3. Bitcoin. 4. Atomicity. The responses indicate that the money transfer system can be decentralized by removing the intermediary, implemented on the Bitcoin blockchain, and that a security guarantee will be provided via atomicity. Atomicity will ensure that transactions execute successfully in full or do not execute at all.
We have chosen the Bitcoin blockchain because it is the longest established blockchain and has stood the test of time. Similarly, this framework can be used for any other system that needs to be evaluated in terms of decentralization.
The answers to these 4 simple questions help clarify what approach to take to decentralize the system. To achieve complete decentralization, it is necessary that the environment around the blockchain also be decentralized. We'll look at the full ecosystem of decentralization next. Blockchain and full ecosystem decentralization. The blockchain is a distributed ledger that runs on top of conventional systems. These elements include storage, communication, and computation. There are other factors such as identity and wealth, which are traditionally based on centralized paradigms, and there's a need to decentralize these aspects as well in order to achieve a sufficiently decentralized ecosystem. Storage. Data can be stored directly in a blockchain, and with this fact it achieves decentralization. However, a significant disadvantage of this approach is that a blockchain is not suitable for storing large amounts of data by design. It can store simple transactions and some arbitrary data, but it is certainly not suitable for storing images or large blobs of data, as is the case with traditional database systems. A better alternative for storing data is to use distributed hash tables, DHTs. DHTs were used initially in peer-to-peer file sharing software, such as BitTorrent, Napster, Kazaa, and Gnutella. DHT research was made popular by the CAN, Chord, Pastry, and Tapestry projects. BitTorrent is the most scalable and fastest network, but the issue with BitTorrent and the others is that there is no incentive for users to keep the files indefinitely. Users generally don't keep files permanently, and if nodes that have data still required by someone leave the network, there is no way to retrieve it except by having the required nodes rejoin the network so that the files once again become available. 2 primary requirements here are high availability and link stability, which means that data should be available when required, and network links also should always be accessible. Interplanetary File System, IPFS, by Juan Benet, possesses both of these properties, and its vision is to provide a decentralized World Wide Web by replacing the HTTP protocol. IPFS uses Kademlia DHT and Merkle Directed Acyclic Graphs, DAGs, to provide storage and searching functionality respectively. The concept of DHTs and DAGs will be introduced in detail in Chapter 4, Public Key Cryptography. The incentive mechanism for storing data is based on a protocol known as Filecoin, which pays incentives to nodes that store data using the bit swap mechanism. The bit swap mechanism lets nodes keep a simple ledger of bytes sent or bytes received in a one-to-one relationship. Also, a Git-based version control mechanism is used in IPFS to provide structure and control over the versioning of data. There are other alternatives for data storage such as Ethereum Swarm, Storj, and MadeSafe. Ethereum has its own decentralized and distributed ecosystem that uses Swarm for storage and the Whisper protocol for communication. MadeSafe aims to provide a decentralized World Wide Web. All of these projects are discussed later in this book in greater detail. BigchainDB is another storage layer decentralization project aimed at providing a scalable, fast, and linearly scalable decentralized database as opposed to a traditional file system. BigchainDB complements decentralized processing platforms and file systems such as Ethereum and IPFS. Communication. The Internet, the communication layer in blockchain, is considered to be decentralized. This belief is correct to some extent, as the original version of the Internet was to develop a decentralized communication system. Services such as email and online storage are now all based on a paradigm where the service provider is in control, and users trust such providers to grant them access to the service as requested. This model is based on the unconditional trust of a central authority, the service provider, where users are not in control of their data. Even user passwords are stored on trusted third-party systems. Thus, there is a need to provide control to individual users in such a way that access to their data is guaranteed and is not dependent on a single third party. Access to the Internet, the communication layer, is based on Internet Service Providers, ISPs, who act as a central hub for Internet users. If the ISP is shut down for any reason, then no communication is possible with this model. An alternative is to use mesh networks. Even though they are limited in functionality when compared to the Internet, they still provide a decentralized alternative where nodes can talk directly to each other without a central hub, such as an ISP. An example of a mesh network is FireChat, which allows iPhone users to communicate with each other directly in a peer-to-peer fashion without an internet connection. More information is available at opengarden.com/firechat. Now imagine a network that allows users to be in control of their communication. No one can shut it down for any reason. This could be the next step toward decentralizing communication networks in the blockchain ecosystem. It must be noted that this model may only be vital in a jurisdiction where the internet is censored and controlled by the media. As mentioned earlier, the original vision of the internet was to build a decentralized network. However, over the years, with the advent of large-scale service providers such as Google, Amazon, and eBay, control is shifting toward these big players. For example, email is a decentralized system at its core. That is, anyone can run an email server with minimal effort and can start sending and receiving emails. There are better alternatives available. For example, Gmail and Outlook already provide managed services for end users. So there is a natural inclination toward selecting one of these large centralized services as they are more convenient and free to use. This is one example that shows how the internet has moved toward centralization. Free services, however, are offered at the cost of exposing valuable personal data, and many users are unaware of this fact. Blockchain has revived the vision of decentralization across the world, and now concerted efforts are being made to harness this technology and take advantage of the benefits that it can provide. Computing power and decentralization. Decentralization of computing or processing power is achieved by a blockchain technology such as Ethereum, where smart contracts with embedded business logic can run on the blockchain network. Other blockchain technologies also provide similar processing layer platforms, where business logic can run over the network in a decentralized manner. The following diagram shows an overview of a decentralized ecosystem. In the bottom layer, the internet or mesh networks provide a decentralized communication layer. In the next layer up, a storage layer uses technologies such as IPFS and BigChainDB to enable decentralization. Finally, in the next level up, you can see that the blockchain serves as a decentralized processing computation layer. Blockchain can, in a limited way, provide a storage layer too, but that severely hampers the speed and capacity of the system. Therefore, other solutions such as IPFS and BigChainDB are more suitable for storing large amounts of data in a decentralized way. The identity and wealth layers are shown at the top level. Identity on the internet is a vast topic, and systems such as BitAuth and OpenID provide authentication and identification services with varying degrees of decentralization and security assumptions. The blockchain is capable of providing solutions to various issues relating to decentralization, a concept relevant to identity known as Zukow's triangle. Requires that the naming system in a network protocol is secure, decentralized, and able to provide human, meaningful, and memorable names to the users. Conjecture has it that a system can have only two of these properties simultaneously. Nevertheless, with the advent of blockchain in the form of Namecoin, this problem was resolved. It is now possible to achieve security, decentralization, and human meaningful names with the Namecoin blockchain. However, this is not a panacea, and it comes with many challenges, such as reliance on users to store and maintain private keys securely. This opens up other general questions about the suitability of decentralization to a particular problem. Decentralization may not be appropriate for every scenario. Centralized systems with well-established reputations tend to work better in many cases. For example, email platforms from reputable companies such as Google or Microsoft would provide a better service than a scenario where individual email servers are hosted by users on the internet. There are many projects underway that are developing solutions for a more comprehensive, distributed blockchain system. For example, Swarm and Whisper are developed to provide decentralized storage and communication for Ethereum. We will discuss Swarm and Ethereum in more detail in Chapter 13, Ethereum Development Environment. With the advent of blockchain technology, it is now possible to build software versions of traditional physical organizations in the form of decentralized organizations, DOs, and other similar constructs, which we will examine in detail shortly. Moreover, with the emergence of the decentralization paradigm, different terminology and buzzwords are now appearing in the media and academic literature, which we will explore in the next section. Pertinent terminology. The following concepts are worth citing in the context of decentralization. The terminology introduced here is often used in the literature concerning decentralization and its applications. Smart contracts. A smart contract is a software program that usually runs on a blockchain. Smart contracts do not necessarily need a blockchain to run. However, due to the security benefits that blockchain technology provides, blockchain has become a standard decentralized execution platform for smart contracts. A smart contract usually contains some business logic and a limited amount of data. The business logic is executed if specific criteria are met. Actors or participants in the blockchain use these smart contracts or they run autonomously on behalf of the network participants. More information on smart contracts will be provided in Chapter 10, Smart Contracts. Autonomous agents. An autonomous agent, AA, is an artificially intelligent software entity that acts on the behalf of its owner to achieve some desirable goals without requiring any or minimal intervention from its owner. Decentralized organizations. DOs are software programs that run on a blockchain and are based on the idea of actual organizations with people and protocols. Once a DO is added to the blockchain in the form of a smart contract, or a set of smart contracts, it becomes decentralized and parties interact with each other based on the code defined within the DO software. Decentralized autonomous organizations. Just like DOs, a decentralized autonomous organization, DAO, is also a computer program that runs on top of a blockchain, and embedded within it are governance and business logic rules. DAOs and DOs are fundamentally the same thing. The main difference, however, is that DAOs are autonomous, which means that they are fully automated and contain artificially intelligent logic. DOs, on the other hand, lack this feature and rely on human input to execute business logic. Ethereum blockchain led the way with the introduction of DAOs. In a DAO, the code is considered the governing entity rather than people or paper contracts. However, a human curator maintains this code and acts as a proposal evaluator for the community. DAOs are capable of hiring external contractors if enough input is received from the token holders' participants. The most famous DAO project is the DAO, which raised $168 million in its crowdfunding phase. The DAO project was designed to be a venture capital fund aimed at providing a decentralized business model with no single entity as owner. Unfortunately, this project was hacked due to a bug in the DAO code and millions of dollars worth of Ether currency, Ethereum, was siphoned out of the project and into a child DAO created by hackers. A major network change, hard fork, was required on the Ethereum blockchain to reverse the impact of the hack and initiate the recovery of the funds. This incident opened up the debate on the security, quality, and need for thorough testing of the code in smart contracts in order to ensure their integrity and adequate control. There are other projects underway, especially in academia, that are seeking to formalize smart contract coding and testing. Currently, DAOs do not have any legal status, even though they may contain some intelligent code that enforces certain protocols and conditions. However, these rules have no value in the real-world legal system at present. One day perhaps an AA, that is, a piece of code that runs without human intervention, commissioned by a law enforcement agency or regulator, will contain rules and regulations that could be embedded in a DAO for the purpose of ensuring its integrity from a legalistic and compliance perspective. The fact that DAOs are purely decentralized entities enables them to run in any jurisdiction. Thus, they raise a big question as to how the current legal system could be applied to such a varied mix of jurisdictions and geographies. Decentralized Autonomous Corporations. Decentralized Autonomous Corporations, DACs, are similar to DAOs in concept. Though considered to be a subset of them, the definitions of DACs and DAOs may sometimes overlap, but the general distinction is that DAOs are usually considered to be non-profit, whereas DACs can earn a profit via shares offered to the participants and to whom they can pay dividends. DACs can run a business automatically without human intervention based on the logic programmed into them. Decentralized Autonomous Societies. Decentralized Autonomous Societies, DASs, are a concept whereby an entire society can function on a blockchain with the help of multiple complex smart contracts and a combination of DAOs and decentralized applications, DApps, running autonomously. This model does not necessarily translate to a free-for-all approach, nor is it based on an entirely libertarian ideology. Instead, many services that a government commonly offers can be delivered via blockchains, such as government identity card systems, passports, and records of deeds, marriages, and births. Another theory is that if a government is corrupt and central systems do not provide the levels of trust that a society needs, then that society can start its own virtual one on a blockchain that is driven by decentralized consensus and transparency. This concept might look like a libertarian's or cyberpunk's dream, but it is entirely possible on a blockchain. Decentralized applications. All the ideas mentioned up to this point come under the broad umbrella or decentralized applications, abbreviated to DApps. DAOs, DACs, and DOs are DApps that run on top of a blockchain in a peer-to-peer network. They represent the latest advancement in decentralization technology. DApps at a fundamental level are software programs that execute using either of the following methods. They are categorized as Type 1, Type 2, or Type 3 DApps. 1. Type 1 run on their own dedicated blockchain, for example, standard smart contract-based DApps running on Ethereum. If required, they make use of a native token, for example, ETH on Ethereum blockchain. For example, Ethlance is a DApp that makes use of ETH to provide a job market. More information about Ethlance can be found at ethlance.com. 2. Type 2. Use an existing established blockchain, that is, make use of Type 1 blockchain and bear custom protocols and tokens. For example, smart contract-based tokenization, DApps running Ethereum blockchain. An example is DAI, which is built on top of Ethereum blockchain, but contains its own stablecoins and mechanism of distribution and control. Another example is Golem, which has its own token GNT and a transaction framework built on top of Ethereum blockchain to provide a decentralized marketplace for computing power where users share their computing power with each other in a peer-to-peer network. A peer example of Type 2 dApps is on the Omni network, which is a software layer built on top of Bitcoin to support trading of custom digital assets and digital currencies. More information on the Omni network can be found at omnilayer.org. More information on the Golem network is available at golem.network. More information on DAI is available at makerdao.com/en/en. 3. Type 3. Use the protocols of Type 2, the apps. For example, the Safe network uses the Omni network protocol. More information on the Safe network can be found at safenetwork.tech. Another example to understand the difference between different types of the apps is the USDT tokens, tethers. The original USDT uses the Omni layer, a Type 2 dApp, on top of the Bitcoin network. USDT can be considered a Type 3 dApp where the Omni layer protocol, a Type 2 dApp, is used, which is itself built on Bitcoin, a Type 1 dApp. Also, from an Ethereum point of view, USDT can also be considered a Type 3 dApp, in that it makes use of the Type 1 dApp Ethereum blockchain, using the ERC-20 standard, which was built to operate on Ethereum. More information can be found about Tether at tether.to. In the last few years, the expression dApp has been increasingly used to refer to any end-to-end decentralized blockchain application, including a user interface, usually a web interface, smart contracts, and the host blockchain. The clear distinction between different types of the apps is now not commonly referred to, but it does exist. Often the apps are now considered just as apps, blockchain apps, running on a blockchain such as Ethereum, Tezos, Neo, or EOS without any particular reference to their type. There are thousands of different dApps running on various platforms, blockchains now. There are various categories of these dApps covering media, social, finance, games, insurance, and health. There are various decentralized platforms or blockchains running such as Ethereum, EOS, Neo, Loom, and Steam. The highest number of dApps currently is on Ethereum. Requirements of a dApp. For an application to be considered decentralized, it must meet the following criteria. This definition was provided in a white paper by Johnston et al. In 2015. The General Theory of Decentralized Applications, dApps. 1. The dApp should be fully open source and autonomous, and no single entity should be in control of a majority of its tokens. All changes to the application must be consensus-driven, based on the feedback given by the community. 2. Data and records of operations of the application must be cryptographically secured and stored on a public, decentralized blockchain to avoid any central points of failure. 3. A cryptographic token must be used by the application to provide access for and incentivize those who contribute value to the applications. For example, miners in Bitcoin. 4. The tokens, if applicable, must be generated by the decentralized application using consensus and an applicable cryptographic algorithm. This generation of tokens acts as a proof of the value to contributors, for example, miners. Generally, the apps now provide all sorts of different services, including but not limited to financial applications, gaming, social media, and health. Operations of a dApp. Establishment of consensus by a dApp can be achieved using consensus algorithms such as POW and proof of stake, POS. So far, only POW has been found to be incredibly resistant to attacks, as is evident from the success of and trust people have put in the Bitcoin network. Furthermore, a dApp can distribute tokens, coins, via mining, fundraising, and development. Design of a dApp. A dApp, pronounced dApp, or now more commonly rhyming with app, is a software application that runs on a decentralized network, such as a distributed ledger. They have recently become very popular due to the development of various decentralized platforms, such as Ethereum, EOS, and Tezos. Traditional apps commonly consist of a user interface and usually a web server or an application server and a backend database. This is a common client-server architecture. This is visualized in the following diagram. A DApp, on the other hand, has a blockchain as a backend and can be visualized as depicted in the following diagram. The key element that plays a vital role in the creation of a DApp is a smart contract that runs on the blockchain and has business logic embedded within it. Note that the front end in either a DApp or app architecture can either be a thick client, a mobile app, or a web front end, a web user interface. However, it is usually a web front end commonly written using a JavaScript framework such as React or Angular. The following comparison table highlights the key properties of and differences between these different types of decentralized entities. Having covered the main concepts of DApps, it will be useful to explore some specific examples. DApps examples. Examples of some DApps are provided here. KYC chain. This application provides the facility to manage Know Your Customer (KYC) data securely and conveniently based on smart contracts. OpenBazaar. This is a decentralized peer-to-peer network that enables commercial activities directly between sellers and buyers instead of relying on a central party, such as eBay or Amazon. It should be noted that this system is not built on top of a blockchain. Instead, distributed hash tables are used in a peer-to-peer network to enable direct communication and data sharing among peers. It makes use of Bitcoin and various other cryptocurrencies as a payment method. More information regarding OpenBazaar is available at openbazaar.org. Lazuz. This is the decentralized equivalent of Uber. It allows peer-to-peer ride-sharing and users to be incentivized by proof of movement, and they can earn Zuz coins. More information on Lazuz is available at lazuz.org. Many other DApps have been built on the Ethereum blockchain and are showcased at dapps.ethercast.com. Now that we have covered the pertinent technology, DApps, and relevant examples, let's now look at what platforms can be used to build and host DApps. Platforms for decentralization. Today there are many platforms available for decentralization. In fact, the fundamental feature of blockchain networks is to provide decentralization. Therefore, any blockchain network such as Bitcoin, Ethereum, Hyperledger Fabric, or Quorum can be used to provide a decentralization service. Many organizations around the world have introduced platforms that promise to make distributed application development easy, accessible, and secure. Some of these platforms are described as follows. Ethereum. Ethereum tops the list as being the first blockchain to introduce a Turing-complete language and the concept of a virtual machine. This is in stark contrast to the limited scripting language in Bitcoin and many other cryptocurrencies. With the availability of its Turing-complete language, Solidity endless possibilities have opened for the development of decentralized applications. This blockchain was first proposed in 2013 by Vitalik Buterin, and it provides a public blockchain to develop smart contracts and decentralized applications. Currency tokens on Ethereum are called Ethers. MadeSafe. This is a project for the decentralized internet introduced in 2006. This is not a blockchain, but a decentralized and autonomous network. MadeSafe provides a safe, secure access for everyone network that is made up of unused computing resources, such as storage, processing power, and the data connections of its users. The files on the network are divided into small chunks of data, which are encrypted and distributed randomly throughout the network. This data can only be retrieved by its respective owner. One key innovation of MadeSafe is that duplicate files are automatically rejected on the network, which helps reduce the need for additional computing resources needed to manage the load. It uses SafeCoin as a token to incentivize its contributors. More information on MadeSafe is available at madesafe.net. Lisk. Lisk is a blockchain application development and cryptocurrency platform. It allows developers to use JavaScript to build decentralized applications and host them in their respective sidechains. Lisk uses the delegated proof of stake (DPoS) mechanism for consensus, whereby 101 nodes can be elected to secure the network and propose blocks. It uses the Node.js and JavaScript backend, while the front end allows the use of standard technologies such as CSS3, HTML5, and JavaScript. Lisk uses LSK coin as a currency on the blockchain. Another derivative of Lisk is Rise, which is a Lisk-based DApp and digital currency platform. It offers greater focus on the security of the system. EOS. This is a blockchain protocol launched in January 2018 with its own cryptocurrency called EOS. EOS raised an incredible $4 billion in 2018 through its initial coin offering, ICO. The key purpose behind EOS, as stated by its founders, to build a decentralized operating system. Its throughput is significantly higher, approximately 3,996 transactions per second, TPS, than other common blockchain platforms, such as Bitcoin approximately 7 TPS, and Ethereum approximately 15 TPS. A practical introduction to these platforms and some others are provided in this book's bonus content pages, which can be found here, static.pack.t-cdn.com/downloads/altcoins_ethereum_projects_and_more bonus_content.pdf. Due to fast-paced innovation and the natural evolution of these platforms and blockchain in general, many innovative trends have emerged, which we explore in the next section. Innovative trends. With the growth of blockchain, several ideas have emerged that make use of the decentralized property of blockchain to provide more user-centric and fully decentralized services. Some of the key ideas in this space are decentralized web, decentralized identity, and decentralized finance. We will explore these ideas one by one as follows. Decentralized web. Decentralized web is a term that's used to describe a vision of the web where no central authority or set of authorities will be in control. The original intention of the Internet was indeed decentralized, and the development of open protocols such as HTTP, SMTP, and DNS meant that any individual could use these protocols freely and immediately become part of the Internet. This is still true, however, with the emergence of a layer above these protocols called the web layer, introduced a more service-oriented infrastructure, which inevitably led to large profit-seeking companies taking over. This is evident from the rise of Facebook, Google, Twitter, and Amazon, which of course provide excellent user services but at the cost of a more controlled, centralized, and closed system. Once intended and developed as decentralized, open and free protocols are now being dominated by powerful commercial entities around the world, which has resulted in major concerns about privacy and data protection. These types of business models do work well and are quite popular due to the high level of standardization and services provided, but they pose a threat to privacy and decentralization due to the dominance of only a handful of entities on the entire Internet. With blockchain, it is envisioned that this situation will change as it will allow development of the decentralized Internet, or the decentralized web, or Web3 for short, which was the original intention of the Internet. We can review the evolution of the web over the last few decades by dividing the major developments into three key stages: Web 1, Web 2, and Web 3. Web 1. This is the original World Wide Web, which was developed in 1989. This was the era when static web pages were hosted on servers and usually only allowed read actions from a user's point of view. Web 3. This is the era when more service-oriented and web-hosted applications started to emerge. E-commerce websites, social networking, social media, blogs, multimedia sharing, mashups, and web applications are the main features of this period. The current web is Web 2, and even though we have a richer and more interactive Internet, all of these services are still centralized. Web 2 has generated massive economic value and provides services that are essential for day-to-day business, personal use, social interactions, and almost every walk of life, but privacy concerns, the need for trusted third parties, and data breaches are genuine issues that need to be addressed. Common examples of centralized Web 2 services include Twitter, Facebook, Google Docs, and email services such as Gmail and Hotmail. Web 3. This is the vision of the decentralized Internet, or web, that will revolutionize the way we use the Internet today.
This is the era that will be fully user-centric and decentralized without any single authority or a large organization or internet company in control. Some examples of Web3 are as follows. Steemit. This is a social media platform based on the Steem blockchain and Steem cryptocurrency. This cryptocurrency is awarded to contributors for the content they have shared, and the more votes they get, the more tokens they earn. More information is available at steemit.com. Status. This is a decentralized, multi-purpose communication platform providing secure and private communication. More information is available at status.im. IPFS. This is a peer-to-peer hypermedia storage protocol that allows storage and sharing of data in a decentralized fashion across peer-to-peer network. More information is available at ipfs.io. Other fast-growing trends include decentralized identity and decentralized finance, which we introduce next. Decentralized identity. Another trend that has gained massive popularity recently is decentralized identity. Identity is a sensitive and difficult problem to solve. Currently, due to the dominance of large internet companies and other similar organizations, the identity of a user is not in control of the identity holder, and this often leads to privacy issues. Decentralized identity gives control of identity credentials back to identity holders and enables them to control when and how they share their credentials, and with whom. A prime example of such an initiative is that Microsoft has built a decentralized identity network called Identity Overlay Network, ION, on top of Bitcoin blockchain. This infrastructure is based on work done for decentralized identity at W3C and the Decentralized Identity Foundation. Similar initiatives have also been taken by IBM and other organizations around the world. More information regarding ION is available at github.com/decentralized-identity/ION. Information regarding the Decentralized Identity Foundation is available at identity.foundation. Information regarding decentralized identifiers, DIDs, is available at w3.org/tr/did-core/#DFN-decentralized-identifiers. Decentralized finance, DeFi. DeFi could be the killer app of the decentralized revolution that everyone has been waiting for. Traditionally, finance is a business that is almost impossible to do without the involvement of a trusted third party. It can be either a bank or some other financial firm. Consumers have to trust a central authority to do business on their behalf and provide the services. There are rules, policies, procedures, and strict regulations that govern this ecosystem. This control and management is of paramount importance for the integrity of the entire financial ecosystem. Still, since there is always a central party that is required in every single transaction consumers do, this approach has some disadvantages. Some main disadvantages are listed as follows. Access barrier. Access to financial services and banking requires a rigorous onboarding process involving KYC and other relevant checks and procedures. Even though this is extremely important for the integrity of the existing financial system, it can become a barrier at times for millions of unbanked people all around the world, especially in third world countries. High cost. Financial services can be costly in some scenarios, especially investment-related activities, and could be seen as a barrier toward entering the financial services industry. Transparency issues. There are concerns around transparency and trust due to the proprietary nature of the financial industry. Silhouette. Most current financial industry solutions are proprietary and are owned by their respective organization. This results in interoperability issues where systems from one organization are unable to talk with another. DeFi comes with a number of advantages, such as inclusion, easy access, and cheaper services. However, it has its own challenges. These drawbacks must be addressed for further adoption of this novel paradigm of financial services. Underdeveloped ecosystem. This ecosystem is still developing and requires more effort to improve usability and adoption. Too technical. As some users may find understanding and handling all financial transactions and jargon a bit daunting, adopting a DeFi platform may take some time and educational effort. Lack of regulation. This is a genuine and clear concern because without the existence of any regulatory framework, this ecosystem can be used for illegal activities. Moreover, trusting the code alone instead of traditional paper contracts with established financial institutions is seen as a major problem, especially by consumers who are used to traditional financial systems. Human error. On a blockchain, human errors can result in serious implications, especially on DeFi systems or cryptocurrency blockchains. Any human negligence can result in serious implications, such as financial loss. Moreover, due to the lack of regulation relative to traditional finance, such an issue can have an even greater detrimental impact. Note that human error can occur in any system, and blockchain is not immune either. Generally, a blockchain is regarded as a tamper-proof, all-secure, and decentralized platform due to its security promises. However, this perception can give the wrong impression. For example, for a general user who perhaps doesn't understand the underlying technology and associated limitations, human errors may go unnoticed and users may innocently accept everything as accurate, due to blockchain being the source of ultimate truth. Therefore, human errors must be minimized as much as possible. It is essential to perform validation checks in the apps, especially on user interfaces where users might be entering different types of data. For example, it should be ensured at the user interface level that account details, addresses are correct, at least the format of the address, to reduce the possibility of loss of funds. Not much can be done afterward. For example, if funds are set to the wrong address. Other types of human errors might include, but are not limited to, sending funds to incompatible wallets, not appropriately protecting account information, and not understanding how to use the app's front ends correctly. DeFi applications are used in a broad spectrum of use cases, including loans, decentralized exchanges, DEXs, derivatives, payments, insurance, and assets. All of these use cases have one thing in common, which is that there is no central authority in control, and participants, that is, users on DeFi platforms, conduct business directly with each other without the involvement of any intermediaries. This may sound like a utopian fantasy, but the DeFi revolution is happening right now and there is almost $5 billion at the time of writing of value locked in the DeFi system. This large amount of locked value is a clear indication that the usage of DeFi applications is quite significant and is expected to only increase. You can find the latest rankings and analytics of the DeFi protocol on this excellent website, DeFiPulse.com. Use cases of all these developments and further details will be introduced later in Chapter 19, Blockchain Outside of Currencies. In this section, we discuss some innovative trends, including decentralized web and DeFi. However, these are not the only applications of blockchain technology. Some other emerging trends include the convergence of different technologies with blockchain, which can open new vistas for further innovation such as artificial intelligence and the Internet of Things, IoT. We will cover these topics in Chapter 22, Current Landscape and What's Next. Summary. This chapter introduced the concept of decentralization, which is the core service offered by blockchain technology. Although the concept of decentralization is not new, it has gained renewed significance in the world of blockchain. As such, various applications based on a decentralized architecture have recently been introduced. The chapter began with an introduction to the concept of decentralization. Next, decentralization from the blockchain perspective was discussed. Moreover, ideas relating to the different layers of decentralization in the blockchain ecosystem were introduced. Several new concepts and terms have emerged with the advent of blockchain technology and decentralization from the blockchain perspective, including DAOs, DACs, and DApps. Finally, some innovative trends and examples of DApps were presented. In the next chapter, fundamental concepts necessary to understanding the blockchain ecosystem will be presented. Principally cryptography, which provides a crucial foundation for blockchain technology.
Chapter 3. Symmetric Cryptography. In this chapter, you will be introduced to the concepts, theory, and practical aspects of symmetric cryptography. More focus will be given to the elements that are specifically relevant in the context of blockchain technology. This chapter will provide the concepts required to understand the material covered in later chapters. You will also be introduced to applications of cryptographic algorithms so that you can gain hands-on experience in the practical implementation of cryptographic functions. For this, the OpenSSL command line tool is used. Before starting with the theoretical foundations, the installation of OpenSSL is presented in the following section so that you can do some practical work as you read through the conceptual material. Working with the OpenSSL command line. On the Ubuntu Linux distribution, OpenSSL is usually already available. However, it can be installed using the following commands. $sudo apt-get install OpenSSL. Examples in this chapter have been developed using OpenSSL version 1.0.2t. It is available at https://packages.ubuntu.com/xenial/openssl. You are encouraged to use this specific version, as all examples in the chapter have been developed and tested with it. The OpenSSL version can be checked using the following command. $OpenSSL version. If you see the following output, OpenSSL 1.0.2t 10 September 2019, then you are all set to run the examples provided in this chapter. If you are running a version other than 1.0.2t, the examples may still work, but that is not guaranteed, especially as older versions lack the features used in the examples and newer versions may not be backward compatible with version 1.0.2t. In the sections that follow, the theoretical foundations of cryptography are first discussed, and then a series of relevant practical experiments will be presented. Introduction. Cryptography is the science of making information secure in the presence of adversaries. It does so under the assumption that limitless resources are available to adversaries. Ciphers are algorithms used to encrypt or decrypt data so that if intercepted by an adversary, the data is meaningless to them without decryption, which requires a secret key. Cryptography is primarily used to provide a confidentiality service. On its own, it cannot be considered a complete solution. Rather, it serves as a crucial building block within a more extensive security system to address a security problem. For example, securing a blockchain ecosystem requires many different cryptographic primitives, such as hash functions, symmetric key cryptography, digital signatures, and public key cryptography. In addition to a confidentiality service, cryptography also provides other security services such as integrity, authentication, entity authentication, and data origin authentication, and non-repudiation. Additionally, accountability is also provided, which is a requirement in many security systems. Cryptography. A generic cryptographic model is shown in the following diagram. In the preceding diagram, P, E, C, and D represent plaintext encryption, ciphertext, and decryption, respectively. This model utilizes concepts such as entities, senders, receivers, adversaries, keys, and channels. These concepts are explained as follows. Entity. Either a person or system that sends, receives, or performs operations on data. Sender. This is an entity that transmits the data. Receiver. This is an entity that takes delivery of the data. Adversary. This is an entity that tries to circumvent the security service. Key. A key is data that is used to encrypt the plaintext and also to decrypt the ciphertext. Channel. A channel provides a medium of communication between entities. We mentioned the fact that cryptography provides various services. In the following sections, we'll discuss these services in greater detail. Confidentiality. Confidentiality is the assurance that information is only available to authorized entities. Integrity. Integrity is the assurance that information is modifiable only by authorized entities. Authentication. Authentication provides assurance about the identity of an entity or the validity of a message. There are two types of authentication mechanisms, namely entity authentication and data origin authentication, which are discussed in the following sections. Entity authentication. Entity authentication is the assurance that an entity is currently involved and active in a communication session. Traditionally, users are issued a username and password that is used to gain access to the various platforms with which they are working. This practice is known as a single-factor authentication, as there is only one factor involved, namely something you know, that is, the password and username. This type of authentication is not very secure for a variety of reasons. For example, password leakage. Therefore, additional factors are now commonly used to provide better security. The use of additional techniques for user identification is known as multi-factor authentication, or two-factor authentication if only two methods are used. Various authentication methods are described here. The first method uses something you have, such as a hardware token or a smart card. In this case, a user can use a hardware token in addition to login credentials to gain access to a system. This mechanism protects the user by requiring two factors of authentication. A user who has access to the hardware token and knows the login credentials will be able to access the system. Both factors should be available to gain access to the system, thus making this method a two-factor authentication mechanism. If the hardware token is inaccessible, for example, lost or stolen, or the login password is forgotten by the user, access to the system will be denied. The hardware token won't be of any use on its own unless the login password, something you know, is also known and used in conjunction with the hardware token. The second method uses something you are, which uses biometric features to identify the user. With this method, a user's fingerprint, retina, iris, or hand geometry is used to provide an additional factor or authentication. This way, it can be ensured that the user was indeed present during the authentication process, as biometric features are unique to every individual. However, careful implementation is required to guarantee a high level of security, as some research has suggested that biometric systems can be circumvented under specific conditions. Also known as message authentication, data origin authentication is an assurance that the source of the information is indeed verified. Data origin authentication guarantees data integrity because, if a source is corroborated, then the data must not have been altered. Various methods such as message authentication codes, MACs, and digital signatures are most commonly used. These terms will be explained in detail later in the chapter. Non-repudiation. Non-repudiation is the assurance that an entity cannot deny a previous commitment or action by providing incontrovertible evidence. This is a security service that offers definitive proof that a particular activity has occurred. This property is essential in debatable situations whereby an entity has denied the actions performed. For example, the placement of an order on an e-commerce system. This service produces cryptographic evidence in electronic transactions so that in case of disputes, it can be used as confirmation of an action. Non-repudiation has been an active research area for many years. Disputes in electronic transactions are a common issue, and there is a need to address them to increase consumers' confidence levels in such services. The non-repudiation protocol usually runs in a communications network, and it is used to provide evidence that an action has been taken by an entity, originator or recipient, on the network. In this context, two communication models can be used to transfer messages from originator A to recipient B. A message is sent directly from originator A to recipient B, and a message is sent to a delivery agent from originator A, which then delivers the message to recipient B. The primary requirements of a non-repudiation protocol are fairness, effectiveness, and timeliness. In many scenarios, there are multiple participants involved in a transaction as opposed to only two parties. For example, in electronic trading systems, There can be many entities, including clearing agents, brokers, and traders who can be involved in a single transaction. In this case, two-party non-repudiation protocols are not appropriate. To address this problem, multi-party non-repudiation (MPNR) protocols have been developed. MPNR refers to non-repudiation protocols that run between multiple parties instead of the two traditional parties. An excellent text on MPNR is Onieva, J.A. and Zhao, J. 2008, Secure Multi-Party Non-Repudiation Protocols and Applications, Volume 43, Springer Science and Business Media. Accountability. Accountability is the assurance that actions affecting security can be traced back to the responsible party. This is usually provided by logging and audit mechanisms in systems where a detailed audit is required due to the nature of the business. For example, in electronic trading systems, detailed logs are vital to trace an entity's actions, such as when a trade is placed in an audit record with a date and timestamp, and the entity's identity is generated and saved in the log file. This log file can optionally be encrypted and be part of the database or a standalone ASC2 text log file on a system. In order to provide all of the services discussed in this section, different cryptographic primitives are used, which are presented in the next section. Cryptographic primitives. Cryptographic primitives are the basic building blocks of a security protocol or system. In the following section, you are introduced to cryptographic algorithms that are essential for building secure protocols and systems. A security protocol is a set of steps taken to achieve the required security goals by utilizing appropriate security mechanisms. Various types of security protocols are in use, such as authentication protocols, non-repudiation protocols, and key management protocols. The taxonomy of cryptographic primitives can be visualized as shown here. As shown in the preceding cryptographic primitive taxonomy diagram, cryptography is mainly divided into three categories: keyless primitives, symmetric key primitives or cryptography, and asymmetric key primitives or cryptography. Keyless primitives and symmetric cryptography are discussed further in the section, and we will cover asymmetric cryptography or public key cryptography in Chapter 4, Public Key Cryptography. Keyless primitives. In this section, we will introduce two keyless primitives, namely random numbers and hash functions. Random numbers. Randomness provides an indispensable element for the security of the cryptographic protocols. It is used for the generation of keys and in encryption algorithms. Private keys must be generated randomly so that they are unpredictable and not so easy to guess. Randomness ensures that operations of a cryptographic algorithm do not become predictable enough to allow cryptanalysts to predict the outputs and operations of the algorithm, which will make the algorithm insecure. It is quite a feat to generate suitable randomness with a high degree of uncertainty, but there are methods that ensure an adequate level of randomness is generated for use in cryptographic algorithms. There are two categories of source of randomness, namely random number generators (RNGs) and pseudo-random number generators (PRNGs). RNGs are software or hardware systems that make use of the randomness available in the real world, that is, the analog world, where uncertainty in the environment produces randomness. This can be temperature variations, thermal noises from various electronic components, or acoustic noise. This is called real randomness. Other sources are based on the fact that a running computer system generates some randomness from the running processes, such as keystrokes or disk movements. These types of sources of randomness are not very practical due to the difficulty of acquiring this data or not having enough entropy. Also, these sources are not always available and could be available only for a limited time. The measure of randomness is called entropy. PRNGs are deterministic functions that work on the principle of using a random initial value called a seed to produce a random-looking set of elements. PRNGs are commonly used to generate keys for encryption algorithms. A common example of a PRNG is the Blum-Blum-Shub, BBS. PRNGs are a better alternative to RNGs due to their reliability and deterministic nature. More information on BBS is available in the following original research paper, Blum L. Blum M. and Shub M. 1986, A Simple, Unpredictable, Pseudo-Random Number Generator, SIAM Journal on Computing, 15.2 pages 364 to 383. https://shub.ccny.edu/article/1986-a_undescore simple_unpredictable_pseudo-random_number_generator.pdf. With this, our discussion on random numbers is complete. This is a deep and vast subject, but we have covered enough to understand their need in cryptographic algorithms. In the next section, we will look at a category of keyless cryptographic primitives that are not used to encrypt data. Instead, they produce a fixed-length digest of the data that is provided as input. These constructions are called hash functions and play a very crucial role in the development of blockchain. Hash functions. Hash functions are used to create fixed-length digests or arbitrarily long input strings. Hash functions are keyless and they provide a data integrity service. They are usually built using iterated and dedicated hash functions construction techniques. Various families of hash functions are available, such as MD, SHA-1, SHA-2, SHA-3, RIPE-MD, and Whirlpool. Hash functions are commonly used for digital signatures and message authentication codes, such as HMACs. They have three security properties, namely pre-image resistance, second pre-image resistance, and collision resistance. These properties are explained later in this section. Hash functions are also typically used to provide data integrity services. These can be used both as one-way functions and to construct other cryptographic primitives such as MACs and digital signatures. Some applications use hash functions as a means for generating PRNGs. There are two practical and three security properties of hash functions that must be met depending on the level of integrity required. These properties are discussed next. Compression of arbitrary messages into fixed-length digest. This property relates to the fact that a hash function must be able to take an input text of any length and output a fixed-length compressed message. Hash functions produce a compressed output in various bit sizes, usually between 128 bits and 512 bits. Easy to compute. Hash functions are efficient and fast one-way functions. It is required that hash functions be very quick to compute regardless of the message size. The efficiency may decrease if the message is too big, but the function should still be fast enough for practical use. In the following section, the security properties of hash functions are discussed. Pre-image resistance. This property can be explained by using the simple equation h open parentheses x close parentheses equals y. Here h is the hash function, x is the input, and y is the hash. The first security property requires that y cannot be reverse computed to x. X is considered a pre-image of y, hence the name pre-image resistance. This is also called a one-way property. Second pre-image resistance. The second pre-image resistance property requires that given x and h, x, it is almost impossible to find any other message m where m exclamation point equals x, and hash of m equals hash of x or hm equals hx. This property is also known as weak collision resistance. Collision resistance. The collision resistance property requires that two different input messages should not hash to the same output. In other words, hx exclamation point equals hz. This property is also known as strong collision resistance. All these properties are shown in the following diagrams. Due to their very nature, hash functions will always have some collisions.
This is a situation where two different messages hash to the same output. However, they should be computationally impractical to find. A concept known as the avalanche effect is desirable in all cryptographic hash functions. The avalanche effect specifies that a small change, even a single character change in the input text, will result in an entirely different hash output. Hash functions are usually designed by following an iterated hash functions approach. With this method, the input message is compressed in multiple rounds on a block-by-block basis in order to produce the compressed output. A popular type of iterated hash function is the Merkle-Damgard construction. This construction is based on the idea of dividing the input data into equal block sizes and then feeding them through the compression functions in an iterative manner. The collision resistance of the property of compression functions ensures that the hash output is also collision resistant. Compression functions can be built using block ciphers. In addition to Merkle-Damgard, there are various other constructions of compression functions proposed by researchers, for example, Miyaguchi, Prinell, and Davies Mayer. Details of these schemes are available in the excellent book Katz J. Menezes, A. J. Van Oorschot, P.C. and Vanstone, S.A. 1996, Handbook of Applied Cryptography, CRC Press. Refer to Chapter 9 Hash Functions and Data Integrity, cacr.uwaterloo.ca/hac/about/chap9.pdf. Multiple categories of hash functions are introduced in the following section. Message Digest. Message Digest MD functions were prevalent in the early 1990s. MD4 and MD5 fall into this category. Both MD functions were found to be insecure and are not recommended for use anymore. MD5 is a 128-bit hash function that was commonly used for file integrity checks. Secure hash algorithms. The following list describes the most common secure hash algorithms. SHAs. SHA-0. This is a 160-bit function introduced by the U.S. National Institute of Standards and Technology, NIST, in 1993. SHA-1. SHA-1 was introduced in 1995 by NIST as a replacement for SHA-0. This is also a 160-bit hash function. SHA-1 is used commonly in SSL and TLS implementations. It should be noted that SHA-1 is now considered insecure, and it is being deprecated by certificate authorities. Its usage is discouraged in any new implementations. SHA-2. This category includes 4 functions defined by the number of bits of the hash: SHA-224, SHA-256, SHA-384, and SHA-512. SHA-3. This is the latest family of SHA functions. SHA-3-224, SHA-3-256, SHA-3-384, and SHA-3-512 are members of this family. SHA-3 is a NIST standardized version of CACAC. CACAC uses a new approach called sponge construction instead of the commonly used Merkle-Damgard transformation. RIPE-MD. RIPE-MD is the acronym for Race, Integrity, Primitives, Evaluation Message Digest. It is based on the design ideas used to build MD4. There are multiple versions of RIPE-MD, including 128-bit, 160-bit, 256-bit, and 320-bit. Whirlpool. This is based on a modified version of the Rijndael cipher known as W. It uses the Miyaguchi-Prinell compression function, which is a type of one-way function used for the compression of 2 fixed-length inputs into a single fixed-length output. It is a single-block length compression function. Hash functions have many practical applications ranging from simple file integrity checks and password storage to use in cryptographic protocols and algorithms. They are used in hash tables, distributed hash tables, Bloom filters, virus fingerprinting, peer-to-peer, P2P file sharing, and many other applications. Hash functions play a vital role in blockchain. The proof-of-work POW function in particular uses SHA-256 twice in order to verify the computational effort spent by miners. RIPE-MD160 is used to produce Bitcoin addresses. This will be discussed further in later chapters. In the next section, the design of the SHA algorithm is introduced. Design of Secure Hash Algorithms, SHA. In the following section, you will be introduced to the design of SHA-256 and SHA-3. Both of these are used in Bitcoin and Ethereum, respectively. Ethereum uses KAKAK, which is the original algorithm presented to NIST. Rather than NIST standard SHA-3, NIST, after some modifications, such as an increase in the number of rounds and simpler message padding, standardized KAKAK as SHA-3. Design of SHA-256. SHA-256 has an input message size limit of 2 to the 64th power minus 1 bits. The block size is 512 bits, and it has a word size of 32 bits. The output is a 256-bit digest. The compression function processes a 512-bit message block and a 256-bit intermediate hash value. There are two main components of this function: the compression function and a message schedule. The algorithm works as follows in 9 steps. Pre-processing. 1. Padding of the message is used to adjust the length of a block to 512 bits if it is smaller than the required block size of 512 bits. 2. Parsing the message into message blocks, which ensures that the message and its padding is divided into equal blocks of 512 bits. 3. Setting up the initial hash value, which consists of the 8 32-bit words contained by taking the first 32 bits of the fractional parts of the square roots of the first 8 prime numbers. These initial values are fixed and chosen to initialize the process. They provide a level of confidence that no backdoor exists in the algorithm. Hash computation. 4. Each message block is then processed in a sequence, and it requires 64 rounds to compute the full hash output. Each round uses slightly different constants to ensure that no 2 rounds are the same. 5. The message schedule is prepared. 6. 8 working variables are initialized. 7. The compression function runs 64 times. 8. The intermediate hash value is calculated. 9. Finally, after repeating steps 5 through 8 until all blocks, chunks of data, in the input message are processed, the output hash is produced by concatenating intermediate hash values. At a high level, SHA-256 can be visualized in the following diagram. As shown in the preceding diagram, SHA-256 is a Merkle-Damgard construction that takes the input message and divides it into equal blocks, chunks of data of 512 bits. Initial values or initial hash values, or the initialization vector, are composed of 8 32-bit words, 256 bits, that are fed into the compression function with the first message. Subsequent blocks are fed into the compression function until all blocks are processed, and finally the output hash is produced. The compression function of SHA-256 is shown in the following diagram. In the preceding diagram, A, B, C, D, E, F, G, and H are the registers for 8 working variables. Moj and ch functions are applied bitwise. Sigma 0 and Sigma 1 perform bitwise rotation. The round constants are W and K, which are added into the main loop compressor function of the hash function, which runs 64 times. The SHA-256 algorithm is used in Bitcoin's POW algorithm. With this, our introduction to SHA-256 is complete, and next we explore a newer class of hash functions known as the SHA-3 algorithm. Design of SHA-3, KAKAK. The structure of SHA-3 is very different from that of SHA-1 and SHA-2. The key idea behind SHA-3 is based on unkeyed permutations, as opposed to other typical hash function constructions that used keyed permutations. CACAC also does not make use of the Merkle-Damgard transformation that is commonly used to handle arbitrary length input messages in hash functions. A newer approach called sponge and squeeze construction is used in CACAC. It is a random permutation model. Different variants of SHA-3 have been standardized, such as SHA-3 224, SHA-3 256, SHA-3 384, SHA-3 512, Shake 128, and Shake 256. Shake 128 and Shake 256 are extendable output functions, XOFs, which allow the output to be extended to any desired length. The following diagram shows the sponge and squeeze model, which is the basis of SHA-3 or CACAC. Analogous to a sponge, the data, M input data, is first absorbed into the sponge after applying padding. It is then changed into a subset of permutation state using XOR, exclusive OR. And then the output is squeezed out of the sponge function that represents the transform state. The rate R is the input block size of the sponge function, while capacity C determines the security level. In the preceding diagram, state size B is calculated by adding bitrate R, and capacity bits C, R, and C can be any values as long as size of R plus C are 25, 50, 100, 200, 400, 800, or 1600. The state is a three-dimensional bit matrix. The initial state is set to 0. The data M is entered into the absorb phase block by block via XOR after applying padding. The following table shows the value of bitrate R, block size, and capacity C required to achieve the desired output hash size under the most efficient setting of R plus C equals 1600. The function f is a permutation function. It contains 5 transformation operations named theta, rho, pi, chi, and iota, described as follows. Theta, XOR bits in the state used for mixing. Rho, diffusion function performing rotation of bits. Pi, diffusion function. Chi, XOR each bit, bitewise combine. Iota, combination with round constants. The details of transformation operations is beyond the scope of this book. However, a high-level function of each transformation is described previously. The key idea is to apply these transformations to achieve the avalanche effect, which we introduced earlier in this chapter. These 5 operations combined form a round. In the SHA-3 standard, the number of rounds is 24 to achieve the desired level of security. We will see some applications and examples of constructions built using hash functions such as Merkle trees in Chapter 11, Ethereum 101. OpenSSL example of hash functions. The following command will produce a hash of 256 bits of hello messages using the SHA-256 algorithm. $echo -n, open apostrophe hello close apostrophe vertical pipe, OpenSSL DGST -SHA-256, open parentheses STDIN close parentheses equals 185 F8 DB 32271 FE 25F 561 A 6FC 938 B2 E2 64306 EC 304 EDA 518 007D1 764 8263 81969. Note that even a small change in the text, such as changing the case of the letter H, results in a big change in the output hash. This phenomenon is known as the avalanche effect, where if the input is slightly changed, the output changes drastically so that the cryptanalyst cannot make predictions on the input text by analyzing the output. Now we run the following command to see the avalanche effect in action. $echo -n open apostrophe hello, close apostrophe, vertical pipe, open SSL, DGST, hyphen SHA-256. Open parentheses STDIN, close parentheses, equals 2CF24 DBA5FB0A 30E 26E A3B 2AC 5B9E 29E 1B1 61 E5 C1 FA 7425 E7304 336293 8B 9824. Note that both outputs are completely different. Usually hash functions do not use a key. Nevertheless, if they are used with a key, then they can be used to create another cryptographic construct called Message Authentication Codes, MACs. We will see how MACs and HMACs work after we've introduced symmetric key cryptography, because these constructions make use of keys for encryption. Symmetric cryptography. Symmetric cryptography refers to a type of cryptography where the key that is used to encrypt the data is the same one that is used for decrypting the data. Thus, it is also known as shared key cryptography. The key must be established or agreed upon before the data exchange occurs between the communicating parties. This is the reason it is also called secret key cryptography. A key, more precisely a cryptographic key, is required for the encryption and decryption process and must be kept secret, hence it is called a secret key. There are many different types of keys depending upon the protocol. In symmetric key systems, only one key is required, which is shared between the sender and the receiver. It is used for both encryption and decryption, hence the name symmetric key cryptography or shared key cryptography, or just symmetric cryptography. Other types of keys are public keys and private keys, which are generated in pairs for public key cryptography or asymmetric cryptography. Public keys are used for encrypting the plaintext, whereas private keys are used for decryption and are expected to be kept secret by the receiver. We will discuss asymmetric cryptography in the next chapter, Chapter 4, Public Key Cryptography. Keys can also be ephemeral, temporary, or static. Ephemeral keys are intended to be used only for a short period of time, such as in a single session between the participants, whereas static keys are intended for long-term usage. Another type of key is called the master key, which is used for the protection, encryption, decryption, and generation of other keys. There are different methods to generate keys. These methods are listed as follows. 1. Random, where a random number generator is used to generate a random set of bytes that can be used as a key. 2. Key derivation based, where a single key or multiple keys are derived from a password. A key derivation function, KDF, is used for this purpose, taking the password as input and converting that into a key. Commonly used key derivation functions are password-based key derivation function 1, PBKDF1, PBKDF2, Argon2, and script. More information about PBKDFs can be found at tools.ietf.org/html/RFC8018. 3. Using a key agreement protocol, two or more participants run a protocol that produces a key, and that key is then shared between participants. In key agreement schemes, all participants contribute equally in the effort to generate the shared secret key. The most commonly used key agreement protocol is the Diffie-Hellman key exchange protocol. KDFs are used in Ethereum wallets, key store files, to generate an AES symmetric key that is used to encrypt the wallets. The KDF function used in Ethereum wallets is script. We will explain all this in great detail in Chapter 11, Ethereum 101. 4. In encryption schemes, there are also some random numbers that play a vital role in the operation of the encryption process. These concepts are presented as follows. The nonce. This is a number that can be used only once in a cryptographic protocol. It must not be reused. Nonces can be generated from a large pool of random numbers, or they can also be sequential. The most common use of nonces is to prevent replay attacks in cryptographic protocols. The initial value or initialization vector, IV, is a random number which is basically a nonce, but it must be chosen in an unpredictable manner. This means that it cannot be sequential. IVs are used extensively in encryption algorithms to provide increased security. The salt. Salt is a cryptographically strong random value that is typically used in hash functions to provide defense against dictionary or rainbow attacks. Using dictionary attacks, hashing-based password schemes can be broken by trying hashes of millions of words from a dictionary in a brute force manner and matching it with the hash password. If a salt is used, then a dictionary attack becomes difficult to run because a random salt makes each password unique. And secondly, the attacker will then have to run a separate dictionary attack for random salts, which is quite unfeasible. Now that we've introduced symmetric cryptography, we're ready to take a look at MACs and HMACs. Message Authentication Codes, MACs. Message Authentication Codes, MACs, are sometimes called keyed hash functions, and they can be used to provide message integrity and authentication. More specifically, they are used to provide data origin authentication. These are symmetric cryptographic primitives that use a shared key between the sender and the receiver. MACs can be constructed using block ciphers or hash functions. Hash-based MACs, HMACs. Similar to the hash function, hash-based MACs, HMACs, produce a fixed-length output and take an arbitrarily long message as the input. In this scheme, the sender signs a message using the MAC and the receiver verifies it using the shared key. The key is hashed with the message using either of the two methods known as secret prefix or secret suffix. With the secret prefix method, the key is concatenated with the message. That is, the key comes first and the message comes afterward, whereas with the secret suffix method, the key comes after the message, as shown in the following equations. Secret prefix: M equals MACK open parentheses X close parentheses equals H open parentheses K vertical pipe X close parentheses. Secret suffix: M equals MACK open parentheses X close parentheses equals H open parentheses X vertical pipe K close parentheses. There are pros and cons to both methods. Some attacks on both schemes have occurred. There are HMAC construction schemes that use various techniques, such as IPAD, inner padding, and OPAD, outer padding, that have been proposed by cryptographic researchers. These are considered secure, with some assumptions. There are various powerful applications of hash functions used in peer-to-peer networks and blockchain technologies, such as Merkle trees, Patricia trees, and distributed hash tables. There are two types of symmetric ciphers, steam ciphers and block ciphers. Data Encryption Standard DES and Advanced Encryption Standard AES are typical examples of block ciphers, whereas RC4 and A5 are commonly used stream ciphers. Stream ciphers. Stream ciphers are encryption algorithms that apply encryption algorithms on a bit-by-bit basis, 1 bit at a time, to plain text using a key stream. There are two types of stream ciphers: synchronous stream ciphers and asynchronous stream ciphers. Synchronous stream ciphers are those where the key stream is dependent only on the key. Asynchronous stream ciphers have a key stream that is also dependent on the encrypted data. In stream ciphers, encryption and decryption are the same function because they are simple modulo 2 additions or XOR operations. The fundamental requirement in stream ciphers is the security and randomness of key streams. Various techniques ranging from PRNGs to true hardware RNGs have been developed to generate random numbers, and it is vital that all key generators be cryptographically secure. Block ciphers. Block ciphers are encryption algorithms that break up the text to be encrypted, plain text, into blocks of a fixed length and apply the encryption block by block. Block ciphers are generally built using a design strategy known as a facial cipher. Recent block ciphers such as AES, Rijndael have been built using a combination of substitution and permutation called a substitution permutation network, SPN. Facial ciphers are based on the facial network, which is a structure developed by Horst Feistel. This structure is based on the idea of combining multiple rounds of repeated operations to achieve desirable cryptographic properties known as confusion and diffusion. Feistel networks operate by dividing data into two blocks, left and right, and processing these blocks via keyed round functions in iterations to provide sufficient pseudo-random permutations. Confusion adds complexity to the relationship between the encrypted text and plain text. This is achieved by substitution. In practice, A in plain text is replaced by X in encrypted text. In modern cryptographic algorithms, substitution is performed using lookup tables called S-boxes. The diffusion property spreads the plain text statistically over the encrypted data. This ensures that even if a single bit is changed in the input text, it results in changing at least half, on average, of the bits in the cipher text. Confusion is required to make finding the encryption key very difficult, even if many encrypted and decrypted data pairs are created using the same key. In practice, this is achieved by transposition or permutation. A key advantage of using facial ciphers is that encryption and decryption operations are almost identical and only require a reversal of the encryption process to achieve decryption. DES is a prime example of facial-based ciphers. Various modes of operation for block ciphers are electronic codebook, ECB, cipher block, chaining, CBC, output feedback, OFB mode, and counter, CTR mode. These modes are used to specify the way in which an encryption function is applied to the plain text. Some of these modes of block cipher encryption are introduced here. Block encryption mode. In block encryption mode, the plain text is divided into blocks of fixed length depending on the type of cipher used. Then the encryption function is applied to each block. The most common block encryption modes are briefly discussed in the following sections. Electronic codebook. Electronic codebook, ECB, is a basic mode of operation in which the encrypted data is produced as a result of applying the encryption algorithm to each block of plain text, one by one. This is the most straightforward mode, but it should not be used in practice as it is insecure and can reveal information. The preceding diagram shows that we have plain text P provided as an input to the block cipher encryption function along with a key, and ciphertext C is produced as output. Cipher block chaining. In cipher block chaining CBC mode, each block of plain text is XOR'd with the previously encrypted block. CBC mode uses the IV to encrypt the first block. It is recommended that the IV be randomly chosen. Counter mode. The counter mode effectively uses a block cipher as a stream cipher. In this case, a unique nonce is supplied that is concatenated with the counter value to produce a key stream. CTR mode, as shown in the preceding diagram, works by utilizing a nonce, N, and a counter C, that feed into the block cipher encryption function. The block cipher encryption function takes the secret key as input and produces a key stream, a stream of pseudo-random or random characters, which when XOR'd with the plaintext P produces the ciphertext C. So far we have discussed modes that are used to produce ciphertext, encrypted data. However, there are other modes that can be used for different purposes. We discuss some of these in the following section. Keystream generation mode. In keystream generation mode, the encryption function generates a keystream that is used in stream ciphers. Specifically, the keystream is usually XOR'd with the plaintext stream to produce encrypted text. Message authentication mode. In message authentication mode, a message authentication code, MAC, is produced from an encryption function. A MAC is a cryptographic checksum that provides an integrity service. The most common method to generate a MAC using block ciphers is CBC-MAC, where a part of the last block of the chain is used as a MAC. In other words, block ciphers are used in the cipher blockchaining mode, CBC mode, to generate a MAC. A MAC can be used to check if a message has been modified by an unauthorized entity. This can be achieved by encrypting the message with a key using the MAC function. The resulting message and the MAC of the message, once received by the receiver, are checked by encrypting the message received again with the key and comparing it with the MAC received from the sender. If they both match, then it means that the message has not been modified by some unauthorized entity, thus an integrity service is provided. If they don't match, then it means that the message has been altered by some unauthorized entity during transmission. Any block cipher, for example AES in CBC mode, can be used to generate a MAC. The MAC of the message is, in fact, the output of the last round of the CBC operation. The length of the MAC output is the same as the block length of the cipher used to generate the MAC. It should also be noted that MACs work like digital signatures. However, they cannot provide a non-repudiation service due to their symmetric nature. Cryptographic hash mode. Hash functions are primarily used to compress a message to a fixed-length digest. In cryptographic hash mode, block ciphers are used as a compression function to produce a hash of plain text. There are also other modes, such as cipher feedback, CFB mode, Galois counter, GCM mode, and output feedback, OFB mode, which are also used in various scenarios. Discussion of all these different modes is beyond the scope of this book. Interested readers may refer to any standard textbook on cryptography for further details. With this, we have now concluded the introduction to block ciphers. We now introduce some concepts that are relevant to cryptography and are extensively used in many applications. The primitives introduced next are also used in blockchain. In the following section, we will introduce the design and mechanism of a currently market-dominant block cipher known as AES. Before discussing AES, let's review some history about DES that led to the development of the new AES standard, Data Encryption Standard, DES. DES was introduced by NIST as a standard algorithm for encryption, and it was in widespread use during the 1980s and 1990s. However, it did not prove to be very resistant to brute force attacks due to advances in technology and cryptography research. In July 1998, for example, the Electronic Frontier Foundation, EFF, broke DES using a special purpose machine called EFF DES Cracker, or Deep Crack. DES uses a key of only 56 bits, which raised some concerns. This problem was addressed with the introduction of Triple DES, 3DES, which proposed the use of a 168-bit key by means of 3 56-bit keys and the same number of executions of the DES algorithm, thus making brute force attacks almost impossible. However, other limitations such as low performance and 64-bit block size were not desirable. Advanced Encryption Standard, AES. In 2001, after an open competition, an encryption algorithm named Rigendial, invented by cryptographers Joanne Damon and Vincent Bridgman, was standardized as AES with minor modifications by NIST. So far, no attack has been found against AES that is more effective than the brute force method. The original version of Rigendial permits different key and block sizes of 128 bits, 192 bits, and 256 bits. In the AES standard, however, only a 128-bit block size is allowed. However, key sizes of 128 bits, 192 bits, and 256 bits are permissible. How AES works. During AES algorithm processing, a 4x4 array of bytes, known as the state, is modified using multiple rounds. Full encryption requires 10 to 14 rounds, depending on the size of the key. The following table shows the key sizes and the required number of rounds. Once the state is initialized with the input to the cipher, the following 4 operations are performed sequentially, step by step, to encrypt the input. 1. Add round key. In this step, the state array is XOR'd with a subkey, which is derived from the master key. 2. Subbytes. This is the substitution step where a lookup table, SBox, is used to replace all bytes of the state array. 3. Shift rows. This step is used to shift each row to the left, except for the first one in the state array in a cyclic and incremental manner. 4. Mix columns. Finally, all bytes are mixed in a linear fashion, linear transformation, column-wise. This is one round of AES. In the final round, either the 10th, 12th, or 14th round, depending on the key size, stage 4 is replaced with add round key to ensure that the first 3 steps cannot be simply reversed, as shown in the following diagram. Various cryptocurrency wallets use AES encryption to encrypt locally stored data. Bitcoin wallets use AES 256 in CBC mode to encrypt the private keys. In Ethereum wallets, AES 128 CTR is used, that is, AES 128-bit encounter mode is used to encrypt the private key. Peers in Ethereum also use AES encounter mode, AES CTR, to encrypt their peer-to-peer P2P communication. An OpenSSL example of how to encrypt and decrypt using AES. We can use the OpenSSL command line tool to perform encryption and decryption operations. An example is given here. First, we create a plain text file to be encrypted. $echo data to encrypt ~message.txt. Now the file is created, we can run the OpenSSL tool with appropriate parameters to encrypt the file message.txt using 256-bit AES in CBC mode. $OpenSSL ENC-AES-256-CBC-in message.txt-out message.bin. Enter AES-256-CBC encryption password, verifying-enter AES-256-CBC encryption password, . Once the operation completes, it will produce a message.bin file containing the encrypted data from the message.txt file. We can view this file, which shows encrypted contents of the message.txt file. $cat message.bin salted_w s_y h tilde ? Note that message.bin is a binary file. Sometimes it is desirable to encode this binary file in a text format for compatibility, interoperability reasons. A common text encoding format is base64. The following commands can be used to create a base64 encoded message. $OpenSSL ENC-base64-in message.bin-out message.b64. $cat message.b64 U2FSD GBKX19 3UB YICW Z7J1AT plus 4L plus FJ8 /UZE DATJE equals. In order to encrypt an AES encrypted file, the following commands can be used. An example of message.bin from a previous example is used. Readers may have noticed that no IV has been provided, even though it's required in all block encryption modes of operation except ECB. The reason for this is that OpenSSL automatically derives the IV from the given password. Users can specify the IV using the following switch. -k \_IV, open parentheses, initialization vector, close parentheses, should be provided in hex. In order to decode from base64, the following commands are used. Follow the message.b64 file from the previous example. There are many types of ciphers that are supported in OpenSSL. You can explore these options based on the examples provided thus far. A list of supported cipher types is shown as follows. Readers might see a different number of supported ciphers depending on the version of the OpenSSL tool being used. The OpenSSL tool can be used to experiment with all the ciphers shown in the preceding screenshot. We will also use OpenSSL in the next chapter to demonstrate various public key cryptographic primitives and protocols. Summary: this chapter introduced symmetric key cryptography. We started with basic mathematical definitions and cryptographic primitives. After this, we introduced the concepts of stream and block ciphers along with the working modes of block ciphers. Moreover, we introduced some practical exercises using OpenSSL to complement the theoretical concepts covered. In the next chapter, we will introduce public key cryptography, which is used extensively in blockchain technology and has very interesting properties.
Chapter 4: Public Key Cryptography. In this chapter, you will be introduced to the concepts and practical aspects of public key cryptography, also called asymmetric cryptography or asymmetric key cryptography. We will continue to use OpenSSL, as we did in the previous chapter, to experiment with some applications of cryptographic algorithms so that you can gain hands-on experience. We will start with the theoretical foundations of public key cryptography and will gradually build on the concepts with relevant practical exercises. After this, we will introduce some new and advanced cryptography constructs. Before discussing cryptography further, some mathematical terms and concepts need to be explained in order to build a foundation for fully understanding the material provided later in this chapter. The next section serves as a basic introduction to these concepts. An explanation with proofs and relevant background for all of these terms would require somewhat complex mathematics, which is beyond the scope of this book. More details on these topics can be found in any standard number theory, algebra, or cryptography book. Mathematics. As the subject of cryptography is based on mathematics, this section will introduce some basic concepts that will help you understand the concepts presented later. Modular arithmetic. Also known as clock arithmetic, numbers in modular arithmetic wrap around when they reach a certain fixed number. This fixed number is a positive number called modulus, sometimes abbreviated to mod, and all operations are performed concerning this fixed number. Modular arithmetic is analogous to a 12-hour clock. There are numbers from 1 to 12. When 12 is reached, the numbers start from 1 again. Imagine that the time is 9 o'clock now. 4 hours from now it will be 1 o'clock, because the numbers wrap around at 12 and start from 1 again. In normal addition, this would be 9 plus 4 equals 13, but that is not the case on a 12-hour clock. It is 1 o'clock. In other words, this type of arithmetic deals with the remainders after the division operation. For example, 50 mod 11 is 6 because 50 divided by 11 leaves a remainder of 6. Sets. These are collections of distinct objects. For example, x equals 1, 2, 3, 4, 5. Fields. A field is a set in which all its elements form an additive and multiplicative group. It satisfies specific axioms for addition and multiplication. For all group operations, the distributed law is also applied. The law dictates that the same sum or product will be produced, even if any of the terms or factors are reordered. Finite fields. A finite field is one with a finite set of elements, also known as Galois field. These structures are of particular importance in cryptography as they can be used to produce accurate and error-free results of arithmetic operations. For example, prime finite fields are used in elliptic curve cryptography, ECC, to construct discrete logarithm problems. Prime fields. A prime field is a finite one with a prime number of elements. It has specific rules for addition and multiplication, and each non-zero element in the field has an inverse. Addition and multiplication operations are performed modulo p, that is, modulo a prime number. Groups. A group is a commutative set with an operation that combines two elements of the set. The group operation is closed and associated with a defined identity element. Additionally, each element in the set has an inverse. Closure closed means that if, for example, elements A and B are in the set, then the resultant element after performing an operation on the elements is also in the set. Associative means that the grouping of elements does not affect the result of the operation. 4 group axioms must be satisfied for a set to qualify as a group. These group axioms include closure, associativity, an identity element, and an inverse element.
Abelian groups. An abelian group is formed when the operation on the elements of a set is commutative. The commutative law means that changing the order of the elements does not affect the result of the operation. For example, A times B equals B times A. The key difference is that in an abelian group, closure, associativity, identity element, inverse element, and commutativity, abelian group axioms are satisfied, whereas in a group, only the first 4 axioms are required to be satisfied, that is, closure, associativity, an identity element, and an inverse element. Rings. If more than one operation can be defined over an abelian group, that group becomes a ring. There are also specific properties that need to be satisfied. A ring must have closure and associative and distributive properties. Cyclic groups. A cyclic group is a type of group that can be generated by a single element called the group generator. Order. This is the number of events in a field. It is also known as the cardinality of the field. This completes a basic introduction to some mathematical concepts involved in cryptography. In the next section, you will be introduced to cryptography concepts. Asymmetric cryptography. Asymmetric cryptography refers to a type of cryptography where the key that is used to encrypt the data is different from the key that is used to decrypt the data. These keys are called private and public keys, respectively, which why asymmetric cryptography is also known as public key cryptography. It uses both public and private keys to encrypt and decrypt data, respectively. Various asymmetric cryptography schemes are in use, including RSA, named after its founders, Rivas, Shamir, and Adelman, DSA, digital signature algorithm, and El-Gamal encryption. An overview of public key cryptography is shown in the following diagram.
The preceding diagram illustrates how a sender encrypts data P using the recipient's public key and encryption function E, and produces an output encrypted data C, which is then transmitted over the network to the receiver. Once it reaches the receiver, it can be decrypted using the receiver's private key by feeding the C encrypted data into function D, which will output plaintext P. This way, the private key remains on the receiver side, and there is no need to share keys in order to perform encryption and decryption, which is the case with symmetric encryption. The following diagram shows how the receiver uses public key cryptography to verify the integrity of the received message. In this model, the sender signs the data using their private key and transmits the message across to the receiver. Once the message is received, it is verified for integrity by the sender's public key. It's worth noting that there is no encryption being performed in this model. It is simply presented here to help you thoroughly understand the material covering message authentication and validation that will be provided later in this chapter. The preceding diagram shows that the sender digitally signs the plaintext P with their private key using signing function S, and produces data C, which is sent to the receiver, who verifies C using the sender's public key and function V to ensure the message has indeed come from the sender. Security mechanisms offered by public key cryptosystems include key establishment, digital signatures, identification, encryption, and decryption. Key established mechanisms are concerned with the design of protocols that allow the setting up of keys over an insecure channel. Non-repudiation, defined in Chapter 3, Symmetric Cryptography, as the assurance that an action once taken by someone cannot be denied later. Services, a very desirable property in many scenarios, can be provided using digital signatures. Sometimes it is important not only to authenticate a user,
but also to identify the entity involved in a transaction. This can also be achieved by a combination of digital signatures and challenge-response protocols. Finally, the encryption mechanism to provide confidentiality can also be obtained using public key cryptosystems such as RSA, ECC, and El-Gamal. Public key algorithms are slower in terms of computation than symmetric key algorithms. Therefore, they are not commonly used in the encryption of large files or the actual data that requires encryption. They are usually used to exchange keys for symmetric algorithms. Once the keys are established securely, symmetric key algorithms can be used to encrypt the data. Public key cryptography algorithms are based on various underlying mathematical functions. The three main categories of asymmetric algorithms are described here. Integer factorization. Integer factorization schemes are based on the fact that large integers are very hard to factor. RSA is a prime example of this type of algorithm. Discrete logarithm. A discrete logarithm scheme is based on a problem in modular arithmetic. It is easy to calculate the result of a modulo function, but it is computationally impractical to find the exponent of the generator. In other words, it is extremely difficult to find the input from the result, output. This is called a one-way function. For example, consider the following equation. 3 squared mod 10 equals 9. Now given 9, the result of the preceding equation, finding 2, which is the exponent of the generator 3 in the equation, is extremely hard to determine. This difficult problem is commonly used in the Diffie-Hellman key exchange and digital signature algorithms. Elliptic curves. The elliptic curves algorithm is based on the discrete logarithm problem discussed previously, but in the context of elliptic curves. An elliptic curve is an algebraic cubic curve over a field, which can be defined by an equation as shown here. The curve is non-singular, which means that it has no cusps or self-intersections. It has two variables a and b, as well as a point of infinity. Y squared equals x to the third power plus ax plus b. Here a and b are integers whose values are elements of the field, on which the elliptic curve is defined. Elliptic curves can be defined over reals, rational numbers, complex numbers, or finite fields. For cryptographic purposes, an elliptic curve over prime finite fields is used instead of real numbers. Additionally, the prime should be greater than 3. Different curves can be generated by varying the values of a and or b. The most prominently used cryptosystems based on elliptic curves are the elliptic curve digital signatures algorithm, ECDSA, and the elliptic curve Diffie-Hellman ECDH key exchange. In this section, we discovered the basic principle of public key cryptography and relevant categories of asymmetric algorithms. This understanding will serve as a foundation for the concepts introduced next in this chapter. One of the key concepts in asymmetric cryptography is of public and private keys, which we'll describe next. Public and private keys. A private key, as the name suggests, is a randomly generated number that is kept secret and held privately by its users. Private keys need to be protected, and no unauthorized access should be granted to that key, otherwise the whole scheme of public key cryptography is jeopardized, as this is the key that is used to decrypt messages. Private keys can be of various lengths, depending on the type and class of algorithms used. For example, in RSA, typically a key of 1024 bits or 2048 bits is used. The 1024-bit key size is no longer considered secure, and at least a 2048-bit key size is recommended. A public key is freely available and published by the private key owner. Anyone who would then like to send the publisher of the public key an encrypted message can do so by encrypting the message using the published public key and sending it to the holder of the private key. No one else is able to decrypt the message because the corresponding private key is held securely by the intended recipient. Once the public key encrypted message is received, the recipient can decrypt the message using the private key. There are a few concerns, however, regarding public keys. These include authenticity and identification of the publisher of the public keys. In the following section, we will introduce two examples of asymmetric key cryptography, RSA and ECC. RSA is the first implementation of public key cryptography, where ECC is used extensively in blockchain technology. RSA was invented in 1977 by Ron Rivest, Adi Shamir, and Leonard Adelman, hence the name RSA. This type of public key cryptography is based on the integer factorization problem, where the multiplication of two large prime numbers is easy, but it is difficult to factor the product, the result of the multiplication, back to the two original numbers. The crux of the work involved with the RSA algorithm happens during the key generation process. An RSA key pair is generated by performing the following steps. 1. Modulus generation. Select P and Q, which are very large prime numbers. Multiply P and Q, n equals P times Q, to generate modulus n. 2. Generate the coprime. Assume a number called E. E should satisfy a certain condition, that is, it should be greater than 1 and less than P minus 1 Q minus 1. In other words, E must be a number such that no number other than 1 can be divided into E, and P minus 1 Q minus 1. This is called a coprime. That is, E is the coprime of P minus 1 Q minus 1. 3. Generate the public key. The modulus generated in step 1 and coprime E generated in step 2 is a pair that is a public key. This part is the public part that can be shared with anyone. However, P and Q need to be kept secret. 4. Generate the private key. The private key is called D here, and is calculated from P, Q, and E. The private key is basically the inverse of E modulo P minus 1 Q minus 1. As an equation, it is as follows. ED equals 1 mod, open parentheses, P minus 1, close parentheses, open parentheses, Q minus 1, close parentheses. Usually, an extended Euclidean algorithm is used to calculate D. This algorithm takes P, Q, and E and calculates D. The key idea in this scheme is that anyone who knows P and Q can easily calculate private key D by applying the extended Euclidean algorithm. However, someone who does not know the value of P and Q cannot generate D. This also implies that P and Q should be large enough for the modulus n to become extremely difficult, computationally impractical, to factor. The original RSA paper is available here, web.mit.edu/6.857/oldstuff/fall03/rivest78method.pdf. Now let's see how encryption and decryption operations are performed using RSA. RSA uses the following equation to produce ciphertext. C equals P E mod n. This means that plaintext P is raised to the power of E and then reduced to modulo n. Decryption in RSA is provided in the following equation. P equals CD mod n. This means that the receiver who has a public key pair NE can decipher the data by raising C to the value of the private key D and then reducing to modulo n. We'll look at a practical example of encryption and decryption with RSA later in the chapter. For now, let's explore the fundamentals of ECC, elliptic curve cryptography. ECC is based on the discrete logarithm problem founded upon elliptic curves over finite fields, Galois fields. The main benefit of ECC over other types of public key algorithms is that it requires a smaller key size while providing the same level of security as, for example, RSA. Two notable schemes that originate from ECC are ECDH for key exchange and ECDSA for digital signatures. ECC can also be used for encryption, but it is not usually used for this purpose in practice. Instead, key exchange and digital signatures are used more commonly. As ECC needs less space to operate, it is becoming very popular on embedded platforms and in systems where storage resources are limited. By comparison, the same level of security can be achieved with ECC when only using 256-bit operands as compared to 3072 bits in RSA. Mathematics behind ECC. To understand ECC, a basic introduction to the underlying mathematics is necessary. An elliptic curve is basically a type of polynomial equation known as the Weierstrass equation, which generates a curve over a finite field. The most commonly used field is where all arithmetic operations are performed modulo a prime number p. Elliptic curve groups consist of points on the curve over a finite field. An elliptic curve is defined in the following equation: y squared equals x to the third power plus ax plus b mod p. Here, a and b belong to a finite field, zp or fp, prime finite field, along with a special value called the point of infinity. The point of infinity is used to provide identity operations for points on the curve. Furthermore, a condition also needs to be met that ensures that the equation mentioned earlier has no repeated roots. This means that the curve is non-singular. The condition is described in the following equation, which is the standard requirement that needs to be met. More precisely, this ensures that the curve is non-singular. 4a to the third power plus 27b squared is not equal to 0 mod p. To construct the discrete logarithm problem based on elliptic curves, a large enough cyclic group is required. First, the group elements are identified as a set of points that satisfy the previous equation. After this, group operations need to be defined on these points. Basic group operations on elliptic curves are point addition and point doubling. Point addition is a process where two different points are added, and point doubling means that the same point is added to itself. Point addition. Point addition is shown in the following diagram. This is a geometric representation of point addition on elliptic curves. In this method, a diagonal line is drawn through the curve that intersects the curve at 2 points shown below P and Q, which yields a third point between the curve and the line. This point is mirrored as P plus Q, which represents the result of the addition as R. This is shown as P plus Q in the following diagram. The group operation denoted by the plus sign for addition yields the following equation: P plus Q equals R. In this case, 2 points are added to compute the coordinates of the third point on the curve. P plus Q equals R. More precisely, this means that coordinates are added, as shown in the following equation: x1, y1 plus x2, y2 equals x3, y3. The equation of point addition is as follows: x3 equals s squared minus x1 minus x2 mod p. y3 equals s open parentheses x1 minus x3 close parentheses minus y1 mod p. Here we can see the result of the preceding equation. S equals y squared minus y1 divided by x squared minus y1 mod p. S in the preceding equation depicts the line going through P and Q. An example of point addition is shown here. It was produced using Certicom's online calculator. This example shows the addition and solutions for the equation over finite field F23. This is in contrast to the example shown earlier, which is over real numbers and only shows the curve but provides no solutions to the equation. In the preceding example, the graph on the left-hand side shows the points that satisfy this equation. Y squared equals x to the third power plus 7x plus 11. There are 27 solutions to the equation shown earlier over finite field F23. P and Q are chosen to be added to produce point R. Calculations are shown on the right-hand side, which calculates the third point R. Note that in the preceding graph, in the calculation shown on the right-hand side, L is used to depict the line going through P and Q. As an example to show how the equation is satisfied by the points shown on the graph, a point xy is picked up where x equals 3 and y equals 6. This point can be visualized in the graph shown here. Notice the point at coordinate 3, 6 indicated by an arrow. Using these values shows that the equation is indeed satisfied. Y squared mod 23 equals x to the third power plus 7x plus 11 mod 23. 6 squared mod 23 equals 3 to the third power plus 7 open parentheses 3 close parentheses plus 11 mod 23. 36 mod 23 equals 59 mod 23. 13 equals 13. The next section introduces the concept of point doubling, which is another operation that can be performed on elliptic curves. Point doubling, the other group operation on elliptic curves, is called point doubling. This is a process where p is added to itself. This is the case when p and q are at the same point, so effectively the operation becomes adding the point to itself, and is therefore called point doubling. In this method, a tangent line is drawn through the curve as shown in the following graph. The second point is obtained, which is at the intersection of the tangent line drawn and the curve. This point is then mirrored to yield the result, which is shown as 2p equals p plus p. In the case of point doubling, the equation becomes x3 equals s squared minus x1 minus x2 mod p. y3 equals s open parentheses x1 minus x3 close parentheses minus y1 mod p. S equals y2 minus y1 divided by x2 minus x3 mod p. Here, s is the slope of the tangent line going through p, which is the line shown at the top in the preceding graph. In the preceding example, the curve is plotted as a simple example, and no solution to the equation is shown. The following example shows the solution and point doubling of elliptic curves over finite field F23. The graph on the left-hand side shows the points that satisfy the equation. Y squared equals x3 plus 7x plus 11. As shown on the right-hand side of the preceding graph, the calculation that finds r after p is added to itself. Point doubling. There is no q shown here because the same point p is used for doubling. Note that in the calculation shown previously on the right-hand side of the graph, L is used to depict the tangent line going through p. With this, we have covered basics of ECC. In the next section, an introduction to the discrete logarithm problem based on ECC will be presented. The discrete log problem was introduced earlier in this chapter, and can be depicted with a simple equation. That is, given y, find x such that gx equals y. Fundamentally, it is a one-way function, which is easy to evaluate but extremely hard computationally to invert. Using addition and doubling, we can construct another operation called point multiplication, which we introduce next. Point multiplication. This operation is also called scalar point multiplication. It is used to multiply points on elliptic curves by a given integer. Let's call this integer d and the point p. We get dp by repeatedly adding p d times. This operation can be described as follows. P plus p plus p equals dp, where p is added d times. Any point on the curve can be added multiple times to itself. The result of this operation is always another point on the curve. The addition operation is not efficient for large values of d. However, point multiplication operation can be made efficient by utilizing double and add algorithm, which combine point addition and doubling operations to achieve exponential performance gain. For example, if using addition only to get 9p, we have to do p plus 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 p, which can become infeasible pretty quickly if the number of p's increases. To address this, we can use the double and add mechanism, where we first convert 9 into binary. Then, starting from the most significant bit, for each bit that is 1, high, perform double and addition operation, and for each 0, perform only the double operation. We do not perform any operation on the most significant bit. As 9 is 1001 in binary, we get for each bit starting from left to right p, 2p, 4p, 8p plus p. This process produces 9p only with 3 double operations and 1 addition operation instead of 9 addition operations. In this example, point doubling and addition has been used to construct an efficient operation of scalar multiplication. Now consider that dp results in producing another point on the curve. Let's call that point t. We can say that with all these doublings and additions, we have computed a point called t. We multiplied a point p on the curve with a number d to compute another point t. Here's the key idea now. Even if we know points p and t, it is computationally infeasible to reconstruct the sequence of all the double and addition operations that we did to figure out the number d. In other words, even if someone knows p and t, it is almost impossible for them to find d. This means that it is a one-way function, and it is the basis of the elliptic curve discrete logarithm problem, ECDLP. We describe the discrete logarithm problem in more detail next. The discrete logarithm problem in ECC. The discrete logarithm problem in ECC is based on the idea that, under certain conditions, all points on an elliptic curve form a cyclic group. On an elliptic curve, the public key is a random multiple of the generator point, whereas the private key is a randomly chosen integer used to generate the multiple. In other words, a private key is a randomly selected integer, whereas the public key is a point on the curve. The discrete logarithm problem is used to find the private key, an integer where that integer falls within all points on the elliptic curve. The following equation shows this concept more precisely. Consider an elliptic curve E with two elements, p and t. The discrete logarithmic problem is to find the integer d, where 1 is less than or equal to d is less than or equal to #e, such that p plus p plus p equals dp equals t. Here t is the public key, a point on the curve xy, and d is the private key. In other words, the public key is a random multiple of the generator p, whereas the private key is the integer that is used to generate the multiple. #e represents the order of the elliptic curve, which means the number of points that are present in the cyclic group of the elliptic curve. A cyclic group is formed by a combination of points on the elliptic curve and the point of infinity. The initial starting point p is a public parameter, and the public key t is also published, whereas d, the private key, is kept secret. If d is not known, it is impractical to calculate it by only having the knowledge of t and p, thus creating the hard problem on which ECDLP is built. A key pair is linked with the specific domain parameters of an elliptic curve. Domain parameters include field size, field representation, two elements from the field A and B, two field elements xg and yg, order n of point g, which is calculated as g equals xg yg, and the cofactor h equals #e, open parentheses fq, close parentheses, divided by n. A practical example using OpenSSL will be described later in this section. Various parameters are recommended and standardized so they can be used as curves with ECC. An example of the SECP256K1 specification is shown here. The following figure is the specification that is used in Bitcoin, which can be accessed here, www.sec2-v2.pdf. An explanation of all these values in the sextuple follows. P is the prime P that specifies the size of the finite field. A and B are the coefficients of the elliptic curve equation. G is the base point that generates the required subgroup, also known as the generator. The base point can be represented in either compressed or uncompressed form. There is no need to store all points on the curve in a practical implementation. The compressed generator works because the points on the curve can be identified using only the x-coordinate and the least significant bit of the y-coordinate.
N is the order of the subgroup. H is the cofactor of the subgroup.
We can also use the OpenSSL command line to view these parameters of SECP256K1. This can be seen here. This command will show the output as follows. This output can be readily compared and verified using the SECP256K1 specification shown earlier. Note that there are different types of curves, and they must be chosen carefully in order to ensure cryptographic security guarantees. There are also curves that had been standardized by NIST in the US and published in the FIPS 186 document. You can find more about safe curves and their selection criteria at safecurves.cr.yp.to. In the following section, 2 examples of using OpenSSL will be shown to help you understand the practical aspects of RSA and ECC. RSA using OpenSSL. The following example illustrates how RSA public and private key pairs can be generated using the OpenSSL command line. First, the RSA private key can be generated using OpenSSL as follows. Private key $OpenSSL gen p key -algorithm RSA-out private key.pem -p opt RSA _keygen _bits :1024. After executing the command, a file named privatekey.pem is produced, which contains the generated private key as follows. It is okay to reveal the private key here because we are simply using it for our example. However, in production systems, safeguarding the private key is of utmost importance. Make sure that the private key is kept secret. Also, remember that the preceding key is just being used here as an example. Do not reuse it. Public key. As the private key is mathematically linked to the public key, it is also possible to generate or derive the public key from the private key. Using the example of the preceding private key, the public key can be generated as follows. $OpenSSL RSA-pubout-in privatekey.pem -out publickey.pem writing RSA key. The public key can be viewed using a file reader or any text viewer. $cat publickey.pem. In order to see more details of the various components such as the modulus, prime numbers that are used in the encryption process, or exponents and coefficients of the generated private key, the following command can be used. Only part of the output is shown here as the actual output is very long. Exploring the public key. Similarly, the public key can be explored using the following commands. Public and private keys are base 64 encoded. $OpenSSL pkey -in publickey.pem -pubin -text. Now the public key can be shared openly, and anyone who wants to send you a message can use the public key to encrypt the message and send it to you. You can then use the corresponding private key to decrypt the file. Encryption and decryption using RSA. In this section, an example will be presented that demonstrates how encryption and decryption operations can be performed using RSA with OpenSSL. Encryption. Taking the private key we generated in the previous example, the command to encrypt a text file message.txt can be constructed as shown here. $echo data to encrypt greater than message.txt. $OpenSSL RSAUT1 -encrypt -inkey publickey.pem -pubin -in message.txt -out message.rsa. This will produce a file named message.rsa, which is in binary format. If you open message.rsa in the Nano editor or any other text editor of your choice, it will show some scrambled data, as shown in the following screenshot. Decryption. In order to decrypt the RSA encrypted file, the following command can be used. $OpenSSL RSAUT1 -decrypt -inkey privatekey.pem
-in message.rsa-out message.tec. Now if the file is read using cat, decrypted plaintext can be seen as shown here. $cat message.tec data to encrypt. ECC using OpenSSL. OpenSSL provides a very rich library of functions to perform ECC. The following section shows how to use ECC functions in a practical manner in OpenSSL. ECC private and public key pairs. In this section first, an example will be presented that demonstrates the creation of a private key using the ECC functions available in the OpenSSL library. Private key. ECC is based on domain parameters defined by various standards. You can see the list of all available standards defined and the recommended curves available in OpenSSL using the following command. Once again, only part of the output is shown here, and it is truncated in the middle. In the following example, SCCP-256K1 is used to demonstrate ECC usage. Private key generation. In this section, a private key based on SCCP-256K1 will be generated using the OpenSSL command line tool. $OpenSSL ec-param-name SCCP-256K1-genkey -no out ec-privatekey.pem. This command will produce a file named ec-privatekey.pem, which we can view using the command shown here. $cat ec-privatekey.pem. The file named ec-privatekey.pem now contains the elliptic curve private key that is generated based on the SCCP-256K1 curve. In order to generate a public key from a private key, issue the following command: $OpenSSL ec-in ec-privatekey.pem -pubout -out ec-pubkey.pem. Reading the file produces the following output, displaying the generated public key: $cat ec-pubkey.pem. Now the ec-pubkey.pem file contains the public key derived from ec-privatekey.pem. The private key can be further explored using the following command: $OpenSSL ec-in ec-privatekey.pem -text -no out. Similarly, the public key can be further explored with the following command: $OpenSSL ec-in ec-pubkey.pem -pubin -text -no out. It is also possible to generate a file with the required parameters, in this case SCCP-256K1, and then explore it further to understand the underlying patterns. The file now contains all the SCCP-256K1 parameters, and it can be analyzed using the following command: $OpenSSL ec-param-in SCCP-256K1.pem -text -param_enc explicit -no out. This command will produce output similar to the one shown here. The preceding example shows the prime number used and the values of A and B, along with the generator, order, and cofactor of the SCCP-256K1 curve domain parameters. With the preceding example, our introduction to public key cryptography from an encryption and decryption perspective is complete. Another application of hash functions is in digital signatures, where they can be used in combination with asymmetric cryptography. This concept will be explored in detail in the following section. Digital signatures. Digital signatures provide a means of associating a message with an entity from which the message has originated. Digital signatures are used to provide data origin authentication and non-repudiation. Digital signatures are used in blockchains where transactions are digitally signed by senders using their private key before the sender broadcasts the transaction to the network. This digital signing proves that the sender is the rightful owner of the asset, for example, bitcoins. These transactions are verified again by other nodes on the network to ensure that the funds indeed belong to the node user, who claims to be the owner. We will discuss these concepts in more detail in the chapters dedicated to Bitcoin and Ethereum in this book. Digital signatures are calculated in 2 steps. As an example, the high-level steps of the RSA digital signature scheme are as follows. RSA digital signature algorithms. RSA-based digital signature algorithms are calculated using the 2 steps listed here. Fundamentally, the idea is to first compute the hash of the data and then sign it with the private key. 1. Calculate the hash value of the data packet. This will provide the data integrity guarantee as the hash can be computed at the receiver's end again and matched with the original hash to check whether the data has been modified in transit. Technically, messaging signing can work without hashing the data first, but that is not considered secure. 2. Sign the hash value with the signer's private key. As only the signer has the private key, the authenticity of the signature and the signed data is ensured. Digital signatures have some important properties such as authenticity, unforgettability, and non-reusability. Authenticity means that the digital signatures are verifiable by a receiving party. The unforgettability property ensures that only the sender of the message can use the signing functionality using the private key. Digital signatures must provide protection against forgery. Forgery means an adversary fabricating a valid signature for a message without any access to the legitimate signer's private key. In other words, unforgettability means that no one else can produce the signed message produced by a legitimate sender. This is also called the property of non-repudiation. Non-reusability means that the digital signature cannot be separated from a message and used again for another message. In other words, the digital signature is firmly bound to the corresponding message and cannot be simply cut from its original message and attached to another. The operation of a generic digital signature function is shown in the following diagram. If a sender wants to send an authenticated message to a receiver, there are 2 methods that can be used: sign then encrypt and encrypt then sign. These 2 approaches of using digital signatures with encryption are as follows. Sign then encrypt. With this approach, the sender digitally signs the data using the private key, appends the signature to the data, and then encrypts the data and the digital signature using the receiver's public key. This is considered a more secure scheme compared to the encrypt then sign scheme described next. Encrypt then sign. With this method, the sender encrypts the data using the receiver's public key and then digitally signs the encrypted data. In practice, a digital certificate that contains the digital signature is issued by a certificate authority, CA, that associates a public key with an identity. Various schemes such as RSA, DSA, and ECDSA-based digital signature schemes are used in practice. RSA is the most commonly used. However, with the traction of ECC, ECDSA-based schemes are also becoming quite popular. This is beneficial in blockchains because ECC provides the same level of security that RSA does, but it uses less space. Also, the generation of keys is much faster in ECC compared to RSA, so it helps with the overall performance of the system. The following table shows that ECC is able to provide the same level of cryptographic strength as an RSA-based system with smaller key sizes. Now that we understand how the RSA digital signature scheme works, in the next section we'll introduce ECDSA, which is another popular digital signature scheme. The elliptic curve digital signature algorithm. ECDSA is a DSA based on elliptic curves. The DSA is a standard for digital signatures. It is based on modular exponentiation and the discrete logarithm problem. It is used on the Bitcoin and Ethereum blockchain platforms to validate messages and provide data integrity services. Now we'll describe how ECDSA works. In order to sign and verify using the ECDSA scheme, the first key pair needs to be generated. 1. First define an elliptic curve E with the following: modulus P, coefficients A and B, generator point A that forms a cyclic group of prime order Q. 2. An integer D is chosen randomly so that 0 is less than D less than Q.
3. Calculate public key B so that B equals DA. The public key is a sextuple in the form shown here. KPB equals PABQAB. The private key is a randomly chosen integer D in step 2. KPR equals D. Now the signature can be generated using the private and public key. 4. An ephemeral key K is chosen, where 0 is less than KE less than Q. It should be ensured that KE is truly random and that no two signatures have the same key. Otherwise, the private key can be calculated. 5. Another value R is calculated using R equals KEA, that is, by multiplying A, the generator point, and the random ephemeral key.
6. Initialize a variable R with the x-coordinate value of point R so that R equals XR. 7. The signature can be calculated as follows. S equals open parentheses H open parentheses M close parentheses plus DR close parentheses KE -1 mod Q. Here M is the message for which the signature is being computed, and M is the hash of the message M. 8. Signature verification is carried out by following this process. Auxiliary value W is calculated as W equals S-1 mod Q. Auxiliary value U1 equals W point H open parentheses M close parentheses mod Q. Auxiliary value U2 equals W point R mod Q. Calculate point P equals U1A plus U2B. 9. Verification is carried out as follows. RS is accepted as a valid signature if the x-coordinate of point P, calculated in step 4, has the same value as the signature parameter R mod Q, that is, XP equals R mod Q means valid signature. XP exclamation mark equals R mod Q means invalid signature. Various practical examples will now be shown that demonstrate how the RSA digital signature can be generated, used, and verified using OpenSSL. How to generate a digital signature using OpenSSL. The first step is to generate a hash of the message file. $OpenSSL DGST SHA-256 message.txt. SHA-256 open parentheses message.txt close parentheses equals. Both hash generation and signing can be done in a single step, as shown here. Note that private key.pem was generated in the steps provided previously. $OpenSSL DGST SHA-256 sign private key.pem out signature.bin message.txt. Now let's display the directory showing the relevant files. $cat signature.bin. In order to verify the signature, the following operation can be performed. $OpenSSL DGST SHA-256 verify public key.pem signature.bin message.text. Verified OK. Similarly, if some other signature file that is not valid is used, the verification will fail, as shown here. Next, an example will be presented that shows how OpenSSL can be used to perform ECDSA-related operations. ECDSA using OpenSSL. First, the private key is generated using the following commands. $OpenSSL ecparam -genkey -name SECP256 K1 -no out -out ECC private key.pem $cat ECC private key.pem. Next, the public key is generated from the private key. Now suppose a file named testsign.txt needs to be signed and verified. This can be achieved as follows. 1. Create a test file. 2. Run the following command to generate a signature using a private key for the testsign.txt file.
3. Finally, command for verification can be run, as shown here. A certificate can also be produced by using the private key generated earlier by using the command shown here. This command will produce an output similar to the one shown here. Enter the appropriate parameters to generate the certificate. You are about to be asked to enter information that will be incorporated into your certificate request. What you are about to enter is what is called a distinguished name or a DN. There are quite a few fields, but you can leave some blank. Country name, 2-letter code, AU:GB. State or province name, full name, some state.
Cambridge, locality name.
City, Cambridge. Organization name, company. Internet widgets, Pty Limited. Pty Ltd. Dr. Equinox, organizational unit name, section. Common name, Dragonox. Email address, dragonox@dragonox.com. The certificate can be explored using the following command. $open SSL x 509-in ECC certificate.pem-text-noout. In this section, we covered digital signature schemes and some practical examples. Next, we'll present some more advanced cryptography topics, cryptographic constructs, and blockchain technology. Now we'll present some advanced topics in cryptography that not only are important on their own, but are also relevant to blockchain technology due to their various applications in this space. Homomorphic encryption. Usually public key cryptosystems such as RSA are multiplicative homomorphic or additive homomorphic, such as the Palier cryptosystem, and are called partially homomorphic systems. Additive partially homomorphic encryptions, PHEs, are suitable for e-voting and banking applications. Until recently, there has been no system that supported both operations, but in 2009, a fully homomorphic system was discovered by Greg Gentry. As these schemes enable the processing of encrypted data without the need for decryption, they have many different potential applications, especially in scenarios where maintaining privacy is required. But data is also mandated to be processed by potentially untrusted parties. For example, cloud computing and online search engines. Recent development in homomorphic encryption has been very promising, and researchers are actively working to make it efficient and more practical. This is of particular interest in blockchain technology, as described later in this book, as it can solve the problem of confidentiality and privacy in the blockchain. Signcryption. Signcryption is a public key cryptography primitive that provides all of the functions of a digital signature and encryption. Yuliang Zhen invented signcryption, and it is now an ISO standard, ISO/IEC 29150:2011. Traditionally, sign then encrypt or encrypt then sign schemes are used to provide unforgettability, authentication, and non-repudiation. But with signcryption, all the services of digital signatures and encryption, such as confidentiality, are provided at a cost that is less than that of the sign then encrypt scheme. Signcryption enables cost, signature, and encryption, cost signature plus cost encryption, in a single logical step. This means that the cost of applying a digital signature and encrypting a message in the same logical step is lower, compared to a scheme where a message is first signed and then encrypted in 2 independent steps. This property makes signcryption an efficient scheme. Secret sharing. Secret sharing is the mechanism of distributing a secret among a set of entities. All entities within a set get a unique part of the secret after it is split into multiple parts. The secret can be reconstructed by combining all or some parts, a certain number or threshold, of the secret. The individual secret shares parts on their own, do not reveal anything about the secret.
This concept can be visualized through the following diagram. Commitment schemes. Commitment schemes are usually described as a digital cryptographic equivalent of a sealed envelope. A commitment itself does not reveal any information about the actual value inside it. This scheme runs in two phases, namely, commit phase, open phase. The commit phase provides two security features, that is, hiding and binding. The hiding property is required to ensure that the recipient party cannot find any information or reveal the committed value before the open phase. The binding property ensures that once the sender has committed to a value, that value or message cannot be changed. The open phase, also called the unveil phase, is where the receiver receives some additional information from the sender. This allows the receiver to establish the value hidden, concealed by the commitment with a proof that the sender has not modified the value after the commitment. That is, the sender has not deceived during the commit phase. Commit schemes are used for building zero-knowledge protocols and range-proof protocols. The key idea behind commitment schemes is that they allow someone to secretly commit to a value with the ability to reveal it later. These schemes prevent parties from changing their committed value later, after they've committed to a value. A prime example of a commitment scheme is the Peterson commitment scheme. The original paper on the Peterson commitment scheme is available here. https://link.springer.com/content/pdf/10.1007/3-540-46766-1_9.pdf. In the next section, we'll introduce zero-knowledge proofs, which is an exciting subject and a very ripe area for research. Already, various major blockchains and cryptocurrencies make use of zero-knowledge proofs to provide privacy. A prime example is Zcash, z.cash. Zero-knowledge proofs. Zero-knowledge proofs, ZKPs, were introduced by Goldwasser, Micali, and Rakoff in 1985. These proofs are used to prove the validity of an assertion without revealing any information whatsoever about the assertion. There are three properties of ZKPs that are required: completeness, soundness, and the zero-knowledge property. Completeness ensures that if a certain assertion is true, then the verifier will be convinced of this claim by the prover. The soundness property makes sure that if an assertion is false, then no dishonest prover can convince the verifier otherwise. The zero-knowledge property, as the name implies, is the key property of ZKPs, whereby it is ensured that absolutely nothing is revealed about the assertion except whether it is true or false. Zero-knowledge proofs are probabilistic instead of deterministic. The probabilistic nature of ZKPs is because these protocols require several rounds to achieve a higher level of assurance gradually with each round, which allows the verifier to accept that the prover indeed knows the secret. In literature, usually an analogy known as Alibaba's cave is used to explain zero-knowledge proofs. The analogy was first introduced by Jean-Jacques Quisqueter et al. In their paper, which is available at link.springer.com/content/PDF/10.1007/0-38050_60.pdf. The following diagram shows a variant of this analogy of how the zero-knowledge protocol works. It shows two characters called Peggy and Victor, whose roles are prover and verifier, respectively. Peggy knows a secret magic word to open the door in a cave, which is shaped like a ring. It has a split entrance and has a magic door in the middle of the ring that blocks the other side. We have also labeled the left and right entrances as A and B. Victor wants to know the secret, but Peggy does not want to reveal it. However, she would like to prove to Victor that she does know the secret. Now, there are several steps that are taken by both Peggy and Victor to reach a conclusion regarding whether Peggy knows the secret or not. 1. First, Victor waits outside the main cave entrance and Peggy goes in the cave. 2. Peggy randomly chooses either the A or B entrance to the cave. 3. Now Victor enters the cave and shouts either A or B randomly, asking Peggy to come out of the exit he named. 4. Victor records which exit Peggy comes out from. Now suppose Victor asks Peggy to come out from exit A and she came out from exit B. Victor then knows that Peggy does not know the secret. If Peggy comes out of exit A, then there is a 50% chance that she does know the secret. But this also means that she may have got lucky and chose A to enter in the first place and now has just returned without needing to go through the magic door at all. Now if this routine is performed several times, and given that Victor is choosing A or B at random with each round of this routine protocol, the chances of Peggy getting lucky diminish. If Peggy repeatedly manages to emerge from the entrance that Victor has named, then it is highly probable that Peggy does know the secret to open the magic door. Remember we said earlier that zero-knowledge protocols are probabilistic. Peggy and Victor repeatedly performing this routine proves knowledge of the secret with high probability, as the probability of guessing or getting lucky reduces to the point of being negligible after n number of rounds. Note that during this process, Peggy has not revealed the secret at all, but still managed to convince Victor with high probability that she does know the secret. A ZKP compromises the following phases. 1. Witness phase. In this phase, the prover sends proof of the statement and sends it to the verifier. 2. Challenge phase. In this phase, the verifier chooses a question, challenge, and sends it to the prover. 3. Response phase. In this phase, the prover generates an answer and sends it as a response to the verifier. The verifier then checks the answer to ascertain whether the prover really knows the statement. This scheme can also be visualized using the following diagram, which shows how zero-knowledge protocol generally works and what steps the prover and verifier take in order to successfully run the protocol. Even though zero-knowledge is not a new concept, these protocols have sparked a special interest among researchers in the blockchain space due to their privacy properties, which are very much desirable in finance and many other fields, including law and medicine. A prime example of the successful implementation of a zero-knowledge proof mechanism is the Zcash cryptocurrency. In Zcash, the zero-knowledge succinct non-interactive argument of knowledge, ZSNARK, is implemented to provide anonymity and confidentiality. Applications of ZKP include proof of ownership, that is, proof that the prover is the owner of some secret or a private key without revealing the nature of it. ZKPs can also be used to prove that the prover is a member of some organization or group without revealing their identity. Another use case could be proof of age, where the prover proves that they are, for example, older than 25 years but do not want to reveal their exact age. Another application could be where citizens can pay taxes without revealing their income. Zero-knowledge protocols are usually interactive as they require repeated interactions between the prover and the verifier. But there are protocols that do not require any interaction between a prover and a verifier. These types of ZKPs are called non-interactive types of proofs. A prominent example is the ZK snark. Before the introduction of ZK snarks, ZKPs were considered not very practical because of the complexity that arises from the requirements of repeated interaction between the prover and the verifier and a large proof size. ZK snarks. The ZK snark is a variant of ZKPs that is more efficient and simpler to use and implement. There has been some influential work published on non-interactive zero-knowledge proofs over the years. The most prominent of these, and the one that proposed the universal design, is provided by the paper by Eli Ben-Sasson et al., which is available at www.usenex.org/system/files/conference/use-nix security 14/SEC 14 zk-paper-ben-sassen.pdf. ZK snarks have several properties, which are described here. Zero knowledge is ZK. This property allows a prover to convince a verifier that an assertion, statement, is true without revealing any information about it. A statement in this context is any computer program that terminates and does not take too long to run, that is, not too many cycles. Succinct. This property allows for a small proof that is very quick to verify and is succinct. Non-interactive, N. This property allows the prover to prove a statement without any interaction with the verifier. Arguments of knowledge, ARKs. These are the arguments to convince the verifier that the prover's assertion is true. Remember that we discussed soundness and completeness earlier? In the case of ARKs, the prover has a computational soundness property, meaning that the prover is computationally bounded, and it is computationally infeasible for it to cheat the verifier. ZK snarks have been implemented in different blockchains. The most prominent example is Zcash, which uses it for its shielded transactions feature to provide confidentiality and anonymity. Support for cryptographic primitives required for ZK snarks has also been introduced in the Ethereum blockchain with the Byzantium release. ZK snark proofs are generated by following a number of different steps. Generating snarks for a program statement is not a simple process, as it requires the program to be converted into a circuit with a very specific format. This specific form is called the Quadratic Arithmetic Program, QAP. The process of proof generation is as follows. Computation, arithmetic circuit, R1CS, QAP, ZK snark. Arithmetic circuit. The first step in ZK snark construction is to convert a logical step of a computation into the smallest possible units comprised of basic arithmetic operations. Arithmetic operations include addition, subtraction, multiplication, and division. In the arithmetic circuit, the computation is presented as wires and gates, presenting the flow of inputs and arithmetic operation performed on the inputs. R1CS. R1CS is the abbreviation of Rank 1 Constraint System, R1CS. Basically, this system is a set of constraints that allows all the steps in the arithmetic circuit to be verified, and also confirms that at the end of the process, the output is as expected. QAP. The prover makes use of QAPs to construct proof for the statement. In R1CS, the verifier has to check many different constraints, but with QAP representation of the circuit, all the different constraints can be bundled into only a single constraint. Finally, QAP is used in the ZK snark protocol to prove the assertion through the prover and verifier. ZK snarks are not a silver bullet to privacy problems. Instead, like many other technologies, there are pros and cons. The biggest criticism of ZK snarks is the initial trusted setup. This trusted setup can be influenced and compromised. However, if done correctly, it does work, but there is, however, always a chance that the initial setup was compromised, and no one will ever be able to find out. This is the issue that has been addressed in ZK Starks. ZK Starks. Zero-knowledge scalable transparent arguments of knowledge, ZK Starks, are a new type of ZKP that has addressed several limitations in ZK snarks. This scheme was designed by Eli Ben-Sassen et al. The original paper on the subject is available here, eprint.iacr.org/2018/046.pdf. The key differences between the ZK Stark and ZK Snark schemes are listed in the following table. What is post-quantum resistant? Quantum computing is a concept that uses quantum mechanics to solve problems that take an extremely long time to solve on conventional computers. When large-scale quantum computers are built, they can easily compromise the security of most existing cryptosystems. Post-quantum resistance refers to the idea of building cryptographic algorithms that are resistant to attacks by powerful quantum computers. Further discussion on this topic is not in the scope of this book, and more information on the subject can be found at the following Wikipedia page. Even though this scheme is more efficient, post-quantum resistant, scalable, and transparent, the biggest limitation is its size of proof, which is a few hundred kilobytes compared to zk-SNARK's 288 bytes. This is seen as a problem in public blockchains where large proofs may pose a problem to scalability and performance. Zero-knowledge range proofs, ZKRPs. ZKRPs are used to prove that a number is between a certain range. This can be useful when, for example, someone does not want to reveal their salary, but is willing to only reveal the range between their salary lies. Range proofs can also be used for age checks without requiring the prover to reveal their exact age. In this section, we have covered the very interesting topic of ZKPs and their relevant techniques and developments. ZKPs is a very active area of research, especially in the context of blockchains, where this technology can provide much-needed privacy and confidentiality services on public blockchain networks. Next, we'll introduce different types of digital signatures. Different types of digital signatures. We previously covered digital signatures, but that was an introduction to standard digital signatures. Now we'll provide an overview of different types of digital signatures and their relevance and applications in blockchain technology. Blind signatures. Blind signatures were introduced by David Chaum in 1982. They are based on public key digital signature schemes such as RSA. The key idea behind blind signatures is to get the message signed by the signer, without actually revealing the message. This is achieved by disguising or blinding the message before signing it, hence the name blind signatures. This blind signature can then be verified against the original message, just like a normal digital signature. Blind signatures were introduced as a mechanism to allow the development of digital cash schemes. Specifically, a blind signature can provide unlinkability and anonymity services in a distributed system, such as a blockchain. The original paper from David Chaum on blind signatures is available at blog.koe/upload/chaum.blindsigforpayment.1982.pdf. The blind signature scheme is also used in building BlindCoin, which is used in the MixCoin protocol for Bitcoin to hide user addresses from the mixing service. MixCoin protocol allows anonymous payments in the Bitcoin network, but the user addresses are still visible to the mixing service. BlindCoin is a protocol that addresses this limitation. More information on this scheme is available in the following paper. Multi-signatures. In this scheme, a group of entities signs a single message. In other words, multiple unique keys held by their respective owners are used to sign a single message. This scheme was introduced in 1983 by Itakura et al. In their paper, A Public Key Cryptosystem Suitable for Digital Multi-Signatures, Volume 71, NEC Research and Development, 1983, pages 474 to 480. Multi-signatures are also sometimes called multi-party signatures in literature. In blockchain implementations, multi-signatures provide the ability to allow transactions to be signed by multiple users, which results in increased security. This is also called multi-sig and has been implemented in Bitcoin. These schemes can be used in such a way that the requirement of a number of signatures can be set in order to authorize transactions. For example, a one-of-two multi-signature can represent a joint account where either one of the joint account holders is required to authorize a transaction by signing it. As another variation, for example, a two-of-two multi-signature can be used in a scenario where both joint account holders' signatures are required to sign the transaction. This concept is also generalized as M of n signatures, where M is the minimum number of required signatures and N is the total number of signatures. This concept can be visualized with the following diagram. The preceding diagram shows the signing process on the left-hand side, where M is the number of different users and holding M unique signatures signs a single transaction. When the validator or verifier receives it, all the signatures in it need to be individually verified. The open chain and multi-chain blockchains make use of multi-signature schemes. More information on OpenChain is available at docs.openchain.org/en/latest/general/overview.html. More information regarding multi-chain's multi-signature scheme is available at multichain.com/developer/multisignature-transactions/threshold signatures. This scheme does not rely on users to sign the message with their own unique keys. Instead, it requires only one public key and one private key, and results in only one digital signature. In multi-signature, the resultant message contains digital signatures from all signers and requires verification individually by the verification party, but in threshold signatures. The verifier has to verify only one digital signature. The key idea in the scheme is to split the private key into multiple parts, and each signer keeps their own share of the private key. The signing process requires each user to use their respective share of the private key to sign the message. The communication between signers is governed by a specific communication protocol. In contrast with multi-signatures, the threshold signatures results in a smaller transaction and are quicker to verify. A disadvantage, however, is that in order for threshold signatures to work, all signers must remain online, whereas in multi-signatures, the signature can be provided asynchronously. That is, users can provide signatures whenever they are available. From another angle, there could be a scenario in multi-signatures where a user can withhold their signature maliciously, which could be disadvantageous. Threshold signatures can also be used to provide anonymity services in a blockchain network. The preceding diagram shows the signing process on the left-hand side, where M number of different users holding different parts, shares of a digital signature, sign a single transaction. When the validator or verifier receives it, only one signature needs to be verified. Aggregate signatures. Aggregate signatures are used to reduce the size of digital signatures. This scheme is particularly useful in scenarios where multiple digital signatures are in use. The core idea is to aggregate multiple signatures into a single signature without increasing the size of the signature of a single message. It is simply a type of digital signature that supports aggregation. The smaller aggregate signature is enough to provide verification to the verifier that all users did sign their original messages. Aggregate signatures are commonly used to reduce the size of messages in network and security protocols. For example, the size of digital certificate chains in public key infrastructure, PKI, can be reduced significantly by compressing all signatures in the chain into a single signature. Bonnet Lin Shacham, BLS, aggregate signatures is a popular example of the aggregate signature. BLS has also been used in various blockchains and especially in Ethereum 2.0. Ring signatures. Ring signatures were introduced in 2001 by Ron Rivest, Adi Shamir, and Yael Talman. Ring signature schemes allow a mechanism where any member of a group of signers can sign a message on behalf of the entire group. The key requirement here is that the identity of the actual signer who signed the message must remain unknown, computationally infeasible to determine to an outside observer. It looks equally likely that any one of the trusted group of signers could have signed the message, but it is not possible to figure out who actually signed the message. Each member of the ring group keeps a public key and a private key. Ring signatures can be used to provide anonymity services. This scheme is used in CryptoNote and Monero. In this section, we cover different types of digital signatures, their operation, and their relevance to blockchains. In the next section, we will introduce encoding schemes and some relevant examples. Encoding schemes. Other than cryptographic primitives, binary-to-text encoding schemes are also used in various scenarios. The most common use is to convert binary data into text so that it can either be processed, saved, or transmitted via a protocol that does not support the processing of binary data. For example, images can be stored in a database encoded in base 64, which allows a text field to be able to store a picture. Another encoding named base 58 was popularized by its use in Bitcoin and is addressed in detail in Chapter 6, Introducing Bitcoin. Base 64. The base 64 encoding scheme is used to encode binary data into printable characters. We can do a quick experiment using the OpenSSL command line. $OpenSSL rand 16-base 64. The preceding command has generated a random sequence of 16 bits, and then using the base 64 switch, it has converted that into a base 64 text string. Base 64 converts from 8 bits to a 6-bit ASCII representation. This is useful for storage and transmission, especially in cases where binary data handling could lead to incompatibility between systems. This mechanism is a flexible way to represent binary data as ASCII, which can be easily and universally stored and transmitted. Base 58. The base 58 scheme was first introduced with Bitcoin and is used to encode integers into alphanumeric strings. The key idea behind this encoding scheme is to avoid non-alphanumeric characters and also those characters that look similar and could lead to ambiguity. For example, a lowercase l may look like the number 1. This feature is especially useful because Bitcoin addresses must not have any confusion about the character representation. Otherwise, it could lead to wrongly sending Bitcoins to some non-existent or incorrect address, which is clearly a financial loss. This ingenious encoding scheme avoids this type of situation by ignoring similar-looking characters. We will explore base 56 and its role in generating Bitcoin addresses in detail in Chapter 6, Introducing Bitcoin. Cryptography is a vast field, and this section has introduced some of the main concepts that are essential to understanding cryptography in general, and specifically from a blockchain and cryptocurrency point of view. In the next section, we'll introduce some applications of hash functions, which we introduce in Chapter 3, Symmetric Cryptography. Hash functions are extremely important, and we will explore how these constructs are used in blockchains and generally to build useful constructs that provide the foundation for building blockchain networks. Applications of cryptographic hash functions. There are various constructs that have been built using basic cryptographic parameters to solve different problems in computing. These constructs are also used in blockchains to provide various protocol-specific services. For example, hash functions are used to build Merkle trees, which are used to efficiently and securely verify large amounts of data in distributed systems. Some other applications of hash functions in blockchains are to provide a number of security services. These services are listed here. Hash functions are used in cryptographic puzzles such as the proof of work (POW) mechanism in Bitcoin. Bitcoin's POW makes use of the SHA-256 cryptographic hash function. The generation of addresses in blockchains. For example, in Ethereum, blockchain accounts are represented as addresses. These addresses are obtained by hashing the public key with the KAK-256 hash algorithm and then using the last 20 bytes of this hashed value. Message digest in digital signatures. The creation of Merkle trees to guarantee the integrity of transaction structure in the blockchain. Specifically, this structure is used to quickly verify whether a transaction is included in a block or not. However, note that Merkle trees on their own is not a new idea. It has just been made more popular with the advent of blockchain technology. Merkle trees are the core building blocks of all blockchains, for example, Bitcoin and Ethereum. We will explore Merkle trees in detail now. Merkle trees. The concept of Merkle trees was introduced by Ralph Merkle. A diagram of a Merkle tree is shown here. Merkle trees enable the secure and efficient verification of large datasets.
A Merkle tree is a binary tree in which the inputs are first placed at the leaves. Nodes with no children and then the values of pairs of child nodes are hashed together to produce a value for the parent node, internal node, until a single hash value known as a Merkle root is achieved. This structure helps to quickly verify the integrity of the entire tree, entire dataset, but just by verifying the Merkle root on top of the Merkle tree, because if any change occurs in any of the hashes in the tree, the Merkle root will also change. This is the reason why the integrity of the system can be verified quickly by just looking at the Merkle root. Another advantage of Merkle trees is that there is no requirement of storing large amounts of data. Only the hashes of the data, which are fixed-length digests of the large dataset. Due to this property, the storage and management of Merkle trees is easy and efficient, as it takes a very small amount of space for storage. Also, due to the fact that the tree is storage efficient. The relevant proofs for integrity are also smaller in size and quick to transmit over the network, thus making them bandwidth efficient over the network. We will explain in detail how Merkle trees are fundamental for the consistency and integrity of a blockchain and its transactions in the chapters on Ethereum and Bitcoin. Patricia trees. To understand Patricia trees, you will need to be introduced to the concept of a tree. A tree or a digital tree is an ordered tree data structure used to store a dataset. The practical algorithm to retrieve information coded in alphanumeric Patricia tree, also known as a radix tree, is a compact representation of a tree in which a node that is the only child of a parent is merged with its parent. A Merkle Patricia tree, based on the definitions of Patricia and Merkle, is a tree that has a root node that contains the hash value of the entire data structure. Merkle Patricia trees are used in the Ethereum blockchain. Distributed hash tables. A hash table is a data structure that is used to map keys to values. Internally, a hash function is used to calculate an index into an array of buckets from which the required value can be found. Buckets have records stored in them using a hash key and are organized into a particular order. With the definition provided earlier in mind, we can think of a distributed hash table, DHT, as a data structure where data is spread across various nodes, and nodes are equivalent to buckets in a peer-to-peer network. The following diagram shows how a DHT works. In the preceding diagram, data is passed through a hash function, which then generates a compact key. This key is then linked with the data values on the peer-to-peer network. When users on the network request the data via the file name can be hashed again to produce the same key, and any node on the network can then be requested to find the corresponding data. A DHT provides decentralization, fault tolerance, and scalability. In this section, we covered various applications of cryptographic hash functions. Hash functions are of particular importance in blockchains, as they are key to constructing Merkle trees, which are used in blockchains for the efficient and fast verification of large datasets. With this section, we have completed our introduction to the applications of hash functions. Summary. This chapter started with an introduction to some basic mathematics concepts and asymmetric key cryptography. We discuss various constructs such as RSA and ECC. We also performed some experiments using OpenSSL to see how theoretical concepts can be implemented practically. After this, hash functions were discussed in detail, along with their properties and usage. Next, we covered concepts such as Merkle trees that are used extensively in blockchains and, in fact, are at its core. Other concepts such as Patricia trees and hash tables were also introduced. We also looked at some advanced and modern concepts such as zero-knowledge proofs and relevant constructions, along with different types of digital signatures. In the next chapter, we will explore the captivating world of distributed consensus.
which is central to the integrity of any blockchain and is a very hot area of research. Chapter 5: Consensus Algorithms.
Consensus is a fundamental problem in distributed systems. Since the 1970s, this problem has been researched in the context of distributed systems, but recently, with the advent of blockchain technology, a renewed interest has arisen in developing distributed consensus algorithms that are suitable for blockchain networks.
In this chapter, we will explore the underlying techniques behind distributed consensus algorithms, their inner workings, and new algorithms that have been specifically developed for blockchain networks.
In addition, we will introduce various well-known algorithms in a traditional distributed systems arena that can also be implemented in blockchain networks with some modifications, such as Paxos, Raft, and PBFT. We will also explore other mechanisms that have been introduced specifically for blockchain networks, such as proof of work, POW, proof of stake, POS, and modified versions of traditional consensus such as Istanbul Byzantine Fault Tolerant, IBFT, which is a modified blockchain version of the Practical Byzantine Fault Tolerant, PBFT, algorithm, suitable for a blockchain network. Along the way, we'll cover the following topics: introducing the consensus problem, analysis and design, classification, algorithms, choosing an algorithm. Before we delve into specific algorithms, we first need to understand some fundamental concepts and an overview of the consensus problem. Introducing the consensus problem. The distributed consensus problem has been studied extensively in distributed systems research since the late 1970s. Distributed systems are classified into two main categories, namely message passing and shared memory. In the context of blockchain, we are concerned with the message passing type of distributed systems, where participants on the network communicate with each other via passing messages to each other. Blockchain is a distributed system that relies upon a consensus mechanism, which ensures the safety and liveness of the blockchain network. In the past decade, the rapid evolution of blockchain technology has been observed. Also, with this tremendous growth, research regarding distributed consensus has grown significantly. Researchers from industry and academia are especially interested in researching novel methods of consensus. A common research area is to convert traditional, classical, distributed consensus mechanisms into their blockchain variants that are suitable for blockchain networks. Another area of interest is to analyze existing and new consensus protocols. As we saw in Chapter 1, Blockchain 101, there are different types of blockchain networks. In particular, two types, permissioned and public, non-permissioned, were discussed. The consensus is also classified based on these two paradigms. For example, Bitcoin is a public blockchain. It runs POW, sometimes called Nakamoto consensus. In contrast, many permissioned blockchains tend to run variants of traditional or classical distributed consensus. A prime example is IBFT, which is a blockchained version of PBFT. Other examples include Tendermint, Casper FFG, and many variants of PBFT. We will discuss more on that later in this chapter. First, we will look at traditional consensus mechanisms, which are also known as fault-tolerant distributed consensus, classical distributed consensus, or pre-Bitcoin distributed consensus. Distributed consensus is a highly researched problem, and many fundamental ideas to describe and elaborate on the problem have been developed. One of them, and arguably the most famous, is the Byzantine generals problem, which we'll describe next. In addition to the Byzantine generals problem, we will look at relevant and important possibility results, which will help to build a general understanding of the consensus and relevant limitations.
An understanding of these concepts is vital to understand what problem exactly is being solved and how. The Byzantine generals' problem. The problem of reaching agreement in the presence of faults or Byzantine consensus was first formulated by MPs R. Shostak and L. Lamport. In distributed systems, a common goal is to achieve consensus, agreement among nodes on the network, even in the presence of faults. In order to explain the problem, Lamport came up with an allegorical representation of the problem and named it the Byzantine generals' problem. The Byzantine generals' problem metaphorically depicts a situation where a Byzantine army divided into different units is spread around the city. A general commands each unit, and they can only communicate with each other using a messenger. To be successful, the generals must coordinate their plan and decide whether to attack or retreat. The problem, however, is that any generals could potentially be disloyal and act maliciously to obstruct agreement upon a united plan. The requirement now becomes that every honest general must somehow agree on the same decision even in the presence of treacherous generals. In order to address this issue, honest, loyal generals must reach a majority agreement on their plan. Leslie Lamport introduced numerous fundamental ideas and techniques for distributed consensus. The famous Byzantine generals' problem was formulated by Lamport et al. In their paper, the Byzantine Generals Paper. In the digital world, generals are represented by computers, nodes, and communication links are messengers carrying messages. Disloyal generals are faulty nodes. Later in this chapter, we'll see how agreement can be achieved using consensus algorithms even in the presence of faults. Fault tolerance. A fundamental requirement in a consensus mechanism is that it must be fault tolerant. In other words, it must be able to tolerate a number of failures in a network and should continue to work even in the presence of faults. This naturally means that there has to be some limit to the number of faults a network can handle, since no network can operate correctly if a large majority of its nodes are failing. Based on the requirement of fault tolerance, consensus algorithms are also called fault-tolerant algorithms. There are two types of fault-tolerant algorithms. Types of fault-tolerant consensus. Fault-tolerant algorithms can be divided into two types of fault tolerance. The first is crash fault tolerance, CFT, and the other is Byzantine fault tolerance, BFT. CFT covers only crash faults, or in other words, benign faults. In contrast, BFT deals with the type of faults that are arbitrary and can even be malicious. Replication is a standard approach to make a system fault tolerant. Replication results in a synchronized copy of data across all nodes in a network. This technique improves the fault tolerance and availability of the network. This means that even if some of the nodes become faulty, the overall system network remains available due to the data being available on multiple nodes. There are two main types of replication techniques. Active replication, which is a type where each replica becomes a copy of the original state machine replica. Passive replication, which is a type where there is only a single copy of the state machine in the system kept by the primary node, and the rest of the nodes, replicas only, maintain the state. In this section, we've briefly looked at what replication is and its types. In the context of fault-tolerant consensus mechanisms, replication plays a vital role by introducing resiliency into the system. We'll now introduce another relevant concept, known as state machine replication, which is a standard technique used to achieve fault tolerance in distributed systems. State machine replication. State machine replication, SMR, is a de facto technique that is used to provide deterministic replication services in order to achieve fault tolerance in a distributed system. State machine replication was first proposed by Lamport in 1978 in his paper, time clocks, and the ordering of events in a distributed system. Later in 1990, Schneider formalized the state machine replication approach and published the results in a paper titled Implementing Fault-Tolerant Services Using the State Machine Approach. Now, just before we discuss SMR further, let's understand what a state machine is. At an abstract level, it is a mathematical model that is used to describe a machine that can be in different states. It is important to understand that a state machine can only have one state at a time. A state machine stores a state of the system and transitions it to the next state as a result of input received. As a result of state transition, an output is produced along with an updated state. The fundamental idea behind SMR can be summarized as follows. 1. All servers always start with the same initial state. 2. All servers receive requests in a totally ordered fashion, sequenced as generated from clients. 3. All servers produce the same deterministic output for the same input. State machine replication is implemented under a primary backup paradigm, where a primary node is responsible for receiving and broadcasting client requests. This broadcast mechanism is called total order broadcast or atomic broadcast, which ensures that backup or replica nodes receive and execute the same requests in the same sequence as the primary. Consequently, this means that all replicas will eventually have the same state as the primary, thus resulting in achieving consensus. In other words, this means that total order broadcast and distributed consensus are equivalent problems. If you solve one, the other is solved too. Now that we understand the basics of replication and fault tolerance, it is important to understand that fault tolerance works up to a certain threshold. For example, if a network has a vast majority of constantly failing nodes and communication links, it is not hard to understand that this type of network may not be as fault tolerant as we might like it to be. In other words, even in the presence of fault tolerant measures, if there is a lack of resources on a network, the network may still not be able to provide the required level of fault tolerance. In some scenarios, it might be impossible to provide the required services due to a lack of resources in a system. In distributed computing, such impossible scenarios are researched and reported as impossibility results. In distributed computing, impossibility results provide an understanding of whether a problem is solvable and the minimum resources required to do so. If the problem is unsolvable, then these results give a clear understanding that a specific task cannot be accomplished and no further research is necessary. From another angle, we can say that impossibility results, sometimes called unsolvability results, show that certain problems are not computable under insufficient resources. Impossibility results unfold deep aspects of distributed computing and enable us to understand why certain problems are difficult to solve and under what conditions a previously unsolved problem might be solved. The requirement of minimum available resources is known as lower bound results. The problems that are not solvable under any conditions are known as unsolvability results. For example, it has been proven that asynchronous deterministic consensus is impossible. This result is known as the FLP impossibility result, which we'll introduce next. FLP impossibility. FLP impossibility is a fundamental unsolvability result in distributed computing theory that states that in an asynchronous environment, the deterministic consensus is impossible, even if only one process is faulty. FLP is named after the authors' names, Fisher, Lynch, and Patterson, who in 1985 introduced this result. This result was presented in their paper, Impossibility of Distributed Consensus, with one faulty process. To circumvent FLP impossibility, several techniques have been introduced in the literature. These techniques include failure detectors, which can be seen as oracles associated with processors to detect failures. Randomized algorithms have been introduced to provide a probabilistic termination guarantee. The core idea behind the randomized protocols is that the processors in such protocols can make a random choice of decision value if the processor does not receive the required quorum of trusted messages. Synchrony assumptions, where additional synchrony and timing assumptions are made to ensure that the consensus algorithm terminates and makes progress. Now that we understand the fundamental impossibility result, let's look at another relevant result that highlights the unsolvability of consensus due to a lack of resources, that is, a lower bound result. We can think of lower bound as a minimum amount of resources, for example, the number of processors or communication links required to solve a problem. In other words, if a minimum required number of resources is not available in a system, then the problem cannot be solved. In the context of a consensus problem, a fundamental proven result is lower bounds on the number of processors, which we describe next. Lower bounds on the number of processors to solve consensus. As we described previously, there are proven results in distributed computing that state several lower bounds, for example, the minimum number of processors required for consensus or the minimum number of rounds required to achieve consensus. The most common and fundamental of these results is the minimum number of processors required for consensus. These results are listed below. In the case of CFT, at least 2f plus 1 number of nodes is required to achieve consensus. In the case of BFT, at least 3f plus 1 number of nodes is required to achieve consensus. F represents the number of failures. These lower bounds are discussed in several papers with relevant proofs. The most fundamental one is by Lamport et al., reaching agreement in the presence of faults. Another paper that provides a number of impossibility proofs is Easy Impossibility Proofs for Distributed Consensus Problems. Distributed computing. We have now covered the fundamentals of distributed consensus theory. Now we'll delve a little bit deeper into the analysis and design of consensus algorithms. Analysis and design. In order to analyze and understand a consensus algorithm, we need to define a model under which our algorithm will run. This model provides some assumptions about the operating environment of the algorithm and provides a way to intuitively study and reason about the various properties of the algorithm. In the following sections, we'll describe a model that is useful for describing and analyzing consensus mechanisms. Model. Distributed computing systems represent different entities in the system under a computational model. This computational model is a beneficial way of describing the system under some system assumptions. A computational model represents processes, network conditions, timing assumptions, and how all these entities interact and work together. We will now look at this model in detail and introduce all objects one by one. Processes. Processes communicate with each other by passing messages to each other. This is why these systems are called message-passing distributed systems. There is another class called shared memory, which we will not discuss here as we are only dealing with message-passing systems. Timing assumptions. There are also some timing assumptions that are made when designing consensus algorithms. Synchrony. In synchronous systems, there is a known upper bound on the communication and processor delays. Synchronous algorithms are designed to be run on synchronous networks. At a fundamental level, in a synchronous system, a message sent by a processor to another is received by the receiver in the same communication round as it is sent. Asynchrony. In asynchronous systems, there is no upper bound on the communication and processor delays. In other words, it is impossible to define an upper bound for communication and processor delays in asynchronous systems. Asynchronous algorithms are designed to run on asynchronous networks without any timing assumptions. These systems are characterized by the unpredictability of message transfer, communication delays, and processing delays. This scenario is common in large-scale geographically dispersed distributed systems and systems where the input load is unpredictable. Partial synchrony. In this model, there is an upper bound on the communication and processor delays. However, this upper bound is not known to the processors. Eventually, synchronous systems are a type of partial synchrony, which means that the system becomes synchronous after an instance of time called Global Stabilization Time, or GST. GST is not known to the processors. Generally, partial synchrony captures the fact that usually the systems are synchronous, but there are arbitrary but bounded asynchronous periods. Also, the system at some point is synchronous for long enough that processors can decide, achieve agreement, and terminate during that period. Now that we understand the fundamentals of the distributed consensus theory, let's look at two main classes of consensus algorithms. This categorization emerged after the invention of Bitcoin. Prior to Bitcoin, there's a long history of research in distributed consensus protocols. Classification. The consensus algorithms can be classified into two broad categories: traditional, voting-based consensus, lottery-based, Nakamoto and post-Nakamoto consensus. Traditional voting-based consensus has been researched in distributed systems for many decades. Many fundamental results and a lot of groundbreaking work have already been produced in this space. Algorithms like Paxos and PBFT are prime examples of such types of algorithms. Traditional consensus can also be called fault-tolerant distributed consensus. In other words, this is a class of consensus algorithms that existed before Bitcoin and has been part of distributed system research for almost 3 decades. Lottery-based or Nakamoto-type consensus was first introduced with Bitcoin. This class can also be simply called blockchain consensus. The fundamental requirements of consensus algorithms boil down to safety and liveness conditions. A consensus algorithm must be able to satisfy the safety and liveness properties. Safety is usually based on some safety requirements of the algorithms, such as agreement, validity, and integrity. Liveness means that the protocol can make progress even if the network conditions are not ideal. Now we'll define these terms separately. Safety. This requirement generally means that nothing bad happens. There are usually 3 properties within this class of requirements, which are listed as follows. Agreement. The agreement property requires that no 2 processes decide on different values. Validity. Validity states that if a process has decided a value, that value must have been proposed by a process. In other words, the decided value is always proposed by an honest process and has not been created out of thin air. Integrity. A process must be decided only once. Liveness. This requirement generally means that something good eventually happens. Termination. This liveness property states that each honest node must eventually decide on a value. With this, we have covered the classification and requirements of consensus algorithms. In the next section, we'll introduce various consensus algorithms, which we can evaluate using the consensus models covered in this section. Algorithms. In this section, we will discuss the key algorithms in detail. We'll be looking at the 2 main types of fault-tolerant algorithms, CFT and BFT. CFT algorithms. We'll begin by looking at some algorithms that solve the consensus problem with crash fault tolerance. One of the most fundamental algorithms in this space is Paxos. Paxos. Leslie Lamport developed Paxos. It is the most fundamental distributed consensus algorithm, allowing consensus over a value under unreliable communications. In other words, Paxos is used to build a reliable system that works correctly, even in the presence of faults. Paxos was proposed first in 1989 and then later more formally in 1998 in the following paper: The Part-Time Parliament, ACM Transactions on Computer Systems. Note that Paxos works under an asynchronous network model and supports the handling of only benign failures. This is not a Byzantine fault-tolerant protocol. However, later, a variant of Paxos was developed that provides Byzantine fault tolerance. The original paper in which a Byzantine fault-tolerant version of Paxos is described is available here. International Symposium on Distributed Computing. Paxos makes use of 2f+1 processes to ensure fault tolerance in a network where processes can crash fault, that is, experience benign failures. Benign failure means either the loss of a message or a process stops. In other words, Paxos can tolerate one crash failure in a 3-node network. Paxos is a 2-phase protocol. The first phase is called the prepare phase, and the next phase is called the accept phase. Paxos has proposer and acceptors as participants, where the proposer is the replicas or nodes that propose the values and acceptors are the nodes that accept the value. How Paxos works. The Paxos protocol assumes an asynchronous message passing network with less than 50% of crash faults. As usual, the critical properties of the Paxos consensus algorithm are safety and liveness. Under safety, we have agreement, which specifies that no two different values are agreed on. In other words, no two different learners learn different values. Validity, which means that only the proposed values are decided. In other words, the values chosen or learned must have been proposed by a processor. Under liveness, we have termination, which means that eventually the protocol is able to decide and terminate. In other words, if a value has been chosen, then eventually learners will learn it. Processes can assume different roles, which are listed as follows. Proposers. Elected leaders that can propose a new value to be decided. Acceptors, which participate in the protocol as a means to provide a majority decision. Learners, which are nodes that just observe the decision process and value. A single process in a Paxos network can assume all 3 roles. The key idea behind Paxos is that the proposer node proposes a value, which is considered final only if a majority of the acceptor nodes accept it. The learner nodes also learn this final decision. Paxos can be seen as a protocol that is quite similar to the 2-phase commit protocol. 2-phase commit, 2PC, is a standard atomic commitment protocol to ensure that transactions are committed in distributed databases only if all participants agree to commit. Even if a single node cannot agree to commit the transaction, it is fully rolled back. Similarly, in Paxos, in the first phase, the proposer sends a proposal to the acceptors. If and when they accept the proposal, the proposer broadcasts a request to commit to the acceptors. Once the acceptors commit and report back to the proposer, the proposal is considered final, and the protocol concludes. In contrast with the 2-phase commit, Paxos introduced ordering, sequencing to achieve total order, of the proposals and majority-based acceptance of the proposals instead of expecting all nodes to agree, to allow progress even if some nodes fail. Both of these improvements contribute toward ensuring the safety and liveness of the Paxos algorithm. We'll now describe how the Paxos protocol works step by step. 1. The proposer proposes a value by broadcasting a message. Prepare N to all acceptors. 2. Acceptors respond with an acknowledgement message if proposal N is the highest that the acceptor has responded to so far. The acknowledgement message, ACK-NVS, consists of 3 variables where N is the proposal number, V is the proposal value of the highest numbered proposal the acceptor has accepted so far, and S is the sequence number of the highest proposal accepted by the acceptor so far. This is where acceptors agree to commit the proposed value. The proposer now waits to receive acknowledgement messages from the majority of the acceptors indicating the chosen value. 3. If the majority is received, the proposer sends out the accept message, accept NV, to the acceptors. 4. If the majority of the acceptors accept the proposed value, now the accept message, then it is decided, that is, agreement is achieved. 5. Finally, in the learning phase, acceptors broadcast the accepted message, accepted N, V to the proposer. This phase is necessary to disseminate which proposal has been finally accepted. The proposer then informs all other learners of the decided value. Alternatively, learners can learn the decided value via a message that contains the accepted value, decision value, multicast by acceptors. We can visualize this process in the following diagram. Let's move on to see how Paxos achieves the much desired properties of safety and liveness. How Paxos achieves safety and liveness. A natural question arises about how Paxos ensures its safety and liveness guarantees. Paxos, at its core, is quite simple, yet it achieves all these properties efficiently. The actual proofs for the correctness of Paxos are quite in-depth and are not the subject of this chapter. However, the intuition behind each property is presented as follows. Agreement is ensured by enforcing that only one proposal can win votes from a majority of the acceptors. Validity is ensured by enforcing that only the genuine proposals are decided. In other words, no value is committed unless it is proposed in the proposal message first. Liveness or termination is guaranteed by ensuring that at some point during the protocol execution, eventually there is a period during which there is only one fault-free proposer. For detailed proofs and correctness analyses, refer to the following papers. Lamport L. 1998, The Part-Time Parliament. Lamport L. 2006, Fast Paxos. In summary, the key points to remember about Paxos are that, first, a proposer suggests a value with the aim that acceptors achieve agreement on it. The decided value is a result of majority consensus among the acceptors and is finally learned by the learners. There are many other protocols that have emerged from basic Paxos, such as multi-Paxos, fast Paxos, and cheap Paxos. Even though the Paxos algorithm is quite simple at its core, it is seen as challenging to understand, and many academic papers have been written to explain it. This slight problem, however, has not prevented it being implemented in many production networks, such as Google Spanner, as it has proven to be the most efficient protocol to solve the consensus problem. Nevertheless, there have been attempts to create alternative, easy-to-understand algorithms. Raft is such an attempt to create an easy-to-understand CFT algorithm. Raft. The Raft protocol is a CFT consensus mechanism developed by Diego Ongaro and John Ousterhout at Stanford University. In Raft, the leader is always assumed to be honest. At a conceptual level, it is replicated log for a replicated state machine, RSM, where a unique leader is elected every term, time division, whose log is replicated to all follower nodes. Raft is composed of three sub-problems. Leader election, a new leader election in case the existing one fails. Log replication, leader to follow log cinch. Safety, no conflicting log entries, index between servers. The Raft protocol ensures election safety, leader append only, log matching, leader completeness, and state machine safety. Each server in Raft can have either a follower, leader, or candidate state. The protocol ensures election safety, that is, only one winner each election term, and liveness, that is, some candidate must eventually win. How Raft works. The following steps will describe how the Raft protocol functions. At a fundamental level, the protocol is quite simple and can be described simply by the following sequence. Node starts up, leader election, log replication. 1. First, the node starts up. 2. After this, the leader election process starts. Once a node is elected as leader, all changes go through that leader. 3. Each change is entered into the node's log. 4. Log entry remains uncommitted until the entry is replicated to follower nodes and the leader receives right confirmation votes from a majority of the nodes. Then it is committed locally. 5. The leader notifies the followers regarding the committed entry. 6. Once this process ends, agreement is achieved. The state transition of the Raft algorithm can be visualized in the following diagram. We saw earlier that data is eventually replicated across all nodes in a consensus mechanism. In Raft, the log data is eventually replicated across all nodes. We describe this process of log replication next. Log replication. Log replication logic can be visualized in the following diagram. The aim of log replication is to synchronize nodes with each other. Log replication is a simple mechanism. As shown in the preceding diagram, the leader is responsible for log replication. Once the leader has a new entry in its log, it sends out the request to replicate to the follower nodes. When the leader receives enough confirmation votes back from the follower nodes indicating that the replicate request has been accepted and processed by the followers, the leader commits that entry to its local state machine. At this stage, the entry is considered committed. With this, our discussion on CFT algorithms is complete. Now we'll introduce Byzantine fault-tolerant algorithms, which have been a research area for many years in distributed computing. BFT algorithms. We described the formulation of the Byzantine generals problem at the start of this chapter. In this section, we'll introduce the mechanisms that were developed to solve the Byzantine generals' consensus in the presence of faults problem. Practical Byzantine fault tolerance. Practical Byzantine fault tolerance, PBFT, was developed in 1999 by Miguel Castro and Barbara Liskov. PBFT, as the name suggests, is a protocol developed to provide consensus in the presence of Byzantine faults. Before PBFT, Byzantine fault tolerance was considered impractical. With PBFT, it was demonstrated for the first time that practical Byzantine fault tolerance is possible. PBFT comprises three sub-protocols called normal operation, view change, and checkpointing. Normal operation subprotocol refers to a scheme that is executed when everything is running normally and no errors are in the system. View change is a subprotocol that runs when a faulty leader node is detected in the system. Checkpointing is another subprotocol, which is used to discard the old data from the system. The PBFT protocol comprises three phases or steps. These phases run in a sequence to achieve consensus. These phases are pre-prepare, prepare, and commit, which we will cover in detail shortly. The protocol runs in rounds where in each round, an elected leader node, called the primary node, handles the communication with the client. In each round, the protocol progresses through the three previously mentioned phases. The participants in the PBFT protocol are called replicas, where one of the replicas becomes primary as a leader in each round, and the rest of the nodes act as backups. PBFT is based on the SMR protocol introduced earlier. Here, each node maintains a local log, and the logs are kept in sync with each other via the consensus protocol, that is, PBFT. As we saw earlier, in order to tolerate Byzantine faults, the minimum number of nodes required is n equals 3f plus 1, where n is the number of nodes and f is the number of faulty nodes. PBFT ensures Byzantine fault tolerance as long as the number of nodes in a system stays n greater than equals 3f plus 1. We will now look at how the PBFT protocol works. In summary, when a client sends a request to a primary, the protocol initiates a sequence of operation between replicas, which eventually leads to consensus and a reply back to the client. These sequences of operations are divided into different phases: pre-prepare, prepare, commit. In addition, each replica maintains a local state comprising three main elements: service state, a message log, a number representing that replica's current view. Now we'll discuss the phases mentioned above one by one, starting with pre-prepare. Pre-prepare. This is the first phase in the protocol, where the primary node or primary receives a request from the client. The primary node assigns a sequence number to the request. It then sends the pre-prepare message with the request to all backup replicas. When the pre-prepare message is received by the backup replicas, it checks a number of things to ensure the validity of the message. First, whether the digital signature is valid. After this, whether the current view number is valid. Then, that the sequence number of the operations request message is valid. Finally, if the digest hash of the operations request message is valid. If all of these elements are valid, then the backup replica accepts the message. After accepting the message, it updates its local state and progresses toward the prepare phase. Prepare. A prepare message is sent by each backup to all other replicas in the system. Each backup waits for at least 2f+1 prepare messages to be received from other replicas. They also check whether the prepare message contains the same view number, sequence number, and message digest values. If all these checks pass, then the replica updates its local state and progresses toward the commit phase. Commit. In the commit phase, each replica sends a commit message to all other replicas in the network. The same as the prepare phase, replicas wait for 2f+1 commit messages to arrive from other replicas. The replicas also check the view number, sequence number, and message digest values. If they are valid for 2f+1 commit messages received from other replicas, then the replica executes the request, produces a result, and finally updates its state to reflect the commit. If there are already some messages queued up, the replica will execute those requests first before processing the latest sequence numbers. Finally, the replica sends the result to the client in a reply message. The client accepts the result only after receiving 2f+1 reply messages containing the same result. Now let's move on and look at how PBFT works in some more detail. How PBFT works. At a high level, the protocol works as follows. 1. A client sends a request to invoke a service operation in the primary. 2. The primary multicasts the request to the backups. 3. Replicas execute the request and send a reply to the client. 4. The client waits for replies from different replicas with the same result. This is the result of the operation. Now we'll describe each phase of the protocol: pre-prepare, prepare, and commit in more formal terms. The pre-prepare subprotocol algorithm. 1. Accepts a request from the client. 2. Assigns the next sequence number. 3. Sends the pre-prepare message to all backup replicas. The prepare subprotocol algorithm. 1. Accepts the pre-prepare message. If the backup has not accepted any pre-prepare messages for the same view or sequence number, then it accepts the message. 2. Sends the prepare message to all replicas. The commit subprotocol algorithm. 1. The replica waits for 2f prepare messages with the same view, sequence, and request. 2. Sends a commit message to all replicas. 3. Waits until a 2f+1 valid commit message arrives and is accepted. 4. Executes the received request. 5. Sends a reply containing the execution result to the client. In summary, the primary purpose of these phases is to achieve consensus, where each phase is responsible for a critical part of the consensus mechanism, which, after passing through all phases, eventually ends up achieving consensus. One key point to remember about each phase is listed as follows. Pre-prepare. This phase assigns a unique sequence number to the request. We can think of it as an orderer. Prepare. This phase ensures that honest replicas, nodes in the network, agree on the total order of requests within a view. Note that the pre-prepare and prepare phases together provide the total order of the message. Commit. This phase ensures that honest replicas, nodes in the network, agree on the total order of requests across views. The normal view of the PBFT protocol can be visualized as shown as follows. During the execution of the protocol, the integrity of the messages and protocol operations must be maintained to provide an adequate level of security and assurance. This is maintained by the use of digital signatures. In addition, certificates are used to ensure the adequate majority of participants, nodes, Note that these certificates are not usual digital certificates commonly used in PKI and IT infrastructures to secure assets, such as servers. We'll describe the concept of certificates next. Certificates in PBFT. Certificates in PBFT protocols are used to demonstrate that at least 2F+1 nodes have stored the required information. In other words, the collection of 2F+1 messages of a particular type is considered a certificate. For example, if a node has collected 2F+1 messages of type prepare, then combining it with the corresponding pre-prepare message with the same view, sequence, and request represents a certificate called a prepared certificate. Similarly, a collection of 2F+1 commit messages is called a commit certificate. There are also a number of variables that the PBFT protocol maintains in order to execute the algorithm. These variables and the meanings of these are listed as follows. We can now look at the types of messages and their formats, which becomes quite easy to understand if we refer to the preceding variables table shown. Types of messages. The PBFT protocol works by exchanging several messages. A list of these messages is presented as follows with their format and direction. The following table contains message types and relevant details. Let's look at some specific types that are exchanged during the PBFT protocol. View change. View change occurs when a primary is suspected faulty. This phase is required to ensure protocol progress. With the view change subprotocol, a new primary is selected, which then starts normal mode operation again. The new primary is selected in a round-robin fashion. When a backup replica receives a request, it tries to execute it after validating the message. But for some reason, if it does not execute it for a while, the replica times out and initiates the view change subprotocol. In the view change protocol, the replica stops accepting messages related to the current view and updates its state to view change. The only messages it can receive in this state are checkpoint messages, view change messages, and new view messages. After that, it sends a view change message with the next view number to all replicas. When this message arrives at the new primary, the primary waits for at least 2F view change messages for the next view. If at least 2F view change messages are received, it broadcasts a new view message to all replicas and progresses toward running normal operation mode once again. When other replicas receive a new view message, they update their local state accordingly and start normal operation mode. The algorithm for the view change protocol is shown as follows. 1. Stop accepting pre-prepare, prepare, and commit messages for the current view. 2. Create a set of all the certificates prepared so far. 3. Broadcast a view change message with the next view number and a set of all the prepared certificates to all replicas. The view change protocol can be visualized in the following diagram. The view change subprotocol is a mechanism to achieve liveness. 3 smart techniques are used in this subprotocol to ensure that eventually there is a time when the requested operation executes. 1. A replica that has broadcast the view change message waits for 2F+1 view change messages and then starts its timer. If the timer expires before the node receives a new view message for the next view, the node will start the view change for the next sequence but will increase its timeout value. This will also occur if the replica times out before executing the new unique request in the new view. 2. As soon as the replica receives F+1 view change messages for a view number greater than its current view, the replica will send a view change message for the smallest view it knows of in the set so that the next view change does not occur too late. This is also the case even if the timer has not expired. It will still send the view change for the smallest view. 3. As soon as the view change will only occur if at least F+1 replicas have sent the view change message, this mechanism ensures that a faulty primary cannot indefinitely stop progress by successively requesting view changes. Next, let's look in more detail at the checkpoint subprotocol, another important PBFT process. The checkpoint subprotocol.
Checkpointing is a crucial sub-protocol. It is used to discard old messages in the log of all replicas. With this, the replicas agree on a stable checkpoint that provides a snapshot of the global state at a certain point in time. This is a periodic process carried out by each replica after executing the request and marking that as a checkpoint in its log. A variable called low watermark in PBFT terminology is used to record the sequence number of the last stable checkpoint. This checkpoint is then broadcast to other nodes. As soon as a replica has at least 2f+1 checkpoint messages, it saves these messages as proof of a stable checkpoint. It discards all previous prepare, and commit messages from its logs. PBFT advantages and disadvantages. PBFT is indeed a revolutionary protocol that has opened up a new research field of practical, Byzantine fault-tolerant protocols. The original PBFT does have some strength, but it does have some limitations. We'll discuss most of the commonly cited strengths and limitations in the following section. Strengths. PBFT provides immediate and deterministic transaction finality. This is in contrast with the POW protocol, where a number of confirmations are required to finalize a transaction with high probability. PBFT is also energy efficient as compared to POW, which consumes a tremendous amount of electricity. Weaknesses. PBFT is not very scalable. This is the reason it is more suitable for consortium networks instead of public blockchains. It is, however, much faster than POW protocols. Sybil attacks can be carried out on a PBFT network, where a single entity can control many identities to influence the voting and subsequently the decision. However, the fix is trivial and, in fact, this is not very practical in consortium networks where all identities are known on the network. This problem can be addressed simply by increasing the number of nodes in the network. PBFT and blockchain. In the traditional client-server model, PBFT works well. However, in the case of blockchain, directly implementing PBFT in its original state may not work correctly. This is because PBFT's original design was not developed for blockchain. In the following section, we present a few changes that are required to create a blockchain version of PBFT. This is not an exhaustive list, however, it does provide a baseline of requirements. This research resulted in IBFT and PBFT implementation in Sawtooth and other blockchains. In all these scenarios, some changes have been made in the core protocol to ensure that they are compatible with the blockchain environment. PBFT has been implemented in Hyperledger Sawtooth. We will now introduce an algorithm called IBFT, which was inspired by PBFT. Another algorithm that has been inspired by PBFT and DLS is Tendermint, which we will also present shortly. Istanbul Byzantine Fault Tolerance. IBFT was developed by AMIS Technologies as a variant of PBFT suitable for blockchain networks. It was presented in EIP 650 for the Ethereum blockchain. The differences between PBFT and IBFT. Let's first discuss the primary differences between the PBFT and IBFT protocols. They are as follows. There is no distinctive concept of a client in IBFT. Instead, the proposer can be seen as a client, and in fact, all validators can be considered clients. There is a concept of dynamic validators, which is in contrast with the original PBFT, where the nodes are static. However, in IBFT, the validators can be voted in and out as required. There are two types of nodes in an IBFT network, nodes and validators. Nodes are synchronized with the blockchain without participating in the IBFT consensus process. In contrast, validators are the nodes that participate in the IBFT consensus process. IBFT relies on a more straightforward structure of view change, round change messages as compared to PBFT. In contrast with PBFT, in IBFT there is no concrete concept of checkpoints. However, each block can be considered an indicator of the progress so far. The chain height. There is no concept of garbage collection in IBFT. Now we've covered the main points of comparison between the two BFT algorithms. We'll examine how the IBFT protocol runs and its various phases. How IBFT works. IBFT assumes a network model under which it is supposed to run. The model is composed of at least 3F+1 processes, standard BFT assumption, a partially synchronous message passing network, and sound cryptography. By sound cryptography, it is assumed that digital signatures and relevant cryptographic protocols such as cryptographic hash functions are secure. The IBFT protocol runs in rounds. It has 3 phases: pre-prepare, prepare, and commit. In each round, usually a new leader is elected based on a round-robin mechanism. The following flowchart shows how the IBFT protocol works. In the preceding diagram, the flow of IBFT is shown. We'll discuss this process step by step in the following section. 1. The protocol starts with a new round. In the new round, the selected proposer broadcasts a proposal block as a pre-prepare message. 2. The nodes that receive this pre-prepare message validate the message and accept it if it is a valid message. The nodes also then set their state to pre-prepared. 3. At this stage, if a timeout occurs or a proposal is seen as invalid by the nodes, they will initiate a round change. The normal process then begins again with a proposer proposing a block. 4. Nodes then broadcast the prepare message and wait for 2F+1 prepare messages to be received from other nodes. If the nodes do not receive 2F+1 messages in time, then they time out, and the round change process starts. The nodes then set their state to prepared after receiving 2F+1 messages from other nodes. 5. Finally, the nodes broadcast a commit message and wait for 2F+1 messages to arrive from other nodes. If they are received, then the state is set to committed. Otherwise, timeout occurs and the round change process starts. 6. Once committed, block insertion is tried. If it succeeds, the protocol proceeds to the final committed state and eventually a new round starts. If insertion fails for some reason, the round change process triggers. Again, nodes wait for 2F+1 round change messages, and if the threshold of the messages is received, then round change occurs. Now that we've understood the flow of IBFT, let's now further explore which states it maintains and how. Consensus states. IBFT is an SMR algorithm. Each validator maintains a state machine replica in order to reach block consensus, that is, agreement. These states are listed as follows with an explanation. New round. In this state, a new round of the consensus mechanism starts, and the selected proposer sends a new block proposal to other validators. In this state, all other validators wait for the pre-prepare message. Pre-prepared. A validator transitions to this state when it has received a pre-prepare message and broadcasts a prepare message to other validators. The validator then waits for 2F+1 prepare or commit messages. Prepared. This state is achieved by a validator when it has received 2F+1 prepare messages and has broadcast the commit messages. The validator then awaits 2F+1 commit messages to arrive from other validators. Committed. The state indicates that a validator has received 2F+1 commit messages. The validator at this stage can insert the proposed block into the blockchain. Final committed. This state is achieved by a validator when the newly committed block is inserted successfully into the blockchain. At this state, the validator is also ready for the next round of consensus. Round change. This state indicates that the validators are waiting for 2f+1 round change messages to arrive for the newly proposed new round number. The IBFT protocol can be visualized using a diagram similar to PBFT as follows. An additional mechanism that makes IBFT quite appealing is its validator management mechanism. By using this mechanism, validators can be added or removed by voting between members of the network. This is quite a useful feature and provides the right level of flexibility when it comes to managing validators efficiently, instead of manually adding or removing validators from the validator set. IBFT has been implemented in several blockchains. Sample implementations include Quorum and Celo. A Quorum implementation is available at the following link. IBFT with some variations has also been implemented in the Celo blockchain. Several other algorithms have been inspired by PBFT and have emerged as a result of deep interest in blockchain research. One such algorithm is Tendermint. Tendermint is another variant of PBFT. It was inspired by both the DLS and PBFT protocols. Tendermint also makes use of the SMR approach to providing consensus. As we saw before, state machine replication is a mechanism that allows synchronization between replicas nodes of the network. Traditionally, a consensus mechanism used to run with a small number of participants, and thus performance and scalability was not a big concern. However, with the advent of blockchain, there is a need to develop algorithms that can work on wide area networks and in asynchronous environments. Research into these areas of distributed computing is not new, and especially now, due to the rise of cryptocurrencies and blockchain. The interest in these research topics has grown significantly in the last few years. The Tendermint protocol also works by running rounds. In each round, a leader is elected, which proposes the next block. Also note that in Tendermint, the round change or view change processes is part of the normal operation, as opposed to PBFT, where view change only occurs in the event of errors, that is, a suspected faulty leader. Tendermint works similarly to PBFT, where 3 phases are required to achieve a decision. Once a round is complete, a new round starts with 3 phases and terminates when a decision is reached. A key innovation in Tendermint is the design of a new termination mechanism, as opposed to other PBFT-like protocols. Tendermint has developed a more straightforward mechanism, which is similar to PBFT-style normal operation. Instead of having 2 sub-protocols for normal mode and view change mode, recovery in event of errors, Tendermint terminates without any additional communication cost. The model under which Tendermint is supposed to run will now be presented. We saw earlier in the introduction that each consensus model is studied and developed under a system model with some assumptions about the system. Tendermint is also designed with a system model in mind. Now we'll define and introduce each element of the system model. Processes. A process is the fundamental key participant of the protocol. It is also called a replica. In PBFT traditional literature, a node or merely a process. Processes can be correct or honest. Processes can also be faulty or Byzantine. Each process possesses some voting power. Also note that processes are not necessarily connected directly. They are only required to connect loosely or just with their intermediate subset of processes nodes. Processes have a local timer that they use to measure timeout. The network model is a network of processes that communicate using messages. In other words, the network model is a set of processes that communicate using message passing. Particularly, the gossip protocol is used for communication between processes. The standard assumption of n greater than equal 3f plus 1 BFT is also taken into consideration. This means that the protocol operates correctly as long as the number of nodes in the network is more than 3f, where f is the number of faulty nodes. This implies that, at a minimum, there have to be 4 nodes in a network to tolerate Byzantine faults. Timing assumptions. Under the network model, Tendermint assumes a partially synchronous network. This means that there is an unknown bound on the communication delay.
but it only applies after an unknown instance of time is called Global Stabilization Time, or GST. Security and cryptography. It is assumed that the public key cryptography used in the system is secure and the impersonation or spoofing of accounts' identities is not possible. The messages on the network are authenticated and verified via digital signatures. The protocol ignores any messages with an invalid digital signature. State machine replication. To achieve replication among the nodes, the standard SMR mechanism is used. One key observation that is fundamental to the protocol is that in SMR it is ensured that all replicas on the network receive and process the same sequence of requests. As noted in the Tendermint paper, agreement and order are two properties that ensure that all requests are received by replicas, and order ensures that the sequence in which the replicas have received requests is the same. Both of these requirements ensure total order in the system. Also, Tendermint ensures that requests themselves are valid and have been proposed by the clients. In other words, only valid transactions are accepted and executed on the network. There are three fundamental consensus properties that Tendermint solved. As we discussed earlier in the chapter, generally in a consensus problem, there are safety and liveness properties that are required to be met. Similarly, in Tendermint, these safety and liveness properties consist of agreement, termination, and validity. These properties are defined as follows. Agreement. No two correct processes decide on different values. Termination. All correct processes eventually decide on a value. Validity. A decided upon value is valid. That is, it satisfies the predefined predicate denoted, valid. Now we'll describe how the algorithm works. State transition in Tendermint is dependent on the messages received and timeouts. In other words, the status change in response to messages received by a processor or in the event of timeouts. The timeout mechanism ensures liveness and prevents endless waiting. It is assumed that eventually, after a period of asynchrony, there will be a round or communication period during which all processes can communicate in a timely fashion, which will ensure that processes eventually decide on a value. The following diagram depicts the Tendermint protocol at a high level. Types of messages in Tendermint. There are three types of messages in Tendermint. We'll discuss each type individually here. 1. Proposal. As the name suggests, this is used by the leader of the current round to propose a value or block. 2. Pre-vote. This message is used to vote on a proposed value. 3. Pre-commit. This message is also used to vote on a proposed value. These messages can be considered somewhat equivalent to PBFT's pre-prepare, prepare, and commit messages. All of the aforementioned messages also have a corresponding timeout mechanism, which ensures that processes do not end up waiting indefinitely for some conditions to meet. If a processor cannot decide in an expected amount of time, it will time out and trigger a round change. Each type of message has an associated timeout. As such, there are 3 timeouts in Tendermint, corresponding to each message type. 1. Timeout propose. 2. Timeout pre-vote. 3. Timeout pre-commit. These timeout mechanisms prevent the algorithm from waiting infinitely for a condition to be met. They also ensure that processes progress through the rounds. A clever mechanism to increase timeout with every new round ensures that after reaching GST, eventually the communication between correct processes becomes reliable and a decision can be reached. State variables. All processes in Tendermint maintain a set of variables, which helps with the execution of the algorithm. Each of these variables holds critical values, which ensure the correct execution of the algorithm. These variables are listed and discussed as follows. Step. The step variable holds information about the current state of the algorithm, that is, the current state of the Tendermint state machine in the current round. Locked value. The locked value variable stores the most recent value with respect to a round number, for which a pre-commit message has been sent. Locked round. The locked round variable contains information about the last round in which the process sent a non-nil pre-commit message. This is the round where a possible decision value has been locked. This means that if a proposal message and corresponding 2f+1 messages have been received for a value in a round, then due to the reason that 2f+1 pre-votes have already been received for this value. This is the possible decision value. Valid value. The role of the valid value variable is to store the most recent possible decision value. Valid round. The valid round variable is the last round in which valid value was updated. Apart from the preceding variables, a process also stores the current consensus instance called height in Tendermint and the current round number. These variables are attached to every message. A process also stores an array of decisions. Tendermint assumes a sequence of consensus instances, one for each height. How Tendermint works. Tendermint works in rounds, and each round comprises phases: propose, pre-vote, pre-commit, and commit. In this section, we'll explore how Tendermint works. 1. Every round starts with a proposal value being proposed by a proposer. The proposer can propose any new value at the start of the first round for each height. 2. After the first round, any subsequent rounds will have the proposer, which proposes a new value only if there is no value present, that is, null. Otherwise, the valid value, that is, the possible decision value, is proposed, which has already been locked in a previous round. The proposal message also includes a value of valid round, which denotes the last round in which there was a valid value updated. 3. The proposal is accepted by a correct process only if 1. The proposed value is valid, 2. The process has not locked on a round, 3. Or the process has a value locked. 4. If the preceding conditions are met, then the correct process will accept the proposal and send a pre-vote message. 5. If the preceding conditions are not met, then the process will send a pre-vote message with a nil value. 6. In addition, there is also a timeout mechanism associated with the proposal phase, which initiates timeout if a process has not sent a pre-vote message in the current round or the timer expires in the proposal stage. 7. If a correct process receives a proposal message with a value and 2f+1 pre-vote messages, then it sends the pre-commit message. 8. Otherwise, it sends out a nil pre-commit. 9. A timeout mechanism associated with the pre-commit will initialize if the associated timer expires or if the process has not sent a pre-commit message after receiving a proposal message and 2f+1 pre-commit messages. 10. A correct process decides on a value if it has received the proposal message in some round and 2f+1 pre-commit messages for the ID of the proposed value. 11. There is also an associated timeout mechanism with this step, which ensures that the processor does not wait indefinitely to receive 2f+1 messages. If the timer expires before the processor can decide, the processor starts the next round. 12. When a processor eventually decides, it triggers the next consensus instance for the next block proposal, and the entire process of proposal, pre-vote, and pre-commit starts again. The process is as simple as the flow shown here: proposal, pre-vote, pre-commit. We can visualize the protocol flow with the diagram shown here. Now we'll discuss how the termination mechanism works in Tendermint. A new termination mechanism has been introduced in Tendermint. For this purpose, there are two variables, namely valid value and valid round, which are used by the proposal message. Both of these variables are updated by a correct process when the process receives a valid proposal message and subsequent corresponding 2f+1 pre-vote messages. This process works by utilizing the gossip protocol, which ensures that if a correct process has locked a value in a round, all correct processes will then update their valid value and valid round variables, with the locked values by the end of the round during which they have been locked. The key idea is that once these values have been locked by a correct processor, they will be propagated to other nodes within the same round, and each processor will know the locked value and round, that is, the valid values. Now, when the next proposal is made, the locked values will be picked up by the proposer, which have already been locked as a result of the valid proposal and corresponding 2f+1 pre-vote messages. This way it can be ensured that the value that processes eventually decide upon is acceptable as specified by the validity conditions described above. Tendermint implementation. Tendermint is developed in Go. It can be implemented in various different scenarios. The source code is available at github.com/tendermint/tendermint. It is released as Tendermint Core, which is a language-agnostic programming middleware that takes a state transition machine and replicates it on many machines. Tendermint Core is available here, tendermint.com/core. The algorithms discussed so far are variants of traditional Byzantine fault-tolerant algorithms. Now we'll introduce the protocols that are specifically developed for blockchain protocols. A prime example is, of course, POW, which was first introduced with Bitcoin. Nakamoto Consensus. Nakamoto Consensus, or POW, was first introduced with Bitcoin in 2009. Since then, it has stood the test of time and is the longest-running blockchain network. This test of time is a testament to the efficacy of the POW consensus mechanism. Now we will explore how POW works. At a fundamental level, the POW mechanism is designed to mitigate Sybil attacks, which facilitates consensus and the security of the network. A Sybil attack is a type of attack that aims to gain a majority influence on the network to control the network. Once a network is under the control of an adversary, any malicious activity could occur. A Sybil attack is usually conducted by a node generating and using multiple identities on the network. If there are enough multiple identities held by an entity, then that entity can influence the network by skewing majority-based network decisions. The majority in this case is held by the adversary. It is quite easy to obtain multiple identities and try to influence the network. However, in Bitcoin, due to the hashing power requirements, this attack is mitigated. How POW works. In a nutshell, POW works as follows. POW makes use of hash puzzles. A node proposes a block has to find a nonce such that H nonce previous hash TX less than threshold value. The process can be summarized as follows. New transactions are broadcast to all nodes on the network. Each node collects the transactions into a candidate block. Miners propose new blocks. Miners concatenate and hash with the header of the previous block. The resultant hash is checked against the target value, that is, the network difficulty target value. If the resultant hash is less than the threshold value, then POW is solved. Otherwise, the nonce is incremented and the node tries again. This process continues until a resultant hash is found that is less than the threshold value. We can visualize how POW works with the diagram shown here. POW as a solution to the Byzantine general's problem. The original posting on this by Satoshi Nakamoto can be found here, satoshi.nakamotoinstitute.org/email/cryptography/11. The key idea behind POW as a solution to the Byzantine general's problem is that all honest generals, miners in the Bitcoin world, achieve agreement on the same state, decision value. As long as honest participants control the majority of the network, POW solves the Byzantine general's problem. Note that this is a probabilistic solution and not deterministic. Nakamoto versus traditional consensus. Nakamoto consensus was the first of its kind. It solved the consensus problem, which had been traditionally solved using pre-Bitcoin protocols like PBFT. A natural question that arises is, are there any similarities between the Nakamoto world and traditional distributed consensus? The short answer is yes.
because we can map the properties of POW consensus to traditional Byzantine consensus. This mapping is useful to understand what properties of traditional consensus can be applied to the Nakamoto world and vice versa. In traditional consensus algorithms, we have agreement, validity, and liveness properties, which can be mapped to Nakamoto-specific properties of the common prefix, chain quality, and chain growth properties, respectively. The common prefix property means that the blockchain hosted by honest nodes will share the same large common prefix. If that is not the case, then the agreement property of the protocol cannot be guaranteed, meaning that the processors will not be able to decide and agree on the same value. The chain quality property means that the blockchain contains a certain required level of correct blocks created by honest nodes, miners. If chain quality is compromised, then the validity property of the protocol cannot be guaranteed. This means that there is a possibility that a value will be decided that is not proposed by a correct process, resulting in safety violation. The chain growth property simply means that new correct blocks are continuously added to the blockchain. If chain growth is impacted, then the liveness property of the protocol cannot be guaranteed. This means that the system can deadlock or fail to decide on a value. Variants of POW. There are two main variants of POW algorithms, based on the type of hardware used for their processing. CPU-bound POW. CPU-bound POW refers to a type of POW where the processing required to find the solution to the cryptographic hash puzzle is directly proportional to the calculation speed of the CPU or hardware, such as ASICs. Because ASICs have dominated the Bitcoin POW and provide somewhat undue advantage to the miners who can afford to use ASICs, this CPU-bound POW is seen as shifting toward centralization. Moreover, mining pools with extraordinary hashing power can shift the balance of power towards them. Therefore, memory-bound POW algorithms have been introduced, which are ASIC-resistant and are based on memory-oriented design instead of CPU. Memory-bound POW. Memory-bound POW algorithms rely on system, RAM, to provide POW. Here the performance is bound by the access speed of the memory or the size of the memory. This reliance on memory also makes these POW algorithms ASIC resistant. Equihash is one of the most prominent memory-bound POW algorithms. POW consumes tremendous amounts of energy. As such, there are several alternatives suggested by researchers. One of the first alternatives proposed is POS. Proof of Stake, POS. POS is an energy-efficient alternative to the POW algorithm, which consumes an enormous amount of energy. POS was first used in Peercoin, and now prominent blockchains such as EOS, NXT, Steem, and Tezos are using POS algorithms. Ethereum, with its Serenity release, will soon transition to a PO-based consensus mechanism. The stake represents the number of coins, money in the consensus protocol, staked by a blockchain participant. The key idea is that if someone has a stake in the system, then they will not try to sabotage the system. Generally speaking, the chance of proposing the next block is directly proportional to the value staked by the participant. However, there are a few intricate variations, which we will discuss shortly. There are different variations of POS, such as chain-based POS, committee-based POS, BFT-based POS, delegated POS, leased POS, and master node POS. In POS systems, there is no concept of mining in the traditional Nakamoto consensus sense. However, the process related to earning revenue is sometimes called virtual mining. A POS miner is called either a validator, minter, or stakeholder. The right to win the next proposer role is usually assigned randomly. Proposers are rewarded either with transaction fees or block rewards. Similar to POW, control over the majority of the network in the form of the control of a large portion of the stake
is required to attack and control the network. POS mechanisms generally select a stakeholder and grant appropriate rights to it based on their staked assets. The stake calculation is application-specific, but generally is based on balance, deposit value, or voting among the validators. Once the stake is calculated and a stakeholder is selected to propose a block, the block proposed by the proposer is readily accepted. The probability of selection increases with a higher stake. In other words, the higher the stake, the better the chances of winning the right to propose the next block. How POS works. In the preceding diagram, a generic POS mechanism is shown where a stake calculator function is used to calculate the amount of stake funds and, based on that, select a new proposer. Types of POS. There are several types of POS algorithm. Chain-based POS. This mechanism is very similar to POW. The only change from the POW mechanism is the block generation method. A block is generated in 2 steps by following a simple protocol. Transactions are picked up from the memory pool and a candidate block is created. A clock is set up with a constant tick interval, and at each clock tick, whether the hash of the block header concatenated with the clock time is less than the product of the target value and stake value is checked. This process can be shown in a simple formula. Hash B clock time less than target X stake value. The stake value is dependent on the way the algorithm is designed. In some systems, it is directly proportional to the amount of stake, and in others, it is based on the amount of time the stake has been held by the participant, also called coinage. The target is the mining difficulty per unit of the value of stake. This mechanism still uses hashing puzzles as in POW, but instead of competing to solve the hash puzzle by consuming a high amount of electricity and specialized hardware, the hashing puzzle in POS is solved at regular intervals based on the clock tick. A hashing puzzle becomes easier to solve if the stake value of the minter is high. Peercoin was the first blockchain to implement POS. Committee-based POS. In this scheme, a group of stakeholders is chosen randomly, usually by using a verifiable random function, VRF. This VRF, once invoked, produces a random set of stakeholders based on their stake and the current state of the blockchain. The chosen group of stakeholders becomes responsible for proposing blocks in sequential order. This mechanism is used in the Ouroboros POS consensus mechanism, which is used in Cardano. More details on this are available here. Delegated POS. DPoS is very similar to committee-based POS, but with one crucial difference. Instead of using a random function to derive the group of stakeholders, the group is chosen by stake delegation. The group selected is a fixed number of minters that create blocks in a round-robin fashion. Delegates are chosen via voting by network users. Votes are proportional to the amount of the stake that participants have on the network. This technique is used in Lisk, Cosmos, and EOS. DPoS is not decentralized as a small number of known users are made responsible for proposing and generating blocks. Hot Stuff. Hot Stuff is the latest class of PBFT protocol with a number of optimizations. There are several changes in Hot Stuff that make it a different and in some ways better protocol than traditional PBFT. Hot Stuff was introduced by VMware Research in 2018. Later it was presented at the Symposium on Principles of Distributed Computing. There are 3 key properties that Hot Stuff has addressed. These properties are listed as follows. Linear view change. Linear view change results in reduced communication complexity. It is achieved by the algorithm where after GST is reached, a current designated leader will send only ON authenticators, either a partial, signature, or signature, to reach consensus. In the worst case, where leaders fail successively, the communication cost is O(n squared), a quadratic. In simpler words, quadratic complexity means that the performance of the algorithm is proportional to the squared size of the input. Optimistic responsiveness. Optimistic responsiveness ensures that any correct leader after GST is reached only requires the first n-f responses to ensure progress. Chain quality. This property ensures fairness and liveness in the system by allowing fast and frequent leader rotation. Another innovation in Hot Stuff is the separation of safety and liveness mechanisms. The separation of concerns allows better modularity, cleaner architecture, and control over the development of these features independently. Safety is ensured through voting and commit rules for participant nodes in the network. Liveness, on the other hand, is the responsibility of a separate module called Pacemaker, which ensures a new, correct, and unique leader is elected. In comparison with traditional PBFT, Hot Stuff has introduced several changes which result in improved performance. PBFT-style protocols work using a mesh communication topology, where each message is required to be broadcast to other nodes on the network. In Hot Stuff, the communication has been changed to the star topology, which means that nodes do not communicate with each other directly, but all consensus messages are collected by a leader and then broadcast to other nodes. This immediately results in reduced communication complexity. A question arises here: what happens if the leader somehow is corrupt or compromised? This issue is solved by the same BFT tolerance rules where, if a leader proposes a malicious block, it will be rejected by other honest validators and a new leader will be chosen. This scenario can slow down the network for a limited time until a new honest leader is chosen, but eventually, as long as a majority of the network is honest, an honest leader will be chosen which will propose a valid block. Also, for further protection, usually the leader node is usually with each block, rotated between validators, which can neutralize any malicious attacks targeting the network. This property ensures fairness, which helps to achieve chain quality, introduced previously. However, note that there is one problem in this scheme where if the leader becomes too overloaded, then the processing may become slow, impacting the whole network. Mesh and star topologies can be visualized in the following diagram. PBFT has two main subprotocols, namely normal mode and view change mode. View change mode is triggered when a leader is suspected of being faulty. This approach does work to provide a liveness guarantee to PBFT, but increases communication complexity significantly. Hot Stuff addresses this by merging the view change process with normal mode. This means that nodes can switch to a new view directly without waiting for a threshold of view change messages to be received by other nodes. In PBFT, nodes wait for 2f+1 messages before the view change can occur. But in Hot Stuff, view change can occur directly without requiring a new subprotocol. Instead, the checking of the threshold of the messages to change the view becomes part of the normal view. Just like PBFT, Hot Stuff also solves the SMR problem. Now we'll describe how this protocol works. As we saw earlier, consensus algorithms are described and work under a system model. The model and relevant assumptions under which Hot Stuff works is introduced in the next section. Model. The system is based on a standard BFT assumption of n equals 3f+1 nodes in the system, where f is a faulty node and n is the number of nodes in the network. Nodes communicate with each other via point-to-point message passing, utilizing reliable and authenticated communication links. The network is supposed to be partially synchronous. Hot Stuff makes use of threshold signatures, where a single public key is used by all nodes, but a unique private key is used by each replica. The use of threshold signatures results in the decreased communication complexity of the protocol. In addition, cryptographic hash functions are used to provide unique identifiers for messages. How Hot Stuff works. Hot Stuff works in phases, namely the prepare phase, pre-commit phase, commit phase, and decide phase. We'll now introduce these phases. Prepare. Once a new leader has collected new view messages from n-f nodes, the protocol for the new leader starts. The leader collects and processes these messages to figure out the latest branch in which the highest quorum certificate of prepare messages was formed. Pre-commit. As soon as a leader receives N-F prepare votes, it creates a quorum certificate called Prepare Quorum Certificate. This Prepare Quorum Certificate is broadcast to other nodes as a pre-commit message. When a replica receives the pre-commit message, it responds with a pre-commit vote. The quorum certificate is the indication that the required threshold of nodes has confirmed the request. Commit. When the leader receives N-F pre-commit votes, it creates a pre-commit quorum certificate and broadcasts it to other nodes as the commit message. When replicas receive this commit message, they respond with their commit vote. At this stage, replicas lock the pre-commit quorum certificate to ensure the safety of the algorithm even if view change occurs. Decide. When the leader receives N-F commit votes, it creates a commit quorum certificate. This commit quorum certificate is broadcast to other nodes in the decide message. When replicas receive this decide message, replicas execute the request because this message contains an already committed certificate value. Once the state transition occurs as a result of the decide message being processed by a replica, the new view starts. This algorithm can be visualized in the following diagram. Hot stuff guarantees liveness progress by using pacemaker, which ensures progress after GST within a bounded time interval. This component has two elements. There are time intervals during which all replicas stay at a height for sufficiently long periods. This property can be achieved by progressively increasing the time until progress is made, a decision is made. A unique and correct leader is elected for the height. New leaders can be elected deterministically by using a rotating leader scheme or pseudo-random functions. Safety in hot stuff is guaranteed by voting and relevant commit rules. Liveness and safety are separate mechanisms that allow independent development, modularity, and separation of concerns. Hot stuff is a simple yet powerful protocol that provides linearity and responsiveness properties. It allows consensus without any additional latency at the actual speed of the network. Moreover, it is a protocol that manifests linear communication complexity, thus reducing the cost of communication compared to PBFT-style protocols. It is also a framework in which other protocols such as DLS, PBFT, and Tendermint can be expressed. In this section, we have explored various consensus algorithms in detail. We discuss pre-Bitcoin distributed consensus algorithms and post-Bitcoin proof-of-work POW-style algorithms. Now, a question arises naturally. With the availability of all these different algorithms, which algorithm is best and which one should you choose for a particular use case? We'll try to answer this question in the next section. Choosing an algorithm. Choosing a consensus algorithm depends on several factors. It is not only use case dependent, but some trade-offs may also have to be made to create a system that meets all the requirements without compromising the core safety and liveness properties of the system. We will discuss some of the main factors that can influence the choice of consensus algorithm. Note that these factors are different from the core safety and liveness properties discussed earlier, which are the fundamental requirements needed to be fulfilled by any consensus mechanism. Other factors that we are going to introduce here are use case specific and impact the choice of consensus algorithm. These factors include, but are not limited to, finality, speed, performance, and scalability. Finality. Finality refers to a concept where once a transaction has been completed, it cannot be reverted. In other words, if a transaction has been committed to the blockchain, it won't be revoked or rolled back. This feature is especially important in financial networks, where once a transaction has gone through, the consumer can be confident that the transaction is irrevocable and final. There are two types of finality, probabilistic and deterministic. Probabilistic finality, as the name suggests, provides a probabilistic guarantee of finality, the assurance that a transaction once committed to the blockchain cannot be rolled back builds over time instead of immediately. For example, in Nakamoto consensus, the probability that a transaction will not be rolled back increases as the number of blocks after the transaction commits increases. As the chain grows, the block containing the transaction goes deeper, which increasingly ensures that the transaction won't be rolled back. While this method worked and stood the test of time for many years, it is quite slow. For example, in the Bitcoin network, users usually have to wait for 6 blocks, which is equivalent to an hour, to get the right level of confidence that a transaction is final. This type of finality might be acceptable in public blockchains. Still, such a delay is not acceptable in financial transactions in a consortium blockchain. In consortium networks, we need immediate finality. Deterministic finality or immediate finality provides an absolute finality guarantee for a transaction as soon as it is committed in a block. There are no forks or rollbacks, which could result in a transaction rollback. The confidence level of transaction finality is 100% as soon as the block that contains the transaction is finalized. This type of finality is provided by fault-tolerant algorithms such as PBFT. Speed, performance, and scalability. Performance is a significant factor that impacts the choice of consensus algorithms. POW chains are slower than BFT-based chains. If performance is a crucial requirement, then it is advisable to use voting-based algorithms for permission blockchains such as PBFT, which will provide better performance in terms of quicker transaction processing. There is, however, a caveat that needs to be kept in mind here. PBFT-type blockchains do not scale well, but provide better performance. On the other hand, POW-type chains can scale well, but are quite slow and do not meet the enterprise-grade performance requirements. Performance, scalability, and other challenges will be discussed in detail in Chapter 21, Scalability and Other Challenges. Summary. In this chapter, we explain some of the most prominent protocols in blockchain and traditional distributed system consensus. We covered several algorithms including proof of work, proof of state, traditional BFT protocols, and the latest protocols such as hot stuff. Distributed consensus is a very ripe area of research, and academics and industry researchers are participating in this exciting subject. It is also a deep and vast area of research. Therefore, it is impossible to cover every protocol and all dimensions of this gripping discipline in a single chapter. Nevertheless, the protocols and ideas presented in this chapter provide solid ground for further research and more in-depth exploration. In the next chapter, we'll introduce Bitcoin, which was the first blockchain and cryptocurrency invented in 2009. Chapter 6. Introducing Bitcoin. Bitcoin was the first application of blockchain technology and has started a revolution with the introduction of the very first fully decentralized digital currency. It has proven to be remarkably secure and valuable as a digital currency. However, it is quite unstable and highly volatile. The invention of Bitcoin has also sparked a great interest in academic and industrial research and opened up many new research areas. In this chapter, we shall introduce Bitcoin in detail. Specifically, in this chapter, we will focus our attention upon the fundamentals of Bitcoin, how transactions are constructed and used, transaction structures, addresses, accounts, and mining, over the following topic areas: Bitcoin, an overview, cryptographic keys, transactions, blockchain, mining. Let's begin with an overview of Bitcoin. Bitcoin, an overview. Since its introduction in 2008 by Satoshi Nakamoto, Bitcoin has gained immense popularity and is currently the most successful digital currency in the world, with billions of dollars invested in it. The current market cap at the time of writing for this currency is $168,923,803,898 Its popularity is also evident from the high number of users and investors, the increasing price of Bitcoin, daily news related to Bitcoin,
and the many startups and companies that are offering Bitcoin-based online exchanges. It is now also traded as Bitcoin futures on the Chicago Mercantile Exchange, CME. It is built on decades of research in the field of cryptography, digital cash, and distributed computing. In the following section, a brief history is presented to provide the background required to understand the foundations behind the invention of Bitcoin. Digital currencies have always been an active area of research for many decades. Early proposals to create digital cash go as far back as the early 1980s. In 1982, David Chaum, a computer scientist and cryptographer, proposed a scheme that used blind signatures to build an untraceable digital currency. This research was published in a research paper entitled Blind Signatures for Untraceable Payments. We covered this history in Chapter 1, Blockchain 101, which readers can review if required. In this scheme, a bank would issue digital money by signing a blind and random serial number presented to it by the user. The user could then use the digital token signed by the bank as currency. The limitation of this scheme was that the bank had to keep track of all used serial numbers. This was a centralized system by design and required a trusted party, such as a bank, to operate. Later on in 1988, David Chaum et al. Proposed a refined version named eCash that not only used blind signatures but also some private identification data to craft a message that was then sent to the bank. This scheme allowed the detection of double spending, but did not prevent it. If the same token were used at two different locations, then the identity of the double spender would be revealed. Also, this eCash scheme could only represent a fixed amount of money. Adam Back, a cryptographer and current CEO of Blockstream, who was involved in blockchain development, introduced Hashcash in 1997. It was initially proposed to thwart email spam. The idea behind Hashcash was to solve a computational puzzle that was easy to verify but comparatively difficult to compute. The idea was that for a single user and a single email, the extra computational effort was negligible. But someone sending a large number of spam emails would be discouraged, as the time and resources required to run the spam campaign would increase prohibitively. In 1998, Wei Dai, a computer engineer who used to work for Microsoft, proposed B-Money, which introduced the idea of using proof of work (POW) to create money. The term POW emerged and got popular later with Bitcoin. But in Wei Dai's B-Money, a scheme of creating money was introduced by providing a solution to a previously unsolved computational problem. This concept is similar to POW, where the money is created by broadcasting the solution to a previously unsolved computational problem. A significant weakness in the system was that an adversary with higher computational power could create unsolicited money without allowing the network to adjust to an appropriate difficulty level. The system lacked details on the consensus mechanism between nodes, and some security issues, such as Sybil attacks, were also not addressed. At the same time, Nick Szabo, a computer scientist, introduced the concept of BitGold, which was also based on the POW mechanism but had the same problems as B-Money, with the exception that the network difficulty level was adjustable. Thomas Sander and Amnon Tashma at the International Computer Science Institute, Berkeley, introduced an eCash scheme in a research paper named Auditable Anonymous Electronic Cash in 1999. This scheme for the first time used Merkle trees to represent coins and zero-knowledge proofs to prove the possession of coins. In this scheme, a central bank was required that kept a record of all used serial numbers. This scheme allowed users to be fully anonymous. This was a theoretical design that was not practical to implement due to inefficient proof mechanisms. RPOW, Reusable Proof of Work, was introduced in 2004 by Hale Finney, a computer scientist, developer, and the first person to receive Bitcoin from Satoshi Nakamoto. It used the Hashcash scheme by Adam Back as a proof of computational resources spent to create the money. This was also a central system that kept a central database to keep track of all used POW tokens. This was an online system that used remote attestation made possible by a trusted computing platform, TPM hardware. All the previously mentioned schemes are intelligently designed but had weaknesses in one aspect or another. Specifically, all these schemes rely on a central server that is required to be trusted by the users. Having covered some of the fundamentals of Bitcoin, let's talk about how Bitcoin started. The beginnings of Bitcoin. In 2008, Bitcoin was introduced in a paper called Bitcoin, a peer-to-peer electronic cash system. Satoshi Nakamoto wrote the Bitcoin paper. The name of the author is believed to be a pseudonym, as the true identity of the inventor of Bitcoin is unknown and is the subject of much speculation. The first key idea introduced in the paper was of a purely peer-to-peer electronic cash that does need an intermediary bank to transfer payments between peers. Bitcoin is built on decades of research. Various ideas and techniques from cryptography and distributed computing such as Merkle trees, hash functions, and digital signatures were used to design Bitcoin. Other ideas such as Bitgold, B-Money, Hashcash, and cryptographic timestamping also provided some groundwork for the invention of Bitcoin. Ideas from many of these developments were ingeniously used in Bitcoin to create the first ever truly decentralized currency. Bitcoin solves a number of historically difficult problems related to electronic cash and distributed systems, including the Byzantine generals problem, the double spending problem, Sybil attacks. Bitcoin is an elegant solution to the Byzantine generals problem and the double spending problem. We examined both of these concepts in Chapter 1, Blockchain 101. A Sybil attack is a type of attack where a single adversary creates a large number of nodes with fake identities on the network, which are used to gain influence over the network. This attack is also prevented in Bitcoin by using POW, where miners are required to consume a considerable amount of computing power to earn rewards. If fake nodes try to add fake blocks to the Bitcoin blockchain, they will be rejected because those blocks will not have the required amount of work, that is, the POW associated with them. For an adversary to add a fake block, they will have to work at the same difficulty level as the other honest miners and compete honestly. Otherwise, their work, as long as they do not control more than 51% of the network, will always be rejected by the network due to the insufficient amount of work performed to create blocks. Bitcoin is currently the most valuable cryptocurrency. The value of Bitcoin fluctuates quite heavily, but has increased quite significantly over time, as shown in the following graph. Before we talk about the specifics of Bitcoin, let's briefly discuss the philosophy behind it. Go over the official definition of Bitcoin and consider Bitcoin from a user's perspective before delving deeper into the topic in later sections. Egalitarianism versus authoritarianism. For people with a libertarian ideology, Bitcoin is a platform that can be used instead of banks. However, some think that due to regulations, Bitcoin may become another institution that cannot be trusted. The original idea behind Bitcoin was to develop an eCash system, which requires no trusted third party and where users can be anonymous. If regulations require checks like Know Your Customer, KYC, and detailed information about business transactions to facilitate the regulatory process, then it might be too much information to share. As a result, Bitcoin may not remain attractive to some entities. The regulation of Bitcoin is a controversial subject. As much as it is a libertarian's dream, law enforcement agencies, governments, and banks are proposing various regulations to control it. One prime example is the BIT license issued by New York State's Department of Financial Services, which is a permit issued to businesses that perform activities related to virtual currencies. Due to the high costs and stringent regulatory requirements to obtain a BIT license, many companies have withdrawn their services from New York. There are now many initiatives being taken to regulate Bitcoin, cryptocurrencies, and related activities such as Initial Coin Offering, ICO. The Securities and Exchange Commission, SEC, has recently announced that digital tokens, coins, and relevant activities such as ICOs fall under the category of securities. This announcement means that any digital currency trading platforms will now need to be registered with the SEC, and all relevant securities laws and regulations will be applicable to them. This situation impacted the Bitcoin price directly, and it fell almost 10% on the day this announcement was made. Bitcoin has even been made illegal in some countries. At this point, the question arises that if Bitcoin is under so much pressure from regulatory bodies, then how has it managed to grow so significantly? The simple answer is due to its decentralized and trustless nature. In this context, the term trustless refers to the distribution of trust between users rather than a central entity. No single entity can control this network, and even if some entities try to enforce some regulations, they can only go so far because the network is owned collectively by its users instead of a single entity. It also protected by its POW mechanism, which thwarts any adversarial attacks on the network. The growth of Bitcoin is also due to the so-called network effect, also called demand-side economies of scale. It is a concept that means that the more users use the network, the more valuable it becomes. Over time, an exponential increase has been seen in Bitcoin network growth. This increase in the number of users is mostly driven by financial incentives. Also, the scarcity of Bitcoin and its built-in inflation control mechanism give its value, as there are only 21 million Bitcoins that can ever be mined. Also, the miner reward halves every 4 years, which increases scarcity, and consequently the demand increases even more. Bitcoin definition. Bitcoin can be defined in various ways. It's a protocol, a digital currency, and a platform. It is a combination of a peer-to-peer network, protocols, and software that facilitates the creation and usage of the digital currency. Nodes in this peer-to-peer network talk to each other using the Bitcoin protocol. Decentralization of currency was made possible for the first time with the invention of Bitcoin. Moreover, the double spending problem was solved in an elegant and ingenious way in Bitcoin. The double spending problem arises when, for example, a user sends coins to 2 different users at the same time and they are verified independently as valid transactions. The double spending problem is resolved in Bitcoin by using a distributed ledger, the blockchain, where every transaction is recorded permanently, and by implementing a transaction validation and confirmation mechanism. This process will be explained later in the chapter in the mining section. Bitcoin, a user's perspective. In this section, we will see how the Bitcoin network looks from a user's point of view, how a transaction is made, how it propagates from the user to the network, and how transactions are verified and finally accumulated in blocks. We will look at the various actors and components of the Bitcoin network. Finally, some discussion on how all actors and components interact with each other to form the Bitcoin network will also be provided. First, let's see what the main components of a Bitcoin network are. Bitcoin is composed of the elements in the following list. We will further expand on these elements as we progress through the chapter. Digital keys, addresses, transactions, blockchain, miners, the Bitcoin network, wallets, client software. Now we will see how a user utilizes the Bitcoin network. The following example will help you to understand how the Bitcoin network looks from the end user's perspective. We will see what actors and components are involved in a Bitcoin transaction. One of the most common operations is sending funds to someone else. Therefore, in the following example, we will see how a payment transaction can be sent from one user to another on the Bitcoin network. Sending a payment. This example will demonstrate how money can be sent using the Bitcoin network from one user to another. There are several steps that are involved in this process. In this example, we are using the blockchain wallet for mobile devices. The steps are described as follows. 1. First, either the payment is requested from a user who sends their Bitcoin address to the sender via email or some other means such as SMS, chat applications, or in fact any appropriate communication mechanism. The sender can also initiate a transfer to send money to another user. In both cases, the address of the beneficiary is required. As an example, the blockchain wallet is shown in the following screenshot, where a payment request is being created. 2. The sender either enters the receiver's address or scans the QR code that has the Bitcoin address, amount, and an optional description encoded in it. The wallet application recognizes this QR code and decodes it into something like, "Please send amount BTC to address." 3. With actual values, this will look like the following. Please send 0.00033324 BTC to address. 4. This is also shown in the following screenshot. The QR code shown in the preceding screenshot is decoded, which can be opened as a URL in a Bitcoin wallet. 5. In the wallet application of the sender, this transaction is constructed by following some rules and is then broadcast to the Bitcoin network. This transaction is digitally signed using the private key of the sender before broadcasting it. How the transaction is created, digitally signed, broadcasted, validated, and added to the block will become clear in the following sections. From the user's point of view, once the QR code is decoded, the transaction will appear, similar to what is shown in the following screenshot. Note that in the preceding screenshot there are a number of fields such as from, to, BTC, and fee. While other fields are self-explanatory, it's worth noting that the fee is calculated based on size of the transaction and a fee rate, which is a value that depends on the volume of the transactions in the network at that time. This is measured in satoshis per byte.
Bitcoin network fees ensure that your transaction will be included by miners in the block.
At times in the past, Bitcoin fees were so high that even for smaller transactions, a high fee was charged. This was due to the fact that miners are free to choose which transactions they pick to verify and add to a block, and they naturally select the ones with higher fees. A high number of users creating thousands of transactions also played a role in causing this situation of high fees because transactions were competing with each other to be picked up first, and miners picked up the ones with the highest fees. This fee is also usually estimated and calculated by the Bitcoin wallet software automatically before sending the transaction. The higher the transaction fee, the greater the chances are that your transaction will be picked up as a priority and included in the block. This task is performed by the miners. Mining and miners are concepts that we will look at a bit later in this chapter in the section about mining. Once the transaction is sent, it will appear in the wallet software as shown in the following screenshot. 6. At this stage, the transaction has been constructed, signed, and sent out to the Bitcoin network. This transaction will be picked up by miners to be verified and included in the block. Also note that in the preceding screenshot, confirmation is pending for this transaction. These confirmations will start to appear as soon as the transaction is verified, included in the block, and mined. Also, the appropriate fee will be deducted from the original value to be transferred and will be paid to the miner who has included it in the block for mining.
The transaction flow described in the preceding list is illustrated in the following diagram, where a payment of 0.001267 BTC, approximately $11, originated from the sender's address and has been paid to the receiver's address, starting with 1JZ. The fee of 0.000106622, approximately 95 cents, has also been deducted from the transaction as a mining fee. The preceding diagram visually shows how the transaction flowed on the network from the origin, the sender, to the receivers on the right-hand side. A summary view of various attributes of the transaction is shown in the following screenshot. Looking at the preceding screenshot, there are a number of fields that contain various values. Important fields are listed as follows, with their purpose and explanation. Size. This is the size of the transaction in bytes. Weight. This is the new metric given for the block and transaction sizes since the introduction of the segregated witness, SegWit, soft fork version of Bitcoin. Please see Chapter 7, Bitcoin Network and Payments, for more information on SegWit. Receive time. This is the time when the transaction was received. Included in blocks. This shows the block number on the blockchain in which the transaction is included. Confirmations. This is the number of confirmations completed by miners for this transaction. Total input. This is the number of total inputs in the transaction. Total output. This is the number of total outputs from the transaction. Fees. This is the total fee charged. Fee per byte. This field represents the total fee divided by the number of bytes in the transaction. For example, 10 satoshis per byte. Fee per weight unit. For legacy transactions, this is calculated using the total number of bytes times 4. For SegWit transactions, it is calculated by combining a SegWit marker, flag, and witness field as 1 weight unit, and each byte of the other fields as 4 weight units. The transaction ID of this transaction on the Bitcoin network is D28CA5A59864EA C1C96D3 FD1C23B747 F0DED 8F5A F016 1BAE 8A616 B5 6A1D. This can be further explored using the following link via the services provided by blockchain.info. This transaction ID is available in the wallet software after the transaction has been sent to the network. From there, it can be further explored using one of many Bitcoin blockchain explorers available online. We are using blockchain.info as an example, which can be found here. Bitcoin transactions are serialized for transmission over the network and encoded in hex format. As an example, the transaction shown at the preceding URL is also shown in hex format as follows. We will see later in the transactions section how this hex-encoded transaction can be decoded and which fields make up a transaction. In summary, a payment transaction in the Bitcoin network can be divided into the following steps. 1. The transaction starts with the sender signing the transaction with their private key. 2. The transaction is serialized so that it can be transmitted over the network. 3. The transaction is broadcast to the network. 4. Miners listening for transactions pick up the transaction. 5. The transaction is verified for its legitimacy by the miners. 6. The transaction is added to the candidate proposed block for mining. 7. Once mined, the result is broadcast to all nodes on the Bitcoin network. 8. Usually at this point, users wait for up to 6 confirmations to be received before a transaction is considered final. However, a transaction can be considered final at the previous step. Confirmations serve as an additional mechanism to ensure that there is probabilistically a very low chance for a transaction to be reverted. But otherwise, once a mined block is finalized and announced, the transactions within that block are final at that point. Mining, transactions, and other relevant concepts will become clearer in the following sections in the chapter. Bitcoin, being a digital currency, has various denominations, as shown in the following table. A sender or receiver can request any amount. The smallest Bitcoin denomination is the Satoshi. Bitcoin currency units are described as follows. Now we will introduce the building blocks of Bitcoin. First, we will look at the keys and addresses that are used to represent the ownership and transfer of value on the Bitcoin network. Cryptographic keys. On the Bitcoin network, possession of Bitcoins and the transfer of value via transactions are reliant upon private keys, public keys, and addresses. Elliptic curve cryptography, ECC, is used to generate public and private key pairs in the Bitcoin network. We have already covered these concepts in Chapter 4, Public Key Cryptography, and here we will see how private and public keys are used in the Bitcoin network. Private keys in Bitcoin. Private keys are required to be kept safe and normally reside only on the owner side. Private keys are used to digitally sign the transactions, proving ownership of the Bitcoins. Private keys are fundamentally 256-bit numbers randomly chosen in the range specified by the SEC P256K1 ECDSA curve recommendation. Any randomly chosen 256-bit number from 0x1 to 0xFFFF, FFFF, 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 BAAE, DCE6, AF48, A03B, BFD2, 5E8C, D036, 4140 is a valid private key. Private keys are usually encoded using Wallet Import Format, WIF, in order to make them easier to copy and use. It is a way to represent the full-size private key in a different format. WIF can be converted into a private key and vice versa. The steps are described here. For example, consider the following private key. When converted into WIF format, it looks as shown here. Interested readers can do some experimentation using the tool available at gobitist.appspot.com/private-key. Also, mini private key format is sometimes used to create the private key with a maximum of 30 characters in order to allow storage where physical space is limited. For example, etching on physical coins or encoding in damage-resistant QR codes. More dots can be used for error correction, and less for encoding the private key. A private key encoded using mini private key format is also sometimes called a mini key. The first character of the mini private key is always the uppercase letter S. A mini private key can be converted into a normal-sized private key, but an existing normal-sized private key cannot be converted into a mini private key. This format was used in the Casacious physical bitcoins. The Bitcoin Core client also allows the encryption of the wallet that contains the private keys. As we learned in Chapter 4, Public Key Cryptography, private keys have their own corresponding public keys. Public keys on their own are useless, and private keys on their own are equally of no use. Pairs of public and private keys are required for the normal functioning of any public key cryptography-based systems, such as the Bitcoin blockchain. In the next section, we introduce the usage of public keys in Bitcoin. Public keys in Bitcoin. Public keys exist on the blockchain and all network participants can see them. Public keys are derived from private keys due to their special mathematical relationship with those private keys. Once a transaction signed with the private key is broadcast on the Bitcoin network, public keys are used by the nodes to verify that the transaction has indeed been signed with the corresponding private key. This process of verification proves the ownership of the Bitcoin. Bitcoin uses ECC based on the SECP 256K1 standard. More specifically, it makes use of an elliptic curve digital signature algorithm, ECDSA, to ensure that funds remain secure and can only be spent by the legitimate owner. If you need to refresh the relevant cryptography concepts, you can refer to Chapter 4, Public Key Cryptography, where SEC was explained. Public keys can be represented in uncompressed or compressed format, and are fundamentally X and Y coordinates on an elliptic curve. In uncompressed format, public keys are presented with a prefix of 0x4 in hexadecimal format. X and Y coordinates are both 32 bytes in length. In total, a compressed public key is 33 bytes long, compared to the 65-byte uncompressed format. The compressed version of public keys include only the X part, since the Y part can be derived from it. The reason why the compressed version of public keys works is that if the SCC graph is visualized, it reveals that the Y coordinate can be either below the X-axis or above the X-axis. And as the curve is symmetric, only the location in the prime field is required to be stored. If Y is even, then its value lies above the X-axis, and if it is odd, then it is below the X-axis. This means that instead of storing both X and Y as the public key, only X needs to be stored with the information about whether Y is even or odd. Initially, the Bitcoin client used uncompressed keys, but starting from Bitcoin Core Client 0.6, compressed keys are used as standard. This resulted in an almost 50% reduction of space used to store public keys in the blockchain. Keys are identified by various prefixes, described as follows. Uncompressed public keys use 0x04 as the prefix. Uncompressed public keys are 65 bytes long. They are encoded as 256-bit unsigned big endian integers, 32 bytes, which are concatenated together and finally prefixed with a byte 0x04. This means 1 byte for the 0x04 prefix, 32 bytes for the X integer, and 32 bytes for Y integer, which makes it 65 bytes in total. Compressed public keys start with 0x03 if the Y 32-byte 256 part of the public key is odd. It is 33 bytes in length, as 1 byte is used by the 0x03 prefix, depicting an odd Y, and 32 bytes for storing the X coordinate. Compressed public keys start with 0x02 if the Y 32-byte 256-bit part of the public key is even. It is 33 bytes in length, as 1 byte is used by the 0x02 prefix, depicting an even Y, and 32 bytes for storing the X coordinate. Having talked about private and public keys, let's now move on to another important aspect of Bitcoin, addresses derived from public keys. Addresses in Bitcoin. A Bitcoin address is created by taking the corresponding public key of a private key and hashing it twice. First with the SHA-256 algorithm, and then with RIPE-MD-160. The resultant 160-bit hash is then prefixed with a version number and finally encoded with a base 58 check encoding scheme. The Bitcoin addresses are 26 to 35 characters long and begin with digits 1 or 3. A typical Bitcoin address looks like the string shown here. Addresses are also commonly encoded in a QR code for easy distribution. The QR code of the preceding Bitcoin address is shown in the following image. Currently, there are two types of addresses, the commonly used P2P-KH and another P2SH type, starting with numbers 1 and 3, respectively. In the early days, Bitcoin used direct pay-to-pub-key, which is now superseded by P2P-KH. These types will be explained later in the chapter. However, direct pay-to-pub-key is still used in Bitcoin for Coinbase addresses. Addresses should not be used more than once. Otherwise, privacy and security issues can arise. Avoiding address reuse circumvents anonymity issues to an extent. But Bitcoin has some other security issues as well, such as transaction malleability, Sybil attacks, race attacks, and selfish mining, all of which require different approaches to resolve. Base 58 check encoding. Bitcoin addresses are encoded using the base 58 check encoding. This encoding is used to limit the confusion between various characters such as 0, O, I, 1, as they can look the same in different fonts. The encoding basically takes the binary byte arrays and converts them into human-readable strings. This string is composed by utilizing a set of 58 alphanumeric symbols. More explanation and logic can be found in the base58.h source file in the Bitcoin source code. Now that we have covered private keys, public keys, base58 encoding, and addresses, with that knowledge we can now examine how a Bitcoin address is generated by using all these elements. We briefly touched on it when we introduced addresses in Bitcoin earlier, but now we will see this in more detail with a diagram. The following diagram shows how an address is generated, from generating the private key to the final output of the Bitcoin address. In the preceding diagram, there are several steps that we will now explain. 1. In the first step, we have randomly generated ECDSA private key. 2. The public key is derived from the ECDSA private key. 3. The public key is hashed using the SHA-256 cryptographic hash function. 4. The hash generated in step 3 is hashed using the RIPEMD160 hash function. 5. The version number is prefixed to the RIPEMD160 hash generated in step 4. 6. The result produced in step 5 is hashed using the SHA-256 cryptographic hash function. 7. SHA-256 is applied again. 8. The first 4 bytes of the result produced from step 7 is the address checksum. 9. This checksum is appended to the RIPEMD160 hash generated in step 4. 10. The resultant byte string is encoded into a base58 encoded string by applying the base58 encoding function. 11. Finally, the result is a typical Bitcoin address. In addition to common types of addresses in Bitcoin, there are some advanced types of addresses available in Bitcoin too. We discuss these next. Vanity addresses. As Bitcoin addresses are based on base58 encoding, it is possible to generate addresses that contain human-readable messages. An example is shown as follows. Note that in the first line, the name Bashir appears. Vanity addresses are generated using a purely brute force method. An example of a paper wallet with a vanity address is shown in the following screenshot. In the preceding screenshot on the right-hand bottom corner, the public vanity address is displayed with a QR code. The paper wallets can be stored physically as an alternative to the electronic storage of private keys. Multi-signature addresses. As the name implies, these addresses require multiple private keys. In practical terms, this means that in order to release the coins, a certain set number of signatures is required. This is also known as M of n multisig. Here M represents the threshold or minimum number of signatures required from n number of keys to release the bitcoins. Remember that we discussed this concept in Chapter 4, Public Key Cryptography. With this section, we've finished our introduction to addresses in Bitcoin. In the next section, we will introduce Bitcoin transactions, which are the most fundamental and important aspect of Bitcoin. Transactions. Transactions are at the core of the Bitcoin ecosystem. Transactions can be as simple as just sending some Bitcoins to a Bitcoin address, or can be quite complex depending on the requirements. Each transaction is composed of at least one input and output. Inputs can be thought of as coins being sent that have been created in a previous transaction, and outputs as coins being created. If a transaction is minting new coins, then there is no input and therefore no signature is needed. If a transaction should send coins to some other user, a Bitcoin address, then it needs to be signed by the sender with their private key. In this case, a reference is also required to the previous transaction to show the origin of the coins. Coins are unspent transaction outputs, represented in satoshis. Transactions are not encrypted and are publicly visible on the blockchain. Blocks are made up of transactions, and these can be viewed using any online blockchain explorer. The transaction lifecycle. Now let's look at the lifecycle of a Bitcoin transaction. The steps of the process are as follows. 1. A user-sender sends a transaction using wallet software or some other interface. 2. The wallet software signs the transaction using the sender's private key.
3. The transaction is broadcasted to the Bitcoin network using a flooding algorithm. 4. Mining nodes miners who are listening for the transactions verify and include this transaction in the next block to be mined. Just before the transactions are placed in the block, they are placed in a special memory buffer called the transaction pool. The purpose of the transaction pool is explained in the next section. 5. Next, the mining starts, which is the process through which the blockchain is secured and new coins are generated as reward for the miners who spend appropriate computational resources. Once a miner solves the POW problem, it broadcasts the newly mined block to the network. POW is explained in detail in the mining section. The nodes verify the block and propagate the block further, and confirmations start to generate. 6. Finally, the confirmations start to appear in the receiver's wallet, and after approximately 3 confirmations, the transaction is considered finalized and confirmed. However, 3 to 6 is just a recommended number. The transaction can be considered final even after the first confirmation. The key idea behind waiting for 6 confirmations is that the probability of double spending is virtually eliminated after 6 confirmations. When a transaction is created by a user and sent to the network, it ends up in a special area on each Bitcoin software client. This special area is called the transaction pool or memory pool. Transaction pool, also known as memory pools. These pools are basically created in local memory, computer RAM, by nodes, Bitcoin clients, in order to maintain a temporary list of transactions that have not yet been added to a block. Miners pick up transactions from these memory pools to create candidate blocks. Miners select transactions from the pool after they pass the verification and validity checks. The selection of which transactions to choose is based on the fee and their place in the order of transactions in the pool. Miners prefer to pick up transactions with higher fees. To send transactions on the Bitcoin network, the sender needs to pay a fee to the miners. This fee is an incentive mechanism for the miners. Transaction fees. Transaction fees are charged by the miners. The fee charge is dependent upon the size and weight of the transaction. Transaction fees are calculated by subtracting the sum of the inputs from the sum of the outputs. A simple formula can be used. Fee equals sum inputs minus sum outputs. The fees are used as an incentive for miners to encourage them to include users' transactions in the block the miners are creating. All transactions end up in the memory pool, from where miners pick up transactions based on their priority to include them in the proposed block. The calculation of priority is introduced later in this chapter. However, from a transaction fee point of view, a transaction with a higher fee will be picked up sooner by the miners. There are different rules based on which fee is calculated for various types of actions, such as sending transactions, inclusion in blocks, and relaying by nodes. Fees are not fixed by the Bitcoin protocol and are not mandatory. Even a transaction with no fee will be processed in due course, but may take a very long time. This is, however, no longer practical due to the high volume of transactions and competing investors on the Bitcoin network. Therefore, it is advisable to always provide a fee. The time for transaction confirmation usually ranges from 10 minutes to over 12 hours in some cases. Transaction time is dependent on transaction fees and network activity. If the network is very busy, then naturally, transactions will take longer to process. And if you pay a higher fee, then your transaction is more likely to be picked by miners first, due to the additional incentive of the higher fee. A transaction on the Bitcoin network is represented by a data structure that consists of several fields. We will now introduce the transaction data structure. The transaction data structure. A transaction at a high level contains metadata, inputs, and outputs. Transactions are combined to create a block's body. The transaction data structure is shown in the following table. The following sample transaction is the decoded transaction from the first example of a payment provided at the start of this chapter. As shown in the preceding decoded transaction, there are a number of structures that make up the transaction. All these elements will be described now. Metadata. This part of the transaction contains values such as the size of the transaction, the number of inputs and outputs, the hash of the transaction, and a lock time field. Every transaction has a prefix specifying the version number. These fields are shown in the preceding example as lock, time, size, and version. Inputs. Generally, each input spends a previous output. Each output is considered an unspent transaction output, UTXO, until an input consumes it. A UTXO is an unspent transaction output that can be spent as an input to a new transaction. The transaction input data structure is explained in the following table. In the previous sample, decoded transaction, the inputs are defined under the Inputs section. Outputs. Outputs have 3 fields, and they contain instructions for sending bitcoins. The first field contains the amount of satoshis, whereas the second field contains the size of the locking script. Finally, the third field contains a locking script that holds the conditions that need to be met in order for the output to be spent. More information on transaction spending using locking and unlocking scripts and producing outputs is discussed later in this section. The transaction output data structure is explained in the following table. In the previous sample decoded transaction, 2 outputs are shown under the Out section. Verification. Verification is performed using Bitcoin scripting language, which we will now describe in the next section in detail. The script language. Bitcoin uses a simple stack-based language called script to describe how Bitcoins can be spent and transferred. It is not Turing complete and has no loops to avoid any undesirable effects of long-running hung scripts on the Bitcoin network. This scripting language is based on a 4th programming language, like syntax, and uses a Verret polish notation in which every operand is followed by its operators. It is evaluated from left to right using a last-in, first-out LIFO stack. Scripts are composed of 2 components, namely elements and operations. Scripts use various operations, opcodes, or instructions to define their operations. Elements simply represent data such as digital signatures. Opcodes are also known as words, commands, or functions. Earlier versions of the Bitcoin node software had a few opcodes that are no longer used due to bugs discovered in their design. The various categories of the scripting opcodes are constants, flow control, stack, bitwise logic, splice, arithmetic, cryptography, and lock time. A transaction script is evaluated by combining scriptsig and scriptpubkey. Scriptsig is the unlocking script, whereas scriptpubkey is the locking script. We will now describe how a transaction is unlocked and spent. Scriptsig is provided by the user who wishes to unlock the transaction. Scriptpubkey is a part of the transaction output and specifies the conditions that need to be fulfilled in order to spend the output. In other words, outputs are locked by the scriptpubkey, the locking script, which contains the conditions that when met will unlock the output and the coins can then be redeemed. We will now see the script execution in detail shortly. Commonly used opcodes. In a computer, an opcode is an instruction to perform some operation. For example, ADD is an opcode, which is used for integer addition in Intel CPUs and various other architectures. Similarly, in Bitcoin design, opcodes are introduced that perform several operations related to Bitcoin transaction verification. A description of some of the most commonly used opcodes is listed in the following table, extracted from the Bitcoin Developer's Guide. There are many opcodes in the Bitcoin scripting language, and covering all of them is out of scope of this book. Interested readers can refer to the complete list and relevant details at en.bitcoin.it/wiki/script #opcodes. Now that we've covered the transaction lifecycle and data structure, Let's move on to talk about the types of scripts used to undertake these transactions. Types of scripts. There are various standard scripts available in Bitcoin to handle the verification and value transfer from the source to the destination. These scripts range from very simple to quite complex depending upon the requirements of the transaction. Standard transaction types are discussed here. Standard transactions are evaluated using the IS Standard and IS Standard TX tests, and only those transactions that pass the tests are allowed to be broadcasted or mined on the Bitcoin network. However, non-standard transactions are also allowed on the network, as long as they pass the validity checks. Pay-to-public key hash, P2PKH. P2PKH is the most commonly used transaction type and is used to send transactions to Bitcoin addresses. The format of this type of transaction is shown as follows. The script pubkey and script sig parameters are concatenated together and executed. An example will follow shortly in this section, where this is explained in more detail. Pay-to-script hash, P2SH. P2SH is used in order to send transactions to a script hash, that is, addresses starting with 3, and was standardized in BIP16. In addition to passing the script, the redeem script is also evaluated and must be valid. The template is shown as follows. Multisig pay to multisig. The M of N multi-signature transaction script is a complex type of script where it is possible to construct a script that requires multiple signatures to be valid in order to redeem a transaction. Various complex transactions such as escrow and deposits can be built using this script. The template is shown here. Raw multisig is obsolete, and multisig is now usually part of the P2SH redeem script mentioned in the previous bullet point. Pay to pubkey. This script is a very simple script that is commonly used in Coinbase transactions. It is now obsolete and was used in an old version of Bitcoin. The public key is stored within the script in this case, and the unlocking script is required to sign the transaction with the private key. The template is shown as follows. Null data op return. This script is used to store arbitrary data on the blockchain for a fee. The limit of the message is 40 bytes. The output of this script is unredeemable because op return will fail the validation in any case. Script sig is not required in this case. The template is very simple and is shown as follows. The P2PKH script execution is shown in the following diagram. In the preceding diagram, we have a standard P2PKH script presented on top, which shows both the unlocking script sig and locking script pubkey parts of the script. Recall that in the introduction of the script language, we mentioned that a Bitcoin script is composed of two parts, an unlocking script and a locking script. The unlocking script is composed of sig and pubkey elements which are part of all transaction inputs. The unlocking script satisfies the conditions that are required to consume the output. The locking script defines the conditions that are required to be met to spend the bitcoins. Transactions are authorized by executing both of these parts collectively. Now, focusing again on the previous diagram, we see that in the middle we have a visualization of the stack where the data elements are pushed and popped from. In the bottom section, we show the execution of the script. This diagram shows the step-by-step execution of the script with its outcome on the stack. Now let's examine how this script is executed. 1. In the first step of the data elements, sig and pubkey are placed on the stack. 2. The stack item at the top pubkey is duplicated due to the op-dup instruction, which duplicates the top stack item. 3. After this, the instruction op-hash 160 executes, which produces the hash of pubkey, which is the top element in the stack. 4. Pubkey hash is then pushed onto the stack. At this stage, we have two hashes on the stack, the one that is produced as a result of executing op-hash 160 on pubkey from the unlocking script, and the other one provided by the locking script. 5. Now the op equal verify opcode instruction executes and checks that whether the top two elements, that is, the hashes, are equal or not. If they are equal, the script continues. Otherwise, it fails. 6. Finally, op check sig executes to check the validity of the signatures of the top two elements of the stack. If the signature is valid, then the stack will contain the value true, that is, 1, otherwise false, that is 0. All transactions are encoded into hex format before being transmitted over the Bitcoin network. The following sample transaction is shown in hex format and is retrieved using Bitcoin CLI on the Bitcoin node running on mainnet by using the following command. Scripting is quite limited and can only be used to program one thing, the transfer of Bitcoins from one address to other addresses. However, there is some flexibility possible when creating these scripts, which allows for certain conditions to be put on the spending of the Bitcoins. This set of conditions can be considered a basic form of a financial contract. In other words, we can say that there is a basic support for building contracts in Bitcoin. However, it is not same as smart contracts, which allow the writing of arbitrary programs on the blockchain. We will discuss smart contracts in detail later in Chapter 10, Smart Contracts, but for now we will introduce the concept of contracts in Bitcoin. Contracts. Contracts are Bitcoin scripts that use the Bitcoin blockchain to enforce a financial agreement. This is a simple definition but has far-reaching consequences as it allows users to programmatically create complex contracts that can be used in many real-world scenarios. Contracts allow the development of completely decentralized, independent, and reduced-risk platforms by programmatically enforcing different conditions for unlocking the money, Bitcoins. With the security guarantees provided by the Bitcoin blockchain, it is almost impossible to circumvent these conditions. Various contracts such as escrow, arbitration, and micropayment channels can be built using the Bitcoin scripting language. The current implementation of the script language is minimal, but it is still possible to develop various types of complex contracts. For example, we could set the release of funds to be allowed only when multiple parties sign the transaction, or release the funds only after a specific amount of time has elapsed. Both of these scenarios can be realized using the multi-sig and transaction lock time options. Even though the scripting language in Bitcoin can be used to create complex contracts, it is quite limited and is not at all on par with the smart contracts, which are Turing-complete constructs and allow arbitrary program development. Recently, however, there has been more advancement in this area. A new smart contract language for Bitcoin has been announced, called Miniscript, which will be discussed next. Miniscript. This language allows for a more structured approach to writing Bitcoin scripts. Even though Bitcoin script supports combinations of different spending conditions, such as time and hash locks, it is not easy to analyze existing scripts or build new complex scripts. Miniscript makes it easier to write complex spending rules. It also makes it easier to ascertain the correctness of the script. Currently, Miniscript supports P2WSH and P2SH, P2WSH, and offers limited support for P2SH. Coinbase transactions. A Coinbase transaction or generation transaction is always created by a miner and is the first transaction in a block. It is used to create new coins. It includes a special field also called the Coinbase, which acts as an input to the Coinbase transaction. This transaction also allows up to 100 bytes of arbitrary data storage. A Coinbase transaction input has the same number of fields as a usual transaction input, but the structure contains the Coinbase data size and fields instead of the unlocking script size and fields. Also, it does not have a reference pointer to the previous transaction. This structure is shown in the following table. All transactions in the Bitcoin system go under a validation mechanism. We introduce how Bitcoin transactions are validated in the next section. Transaction validation. This verification process is performed by Bitcoin nodes. There are three main things that nodes check when verifying a transaction. 1. The transaction inputs are previously unspent. This validation step prevents double spending by verifying that the transaction inputs have not already been spent by someone else. 2. That the sum of the transaction outputs is not more than the total sum of the transaction inputs. However, both input and output sums can be the same, or the sum of the input total value could be more than the total value of the outputs. This check ensures that no new bitcoins are created out of thin air. 3. That the digital signatures are valid, which ensures that the script is valid. Even though transaction construction and validation are generally a secure and sound process, some vulnerabilities exist in Bitcoin. We will now introduce some of Bitcoin's infamous shortcomings. Transaction bugs. The following are two major Bitcoin vulnerabilities that have been infamously exploited. Transaction malleability. Transaction malleability is a Bitcoin attack that was introduced due to a bug in the Bitcoin implementation. Due to this bug, it became possible for an adversary to change the transaction ID of a transaction, thus resulting in a scenario where it would appear that a certain transaction has not been executed. This can allow scenarios where double deposits or withdrawals can occur. In other words, this bug allows the changing of the unique ID of a Bitcoin transaction before it is confirmed. If the ID is changed before confirmation without making the transaction valid, it would seem that the transaction did not occur at all, which can then give the false impression that the transaction has not been executed, thus allowing double deposit or withdrawal attacks. Value overflow. This incident is one of the most well-known events in Bitcoin history. On August 15, 2010, a transaction was discovered that created roughly 184 billion Bitcoins. This problem occurred due to the integer overflow bug, where the amount field in the Bitcoin code was defined as a signed integer instead of an unsigned integer. This bug means that the amount can also be negative, and resulted in a situation where the outputs were so large that the total value resulted in an overflow. To the validation logic in Bitcoin code, all appeared to be correct, and it looked like the fee was also positive after the overflow. This bug was fixed via a soft fork. More on this in the blockchain section, quickly after its discovery. Now that we understand the fundamentals of how Bitcoin transactions work and we appreciate some of the security-related aspects of Bitcoin, let's now look at the Bitcoin blockchain, which is the foundation of the Bitcoin cryptocurrency. Blockchain. As we discussed in Chapter 1, Blockchain 101, a blockchain is a distributed ledger of transactions. Specifically from Bitcoin's perspective, the blockchain can be defined as a public distributed ledger holding a time-stamped, ordered, and immutable record of all transactions on the Bitcoin network. Transactions are picked up by miners and bundled into blocks for mining. Each block is identified by a hash and is linked to its previous block by referencing the previous block's hash in its header. The data structure of a Bitcoin block is shown in the following table. The block header mentioned in the previous table is the data structure that contains several fields. This is shown in the following table. The following diagram provides a detailed view of the blockchain structure. As shown in the following diagram, blockchain is a chain of blocks where each block is linked to its previous block by referencing the previous block header's hash. This linking makes sure that no transaction can be modified unless the block that records it and all blocks that follow it are also modified. The first block is not linked to any previous block and is known as the Genesis block. The preceding diagram shows a high-level overview of the Bitcoin blockchain. On the left-hand side, blocks are shown starting from bottom to top. Each block contains transactions and block headers, which are further magnified on the right-hand side. At the top, first, the block header is enlarged to show various elements within the block header. Then on the right-hand side, the Merkle root element of the block header is shown in magnified view, which shows how Merkle root is constructed. We have discussed Merkle trees in detail previously, You can refer to Chapter 4, Public Key Cryptography, if you need to revise the concept. Further down the diagram, transactions are also magnified to show the structure of a transaction and the elements that it contains. Also note that transactions are then further elaborated to show what locking and unlocking scripts look like. The size, in bytes, of each field of block, header, and transaction is also shown as a number under the name of the field. Let's move on to discuss the first block in the Bitcoin blockchain, the Genesis block. The Genesis block. This is the first block in the Bitcoin blockchain. The Genesis block was hard-coded in the Bitcoin Core software. In the Genesis block, the Coinbase transaction included a comment taken from the Times newspaper. This message is a proof that the first Bitcoin block, Genesis block, was not mined earlier than January 3, 2009. This is because the Genesis block was created on January 3, 2009, and this news excerpt was taken from that day's newspaper. The following representation of the Genesis block code can be found in the chainparams.cpp file available at github.com/bitcoin/bitcoin/blob/master/src/chainparams.cpp:. Bitcoin provides protection against double spending by enforcing strict rules on transaction verification and via mining. Transactions and blocks are added to the blockchain only after the strict rule checking explained in the transaction validation section on successful POW solutions. Block height is the number of blocks before a particular block in the blockchain. POW is used to secure the blockchain. Each block contains one or more transactions, out of which the first transaction is the Coinbase transaction. There is a special condition for Coinbase transactions that prevent them from being spent until at least 100 blocks have passed in order to avoid a situation where the block may be declared stale later on. Stale blocks are old blocks that have already been mined. Miners who keep working on these blocks due to a fork where the longest chain, main chain, has already progressed beyond those blocks are said to be working on a stale block. In other words, these blocks exist on a shorter chain and will not provide any reward to their miners. Orphan blocks are a slightly different concept. Their parent blocks are unknown. As their parents are unknown, they cannot be validated. This problem occurs when two or more miners discover a block at almost the same time. These are valid blocks and were correctly discovered at some point in the past, but now they are no longer part of the main chain. The reason why this occurs is that if there are two blocks discovered at almost the same time, the one with a larger amount of POW will be accepted and the one with a lower amount of work will be rejected. Similar to stale blocks, they do not provide any reward to their miners. We can see this concept visually in the following diagram. In the preceding introduction of stale blocks, we introduced a new term, a fork. A fork is a condition that occurs when two different versions of the blockchain exist. It is acceptable in some conditions and detrimental in a few others. There are different types of forks that can occur in a blockchain: temporary forks, soft forks, hard forks. Because of the distributed nature of Bitcoin, network forks can occur inherently. In cases where two nodes simultaneously announce a valid block, it can result in a situation where there are two blockchains with different transactions. This is an undesirable situation, but can be addressed by the Bitcoin network only by accepting the longest chain. In this case, the smaller chain will be considered orphaned. If an adversary manages to gain control of 51% of the network hash rate, computational power, then they can impose their own version of the transaction history. Forks in a blockchain can also occur with the introduction of changes to the Bitcoin protocol. In the case of a soft fork, a client that chooses not to upgrade to the latest version supporting the updated protocol will still be able to work and operate normally. In this case, new and previous blocks are both acceptable, thus making a soft fork backward compatible. Miners are only required to upgrade to the new soft fork client software in order to make use of the new protocol rules. Planned upgrades do not necessarily create forks.
because all users should have updated already. A hard fork, on the other hand, invalidates previously valid blocks and requires all users to upgrade. New transaction types are sometimes added as a soft fork, and any changes such as block structure changes or major protocol changes result in a hard fork. As Bitcoin evolves and new upgrades and innovations are introduced in it, the version associated with blocks also changes. These versions introduce various security parameters and new features. The latest Bitcoin block version is 4, which was proposed with BIP65 and has been used since Bitcoin Core Client 0.11.2. Since the implementation of BIP9, bits in the N version field are used to indicate soft fork changes. Size of the blockchain. Bitcoin is an ever-growing chain of blocks and is increasing in size. The current size of the Bitcoin blockchain stands at approximately 269 gigabytes. The following figure shows the increase in size of the blockchain over time. As the chain grows and more miners are added to the network difficulty also increases. Network difficulty. Network difficulty refers to a measure of how difficult it is to find a new block, or in other words, how difficult it is to find the hash below the given target. New blocks are added to the blockchain approximately every 10 minutes, and the network difficulty is adjusted dynamically every 2016 blocks in order to maintain a steady addition of new blocks to the network. Network difficulty is calculated using the following equation. Target equals previous target times time divided by 2016 times 10 minutes. Difficulty and target are interchangeable and represent the same thing. The previous target represents the old target value, and time is the time spent to generate the previous 2016 blocks. Network difficulty essentially means how hard it is for miners to find a new block. That is, how difficult the hashing puzzle is now. In the next section, mining is discussed, which will explain how the hashing puzzle is solved. Mining. Mining is a process by which new blocks are added to the blockchain. Blocks contain transactions that are validated via the mining process by mining nodes on the Bitcoin network. Blocks, once mined and verified, are added to the blockchain, which keeps the blockchain growing. This process is resource-intensive due to the requirements of POW, where miners compete to find the number less than the difficulty target of the network. This difficulty in finding the correct value, also called sometimes the mathematical puzzle, is there to ensure that miners have spent the required resources before a new proposed block can be accepted. The miners mint new coins by solving the POW problem, also known as the partial hash inversion problem. This process consumes a high amount of resources, including computing power and electricity. This process also secures the system against fraud and double spending attacks, while adding more virtual currency to the Bitcoin ecosystem. Roughly one new block is created, mined every 10 minutes to control the frequency of generation of Bitcoins. This frequency needs to be maintained by the Bitcoin network. It is encoded in the Bitcoin Core Client to control the money supply. Approximately 144 blocks, that is 1,728 Bitcoins, are generated per day. The number of actual coins can vary per day, however the number of blocks remains at an average of 144 per day. Bitcoin supply is also limited. In 2140, all 21 million Bitcoins will be finally created, and no new Bitcoins can be created after that. Bitcoin miners, however, will still be able to profit from the ecosystem by charging transaction fees. Tasks of the miners. Once a node connects to the Bitcoin network, there are several tasks that a Bitcoin miner performs. 1. Syncing up with the network. Once a new node joins the Bitcoin network, it downloads the blockchain by requesting historical blocks from other nodes. This is mentioned here in the context of the Bitcoin miner. However, this is not necessarily a task that only concerns miners. 2. Transaction validation. Transactions broadcast on the network are validated by full nodes by verifying and validating signatures and outputs. 3. Block validation. Miners and full nodes can start validating blocks received by them by evaluating them against certain rules. This includes the verification of each transaction in the block along with verification of the nonce value. 4. Create a new block. Miners propose a new block by combining transactions broadcast on the network after validating them. 5. Perform POW. This task is the core of the mining process, and this is where miners find a valid block by solving a computational puzzle. The block header contains a 32-bit nonce field, and miners are required to repeatedly vary the nonce until the resultant hash is less than the predetermined target. 6. Fetch reward. Once a node solves the hash puzzle, POW, it immediately broadcasts the results, and other nodes verify it and accept the block. There is a slight chance that the newly minted block will not be accepted by other miners on the network due to a clash with another block found at roughly the same time. But once accepted, the miner is rewarded with 12.5 bitcoins and any associated transaction fees. We've discussed the tasks. Let's now consider the rewards for performing them. Mining rewards. Miners are rewarded with new coins if and when they discover new blocks by solving the POW. Miners are paid transaction fees in return for the transactions in their proposed blocks. New blocks are created at an approximate fixed rate of every 10 minutes. The rate of creation of new bitcoins decreases by 50% every 210,000 blocks, which is roughly every 4 years. When Bitcoin started in 2009, the mining reward used to be 50 bitcoins. After every 210,000 blocks, the block reward halves. In November 2012, it halved down to 25 bitcoins. Currently, since May 2020, it is 6.25 bitcoins per block. This mechanism is hard-coded in Bitcoin to regulate and control inflation and limit the supply of bitcoins. In order for miners to earn the reward, they have to show that they have solved the computational puzzle. This is called the POW. Proof of work. This is a proof that enough computational resources have been spent in order to build a valid block. POW is based on the idea that a random node is selected every time to create a new block. In this model, nodes compete with each other in proportion to their computing capacity in order to be selected. The following equation sums up the POW requirement in Bitcoin. Here, n is a nonce, p hash is a hash of the previous block. Tx represents transactions in the block, and target is the target network difficulty value. This means that the hash of the previously mentioned concatenated fields should be less than the target hash value. The only way to find this nonce is the brute force method. Once a certain pattern of a certain number of zeros is met by a miner, the block is immediately broadcast and accepted by other miners. The mining algorithm. The mining algorithm consists of the following steps. 1. The previous block's header is retrieved from the Bitcoin network. 2. Assemble a set of transactions broadcast on the network into a block to be proposed. 3. Compute the double hash of the previous block's header, combined with a nonce and the newly proposed block, using the SHA-256 algorithm. 4. Check if the resulting hash is lower than the current difficulty level, the target, then POW is solved. As a result of successful POW, the discovered block is broadcasted to the network and miners fetch the reward. 5. If the resultant hash is not less than the current difficulty level, target, then repeat the process after incrementing the nonce. As the hash rate of the Bitcoin network increased, the total amount of the 32-bit nonce was exhausted too quickly. In order to address this issue, the extra nonce solution was implemented, whereby the Coinbase transaction is used to provide a larger range of nonces to be searched by the miners. This process is visualized in the following flowchart. Mining difficulty increases over time, and bitcoins that could once be mined by a single CPU laptop computer now require dedicated mining centers to solve the hash puzzle. The current difficulty level can be queried through the Bitcoin command line interface using the following command: $Bitcoin-CLI get difficulty. This generates something like the following. This number represents the difficulty level of the Bitcoin network. Recall from previous sections that miners compete to find a solution to a problem. This number in fact shows how difficult it is to find a hash lower than the network difficulty target. All successfully mined blocks must contain a hash that is less than this target number. This number is updated every 2 weeks or 2016 blocks to ensure that, on average, the 10-minute block generation time is maintained. Bitcoin network difficulty has increased in a roughly exponential fashion. The following graph shows this difficulty level over a period of 1 year. The preceding graph shows the difficulty of the Bitcoin network over last year, and it has increased quite significantly. The reason why mining difficulty increases is because, in Bitcoin, the block generation time always has to be around 10 minutes. This means that if blocks are being mined too quickly because of faster hardware, the difficulty increases accordingly so that the block generation time can remain at roughly 10 minutes per block. This phenomenon is also true in reverse. If blocks take longer than 10 minutes on average to mine, then the difficulty is decreased. The difficulty is calculated every 2016 blocks, around 2 weeks, and adjusted accordingly. If the previous set of 2016 blocks were mined in a period of less than 2 weeks, then the difficulty increases. Similarly, if 2016 blocks were found in more than 2 weeks, bearing in mind that if blocks are mined every 10 minutes, then 2016 blocks take 2 weeks to be mined. Then the difficulty is decreased. The Bitcoin miners have to calculate hashes to solve the POW algorithm. If the difficulty goes up, then a higher hash rate is required to find the blocks. The difficulty increases accordingly if more hashing power is added due to more miners joining the network. Now let's explain the hash rate in a bit more detail. The hash rate. The hash rate basically represents the rate of hash calculation per second. In other words, this is the speed at which miners in the Bitcoin network are calculating hashes to find a block. In the early days of Bitcoin, it used to be quite small, as CPUs were used, which are relatively weak in mining terms. However, with dedicated mining pools and application-specific integrated circuits, ASICs, now this has gone up exponentially in the last few years. This has resulted in increased difficulty in the Bitcoin network. The following hash rate graph shows the hash rate increases over time and is currently measured in exahashes. This means that in 1 second, Bitcoin network miners are computing more than 24 quintillion hashes per second. Mining systems. Over time, Bitcoin miners have used various methods to mine Bitcoins, as the core principle behind mining is based on the double SHA-256 algorithm. Over time, experts have developed sophisticated systems to calculate the hash faster and faster. The following is a review of the different types of mining methods used in Bitcoin and how they evolved with time. CPU. CPU mining was the first type of mining available in the original Bitcoin client. Users could even use laptop or desktop computers to mine Bitcoins. CPU mining is no longer profitable, and now more advanced mining methods, such as ASIC-based mining, are used. CPU mining only lasted for around a year from the introduction of Bitcoin, and soon other methods were explored and tried by the miners. GPU. Due to the increased difficulty of the Bitcoin network and the general tendency of finding faster methods to mine, miners started to use the GPUs or graphics cards available in PCs to perform mining. GPUs support faster and parallelized calculations that are usually programmed using the OpenCL language. This turned out to be a faster option as compared to CPUs. Users also use techniques such as overclocking to gain maximum benefit of the GPU power. Also, the possibility of using multiple graphics cards in parallel increased the popularity of graphics cards usage for Bitcoin mining. GPU mining, however, has some limitations, such as overheating and the requirement for specialized motherboards and extra hardware to house multiple graphics cards. From another angle, graphics cards have become quite expensive due to increased demand, and this has impacted gamers and graphics software users. FPGA. Even GPU mining did not last long, and soon miners found another way to perform mining using Field Programmable Gate Arrays, FPGAs. An FPGA is basically an integrated circuit that can be programmed to perform specific operations. FPGAs are usually programmed in hardware description languages, HDLs such as Verilog and VHDL. Double SHA-256 quickly became an attractive programming task for FPGA programmers, and several open-source projects were started too. FPGA offered much better performance compared to GPUs. However, issues such as accessibility, programming difficulty, and the requirement for specialized knowledge to program and configure FPGAs resulted in a short life for the FPGA era of Bitcoin mining. Mining hardware such as the X6500 miner, ZTEX, and Icarus were developed during the time when FPGA mining was profitable. Various FPGA manufacturers such as Xilinx and Altera produce FPGA hardware and development boards that can be used to program mining algorithms. The arrival of ASICs resulted in the quick phasing out of FPGA-based systems for mining. It should be noted that GPU mining is still profitable for some other cryptocurrencies to some extent, such as Zcoin, but not Bitcoin because the network difficulty of Bitcoin is so high that only ASICs, specialized hardware running in parallel, can produce reasonable profit. ASICs were designed to perform SHA-256 operations. These special chips were sold by various manufacturers and offered a very high hashing rate. This worked for some time, but due to the quickly increasing mining difficulty level, single-unit ASICs are no longer profitable. Currently, mining is out of the reach of individuals due to the vast amounts of energy and money needed to be spent in order to build a profitable mining platform. Now, professional mining centers using thousands of ASIC units in parallel are offering mining contracts to users to perform mining on their behalf. There is no technical limitation. A single user can run thousands of ASICs in parallel, but it will require dedicated data centers and hardware, therefore the cost for a single individual can become prohibitive. Examples of these four types of hardware are shown in the following photographs. Mining pools. A mining pool forms when a group of miners work together to mine a block. The pool manager receives the Coinbase transaction if the block is successfully mined, and is then responsible for distributing the reward to the group of miners who invested resources to mine the block. This is more profitable than solo mining, where only one sole miner is trying to solve the partial hash inversion function, hash puzzle, because in mining pools, the reward is paid to each member of the pool, regardless of whether they, or more specifically, their individual node solve the puzzle or not. There are various models that a mining pool manager can use to pay to the miners, such as the pay-per-share model and the proportional model. In the pay-per-share model, the mining pool manager pays a flat fee to all miners who participated in the mining exercise, whereas in the proportional model, the share is calculated based on the amount of computing resources spent to solve the hash puzzle. Many commercial pools now exist and provide mining service contracts via the cloud and easy-to-use web interfaces. The most commonly used ones are Antpool, BTC, and BTC.top. A comparison of the hashing power of all major mining pools is shown in the following pie chart. Mining centralization can occur if a pool manages to control more than 51% of the network by generating more than 51% of the hash rate of the Bitcoin network. As discussed earlier in the introduction section, a 51% attack can result in successful double spending attacks, and it can impact consensus, and in fact even impose another version of the transaction history on the Bitcoin network. This event has happened once in Bitcoin history, when ghash.io, a large mining pool, managed to acquire more than 51% of the network capacity. Theoretical solutions such as two-phase POW have been proposed in academia to disincentivize large mining pools. This scheme introduces a second cryptographic puzzle that results in mining pools either revealing their private keys or providing a considerable portion of the hash rate of their mining pool.
thus reducing the overall hash rate of the pool. Various types of hardware are commercially available for mining purposes. Currently, the most profitable one is ASIC mining, and specialized hardware is available from a number of vendors such as Antminer, Avalon Miner, and Watts Miner. Solo mining is not very profitable now, unless a vast amount of money and energy is spent to build your own mining rig or even a data center. With the current difficulty factor as of June 2020, if a miner manages to produce a hash rate of 60 trillion hashes per second, they can hope to make 0.000478 BTC, around 1 penny per day and around $4 a year, which is extremely low compared to the investment required to source the equipment that can produce 60 terahashes. Including running costs such as electricity, this turns out to be not very profitable at all. For example, the Antminer S9 is an efficient ASIC miner that produces a hash power of 13.5 terahashes, and seems like it can produce some profit per day, which is true. However, a single Antminer S9 costs around 1,700 GPB, and when combined with the cost of electricity, the return on investment is only realized after almost a year's mining, when it produces around 0.3 BTC. It may still seem an okay investment, but also think about the fact that the Bitcoin network difficulty keeps going up with time. So over a year it will become more difficult to mine, and the mining hardware will expend its utility in a few months. The race to build efficient miners is on and is only expected to grow. A recent addition to the ASIC miners market is the Dragon Mint T1 miner, which operates at 16 terahashes. Summary. This chapter started with an introduction to Bitcoin and explained how a transaction works from the user's point of view. Then an introduction to transactions from a technical point of view was presented. After this, the public and private keys used in Bitcoin were discussed. In the next section, we introduced addresses and their different types, followed by a discussion on transactions and their types and usage. Following on from this, we looked at Bitcoin with a detailed explanation of how blockchain works and the various components included in the Bitcoin blockchain. In the last few sections of the chapter, mining processes and relevant concepts such as hardware systems, their limitations, and Bitcoin rewards were introduced. In the next chapter, we will examine concepts related to the Bitcoin network, its elements, and client software tools.